flatness in these geometric situations, let's say, for a morphism of algebraic spaces. Intuitively, it means that x over y is really a nice, smooth family of algebraic spaces parameterized by the different points of y. What could happen, you see, if we had something altogether, if we didn't have anything like flatness or some topological substitute for it, is that the fibers of x over y could have dimensions which jump pretty badly. For instance, assume y, for instance, to be a line, and then x, for instance, could be something like this. It's a union of a line and a vertical, and you map this onto the line by the projection. So the fiber of a point here is just one point, and all of a sudden, if you pass over to this point in the center, this fiber is of dimension 1. I mean, these things cannot happen if you have flatness. And there are a large number, you see, of standard theorems on algebraic geometry, which show that a posteriori, if you want, you couldn't say it a priori, that flatness has all the right properties so that you can deal very nicely with flat families. There's the invariance, for instance, of characteristic polynomials, and there is the existence of Hilbert schemes and such things. I mean, everything tied up with flatness. But in fact, everything finally does boil down to the very down-to-earth, silly definition of flatness, that it makes the tensor product exact, you see. But the tensor product plays a really very important role in algebraic geometry. Because, I mean, all constructions, practically, inverse images of modules or products of algebraic varieties, etc., they're all involved with these tensor products. So whatever, any important notion concerning related with the tensor product will play a basic role in algebraic geometry.
Further question? Would that, in the same direction, would that, the argument that you're giving there with the check homology say that the diagonal x cross x is a closed subscheme of the scheme x cross x, with x cross x is the scheme? Is this the argument that you're making with the Cohen-Roscoe argument that you're making?
So the question is whether the cohomology argument gives this result or what?
Yes.
Well, I don't know. What's the need for getting another proof than this one of this result, after all? That x tensor y goes to xy, define the surjective map of A tensor A to A. I mean, that's what it means that the diagonal is closed.
Yeah.
So I mean, there's nothing more you need. Once you have translated the statement in terms of commutative algebra, it becomes a tautological truth. So you don't have to look at complexes and such things in order to prove it. Maybe you are thinking of something else, of non-offense case. Then you may have trouble with. You have slightly more trouble with homology when the diagonal is not closed, but because the intersection of two affine subsets may not be affine. I mean, that's not to say it. All right. Are there any more questions concerning the last talks, perhaps? Anyhow, we are not going to use all those German nonsense about complexes, I think, in this course. We do not have time really to work with cohomology. So therefore, if some of you didn't follow this German nonsense business, it's not too serious. It doesn't mean that you wouldn't be able to follow the rest. So I want to state a few compliments to some things we did the last times concerning in particular the operations, sums and products and such things within the category C of affine algebraic spaces over K. So one important property of sums within here, which kind of shows that this category C is kind of geometric. Behaves like objects in there behave like sets or spaces or so with respect to new operations. It is that we saw that in this category finite sums exist. In fact, even infinite sums, but they are kind of silly. The finite sums, the infinite sums which would exist within this category wouldn't be good because for example, in the category of all schemes, let's say, so they're not interesting. But finite sums, they are nice. We have seen that finite sums of affine algebraic spaces xi just correspond our dictionary to finite products of algebras over K. And now what I want to say is that these finite sums are disjoint and universal. And I will recall for those who have not followed the course on topoi what this means. If we have in the category C, if we have a set of objects indexed by set I, xi, mapped into an x, and such that x becomes the sum of the xi's by this set of maps, we will say that the sum is disjoint if the following is true. First of all, these morphisms ui are monomorphisms. And second, that for every set of indices I and j which are different, distinct indices, if you look at the fibered product of xi and xj over x, which could be interpreted as intersection of xi and xj, once we know that xi and xj are sub-objects of x, that we have monomorphisms here. That this is an initial object of the category. So think of a set which is the sum of subsets, that means the disjoint union of them. Then these properties just mean that the xi's are actually subsets and that the intersection of two of them is empty. And second, in the category we say that a sum is universal. If the following is true, whenever we have a base change x prime goes to x, so that we can take now the inverse images of the xi's to be x prime i's lying over x prime. So we have now a family of morphisms with target x prime indexed by the same set I. So we get therefore a morphism of x prime of the direct sum of the x prime i's into x prime. And we want this to be an isomorphism for every base change x prime goes to x. By the way, the fact that the ui's are monomorphisms can be expressed also as saying that the fibered product of xi with itself over x, so taking the case I equals j here, is just isomorphic by the diagonal morphism of xi itself. So to say that the sums are disjoint means that the sum is disjoint means that the fibered products of any two of the xi and xj's over x is what one might naturally expect it to be. Of course, you see, in categories like additive categories, sums are practically never disjoint. And this is a basic kind of property which there are a number of exactness properties of the category of sets which are kind of autodual and taken together, you see, and it should be true also or additive categories. And this perhaps is the one key property, which is by no means only rule you see, which will be true for a catalog of sets, for a catalog of topological spaces, catalog of schemes, or algebraic spaces, etc. So for things which look like geometric, so to say, and which will be false for the duals of these categories or for any additive category, except if it's a point and if it's equivalent to the one-point category. All right, so that's the statement. That's the definition, and the statement is that in the case of affine algebraic algebras, of affine algebraic space, cis over k, the finite sums are disjoint and universal. All right, now let's prove this. So I think we have to interpret it in terms of commutative algebra in order to prove it. So X corresponds to ring A, which is the product of the finite number of rings AI which describe the xi's, and the morphism from xi into X corresponds to the projections of this A to the factors AI. And so first what we have to prove the disjointness is if I is different from J. So we have to prove that the xi goes to xi monomorphisms, but this comes from the fact that the projection of A into one object, the AI, is surjective. So in fact, as we have already noticed, xi goes to x is a lot more than a monomorphism. It's in fact a closed inversion. All right. Now let's look what happens for I different from J. We have to prove that the tensor product of AI and AJ over A is equal to the zero ring, because this means that the corresponding affine algebraic space is the empty one. All right. Now we know on the other hand that, well, I mean, this decomposition of A as a product of rings AI corresponds to giving a set of idempotents in A, such that the sum of these idempotents is equal to 1, and that they are mutually orthogonal. All right. Now let's take the idempotent EI in A, corresponding to the index I. So if we map A into AI, EI is mapped into the unit element, and if we map A into any other AJ, it's mapped into 0. That's in fact the description of EI in terms of the product decomposition of A. Now, the tensor product of AI and AJ over A solves the universal problem of mapping AI and AJ into a ring B in such a way that the square commutes. But then 1 and one element here and the 0 element here should give the same image in B, namely the image of EI. That means that in B 1 is equal to 0, and that B is a 0 ring. And so that must be true also when I take B to be the tensor product. So that shows the disjointness. And now, what does universal mean? So we have to look at the space change. X prime goes to X, that corresponds to ring homomorphism. A goes to A prime. And we have to show that if we take the tensor products of AI and A prime over A for every I, so we get homomorphisms of A prime into the A prime I's, we have to prove that the corresponding homomorphism, which goes from A prime into the product of the A prime I, is an isomorphism. But I think that we have seen this essentially when we have spoken about homomorphisms of a product of algebras into another algebra. Taking again these EIs in A, the images in A prime will be idempotence E prime I, which will satisfy the same relations. They will have some 1 and they will be mutually orthogonal. So this will correspond to the decomposition of A prime into a product of rings A prime I, and it's pretty clear that these ring A prime I, they are just the quotient of A prime divided by 1 minus E prime I, that's it, A prime, whereas AI was the quotient of A by 1 minus EIA. And of course, if you make the base change, by A goes into A prime from this algebra to get an algebra of A prime, then this algebra is transformed to this one. All right, so that does it. Now let's give various consequences of the fact, for instance, that sums are universal, which are pretty much used whenever this property is true in a category. This shows, for instance, that sums, let's say finite sums here, but the same would be true if we assume that there are infinite sums and that they're universal. But here we are dealing with finite sums. So look at an object which is a sum of object xi and another y which is a sum of objects yj. I take finite sums throughout. We can then take the products of every one of the xi's by yj, get here a sum, and this is in a natural way mapped into here. That's true in any category where the various expressions written down make a sense. Because for every ij, xi is mapped into x and yj into y, therefore xi times yj is to mapped in x times y. And this being so for every pair of indices, we get them all mapped from the sum like here. What I claim is that if sums are universal, then this must be an isomorphism. So things happen just the same as for the Welsh situations we are accustomed to, working with sets or political spaces or variety, differential varieties or Lie space or whatever. Now, how is this proved in terms of the property of universalness of sums? We are reduced, of course, to prove distributivity of products with respect to sums to the case when one of the factors doesn't move. Either one by symmetry of the product. So we are reduced to proving the property that the product of the sum of the xi's by sum y is equal to the sum of the xi times y. All right, now let's write the situation. We have the xi's which are mapped to x, which is their sum. And now let's look at x times y, which we're interested in. We view it as lining over x. In fact, it's a base change. If you do have a final object, let's assume it for simplicity, it would be just the base change of the object y over e by x goes to e, by the unique morphism from x to the final object. This remark I make just in order to show that the base change x times y is over x by this morphism xi goes to x is just xi times y because of the sensitivity of base changes. But I mean it would be trivial otherwise too. Alright. So we have this Cartesian diagram for every I. The base change of this with respect to this base change. The inverse image of this with respect to this base change is xi times y. All right, and the universalness of sum just says that all right, but I will take rather the opposite. I will take it the opposite way, or symmetrically, the base change. If the inverse image of xi over x by this base change is xi times y. That's the way we are going to look at it. And therefore, if I look at the variable I, x times y must be the sum of the xi times y. That's the universalness of sums. So that's it. Now let's apply this in a still more particular case. Again, the formula with two sums here. Let's apply it to the case when all of the objects xi and yj are just copies of the same object let's say, the final object of the category C. So the direct sum of capital I copies of the final object is called I lower C. It's the constant object in C with value this set I. Sometimes it's also called I times E, where E is the final object of C. Or if you have any object in a category, you can look at say X, then the direct sum of capital I copies of X is sometimes written as I times X. Alright? So, and here you will have in the same way the constant object with value J of the category, JC. And what our formula says is that the product of these two is equal to I times J lower C. That means, in other words, that the functor which associates to every, in this case, finite set I, the corresponding constant object of the category C, commutes with products. Commutes with finite products. Of course, it transforms the final object, namely the one-point set, into the final object of IC. And in fact, the same argument essentially, you will see that it commutes with also with fiber product, which is a little stronger, which means just that this is the left exact functor. Fiber products and it transforms the final object into the final object. That means that it's left exact. So this is a consequence of the universality of sums, but it's weaker than the universality of sums. Of course, I mean, it's the universality of sums in a very peculiar situation. So here, when we are working with the category C of affine algebraic spaces over K, then for every finite set I, we have defined the constant algebraic space over K of this value I. So IK is the same as IC. And we say that the functor, we see therefore that the functor I goes to IK is left exact. And therefore, whenever I is endowed with a structure, algebraic structure of the composition laws type or so, let's say for instance a monoid structure, then the corresponding object in the category of algebraic spaces has the same monoid structure or group structure, whatever it is. So we get in this way a means for constructing, on the one hand, affine algebraic spaces of a very trivial kind, but also affine algebraic spaces with certain types of structures on them, for instance. This is another example of constructing affine algebraic groups, which I didn't give last time as an example. If I is any finite group, in the usual sense, then I lower k is an affine algebraic group. Okay.
Excuse me. I didn't understand what's the relation between left exact and commuting fiber products.
A functor is left exact from a category into another, assuming that in both categories, or in the first one, in fact, left that finite inverse limits exist, so to say, if and only if the functor commutes with fiber products and transforms the final object into a final object. Because then, as usual products are particular cases of fiber products, namely fiber products over the final object, it will commute with products, and then all we have to show is that it commutes also to kernels. But kernels can be interpreted as being fiber products over a diagonal. Remember. Let's see from the point of view of the affine algebras involved what this construction is. So associating to every finite set I, the affine algebraic space corresponding to it, which is just the sum of capital I copies of the final algebraic space over K, E lower K. Now, the K algebra representing E lower K, that's just K itself. And taking sums of affine algebraic spaces corresponds to taking products of algebras. Therefore, I lower K can be viewed as being V of the product algebra K to the I. But now K to the I is viewed as an algebra. So K to the I is, let's say, the K algebra of all K-valued functions on I, of all maps from I to K. And of course, K to the I, once again, is a contrarian functor with respect to I. And therefore, if she takes the affine algebraic space associated to its covariant functor with respect to I, as it should. What about composition laws in I? If you have a composition law in I, namely a map from I times I into I, you see? So this should define, we said, a composition law on the corresponding constant algebraic space. It would be a morphism like this. And this should correspond to a morphism in the opposite direction on the affine rings, which would be a homomorphism from K to the I going to K to the I tensor with K to the I. And what is this homomorphism? Well, K to the I tensor K to the I can be identified with K to the I times I. And as I have a map from I times I into I just take the transposed map from Ki to K to the I times I. So assuming, for instance, that the composition law here is a group law, so we get an affine algebraic group over K, or monoid law if you want. And the diagonal map defined in the affine algebra is just the map we described here. So that's an example of determination of diagonal map on a group algebra, on the affine algebra of the affine algebraic group. Particular to the case.
Does that have a name?
Yeah?
The groups constructed from finite groups I in that fashion have a name?
Constant groups.
Constant groups.
Yes. Those are the most trivial algebraic groups one can construct. They would make a sense in any category. Whatever comes from the category of sets, you see, is the thing that can be universally constructed anywhere. So this was one compliment I had to say about previous things. I want to add some other comments, coming a little closer to this question of spectra now. We said that if we have affine algebraic spaces x, y, and S may be, for instance, the final object of the given affine algebraic spaces, or with E also. And if we look at the finite product, so here now I take Grothendieck x's, y's, s's. And if you look at the spectra for this Grothendieck z, and if you look at the diagram defines by going over to the spectra, get this diagram. Will rarely be Cartesian in the category of sets, and this will not be true either. That's the topology of Z is induced by the topology x times y. So we have dwelt on this at some length. But I will give, however, one case which is important in practice where things on the contrary, it worked nicely, where Z is the final product of x and y over S, and where the topology of Z is induced by project x and y of x times y. And for this, I will rather not assume that S here is the final object of an algebraic space. Anything. So this corresponds to a diagram of algebras A, B, C, and B tensor over AC. And this here is just the diagram for the spectra of these rings. Alright, assume that y is equal to n, that I'm sorry, I should look at as others on the upper algebraic space on the functors. Assume that Grothendieck y goes to Grothendieck S is a monomorphism. Then of course, by pullback, Grothendieck Z goes to Grothendieck X is also a monomorphism. And then it will show us, it will follow, as we said, that y goes to S is injective, because if you have a monomorphism here, that means something which defines injective maps for points of y with values in k prime to points of S with values in k prime, and then this will imply that the corresponding map or classes of points up to the equivalency introduced in order to define the spectrum will be also injective. So y is contained in S, and the spectrum y is contained in spectrum S, and the spectrum Z is contained in the spectrum X. So in fact, we have subsets of S and X respectively. And to say that this diagram is Cartesian just means that would mean that this subset Z is the inverse image of the subset Y of S. Or give names to our morphisms. Here we have F and G. Here, let's say F and I. G and J, let's say. I being parallel to J. And let's denote by the same letters the maps on the spectra. They go in the same direction. Alright, so what we want to show is that in this case Z is equal to the inverse image by J of Y. That's true. Well, that's pretty tautological in a way.
F inverse. F inverse.
Oh, I'm sorry, yes. F minus 1 of y. It's inverse image by F of y. So we have to prove that any element of X which is mapped into Y by F belongs to Z. Alright. But this element of X comes from a point with values in some algebra K, in some field K prime lying over K. Alright. And so, what we assume is that when we look at the corresponding point of S with values in K prime, then the compositum of this arrow, this comes from a point of Y with value in K prime. So this arrow can be factored through an arrow from psi. The algebraic space defined by K prime into Y. But because this is a monomorphism, it can be factored in a unique way. Alright? Now, well, in fact, I don't even have to repeat the argument because, no, we know already that the net which goes from the finite product of X and Y over S to Z is surjective. So Z prime is the actual finite product which is also contained in X. So we have an inclusion here which is surjective, therefore Z prime is equal to Z. That would be. I was just in the process of reproving the surjectivity, but we don't have to prove it again, we stated it. So by the mere fact that the arrows which we have here of either Z or of X times S, Y, Z into X, that these arrows are inclusions, and that we know that this arrow is surjective. Moreover, follow that it's an isomorphism. So this much about the set-theoretic aspect. Now, what about the topologies? Here, I don't think that in the generality I stated here, that the topology of C will be the topology of the topological fiber product. That the topology of C will be induced by x times y. I don't think it's true. It wouldn't be hard to make counterexamples. But I will give some cases where it is true. Assume, for instance, that Grothendieck y goes to Grothendieck S is a closed immersion. Now, this means that A goes to C is a surjective homomorphism of rings. And therefore, B goes to B tensor AC is also a surjective homomorphism of rings. This means that C goes to X is also a closed immersion. That means the topology of C is induced by the topology of X. And therefore, Z is the... In fact, to say that the topology of Z is induced by the one of X, yeah, I know that the topology of Y is induced by the one of S already. That comes from the assumption that we have a closed immersion. And then the topology of the fiber product would be the topology induced by X. And so we have to prove that that's the actual topology of the spectrum of C. And that comes from the thing I just said.
Is the same true for open immersions?
And the same is true for open immersions, and therefore for immersions shortly, but we haven't defined them yet. But once we have proved it for closed and open immersions, it will be evident by transitivity. So let's take open immersions of the special type. A goes to A lower F. Assume that Y is of the type now S lower F. So we have now a particular type of open immersions. I have not defined open immersions in general either. But we know in this case, if Y is S lower F, and the ring homomorphism means A goes to AF, I know that SF is the open subset. The topology induced by S, well, I write it down here. YF is what should I say? Y is an open subset of S, and the topology of Y, which is a spectral topology, is induced by S. You have seen this. So what we have to show now is that C, which will of course be open because it's the inverse image of this open set in X, that the topology of C is induced by the topology of X. But if you make the tensor product of B and AF over A, of course in this case we will get B lower F. That's predicted here in terms of the, for instance, of the universal property of the rings of the algebras AF and BF. Alright, and therefore we do know that the topology of C is induced by the topology of X, because this map on the spectra corresponds to the map from B into BF. More generally, you see, let's give a common statement for the two which are being closed immersion and this particular type of open immersion. Let's assume that the homomorphism which we have here, which goes from A to C, is of the following particular type. It's obtained by passing first to a quotient A divided by some ideal J, let's say, and then localizing with respect to a subset of A over J, localized not only with respect to one element, but to an arbitrary set of elements in here. So that T be the set of elements. I have not described yet this operation. We will have to describe it a little later, just to make it as an indication. So that this be C. So we have a transitivity A is mapped to the quotient A over J, which is mapped itself into this localized ring. In this case, it will be true that the topology of Z here is induced. First of all, the topology of Y is induced by the topology of S, and therefore the topology of the fiber product will be the one induced by X, and this is indeed the spectral topology. That means in these cases, taking fiber products of algebraic spaces commutes with the functor of considering the associated spectrum as being the spectrum being viewed as being a functor going from algebraic spaces. the topological spaces, not speaking as yet about the ring structures on it. Now, as a particular case of this, let's give the case of intersections of subobjects. If we have an affine algebraic space, call it again S, why not? And if we have two subobjects x1 and x2 of S, we can take the intersection of the two, which is just a fiber product over S. Taking intersection is just taking intersection of functors. Now if I take the spectra of these things, so I have S, X contained in S and Y contained in S, then the spectrum of this intersection is just X intersects Y. Because the fiber product here of sets X and Y over S is just intersection. And in fact the same would be true for intersection of an arbitrary family of affine algebraic subspaces of S. I don't say anything here about the topology, just it's a set static situation. An important particular case, by the way, is the following. We have, of the space change business, we have X over S here, and we look at the base change. Y, if you wonder what Y is very small, Y is just has a spectrum reduced to a point. So we take Y to the spectrum of a field that we call K prime now, because it's a field we don't call C anymore. All right, so here in this case Y, the spectrum is reduced to just one point. And we see that capital Z will just be the inverse image of this point. It will be the fiber of the map X goes to S at this particular point, Y. Now what about here the fiber product of affine algebraic spaces? X times S, Y. This will be called the fiber of the relative affine algebraic space X over S at the geometric point that we are given, psi, let's say. It can be viewed as being an affine algebraic space now over K prime. For every K prime valid point of S, K prime being any ring, but here we are restricting fields, we get by inverse image, we get an affine algebraic space over K prime, which is called the fiber of this here over K prime. So K prime being a field here, it's an affine algebraic space over a field. And the spectrum of this is just obtained by taking the fiber of the map X goes to S at this particular point. So taking fibers, you see, in the sense of affine algebraic spaces, or the sense of what amounts to say in the sense of tensor product of algebras, just when we pass over to the spectra, commutes with the operation of taking fibers of maps. And it turns out, essentially from what I have said here, except that we have still to make a field extension. But I'm sorry, I assume also that this is a monomorphism. Otherwise it wouldn't work. Therefore, yes, I'm sorry. Therefore we must assume that this field K prime is in fact equal to a residue field of A, a certain prime P. That's it. It turns out, in fact, that the topology of C is induced also by the topology of X. This comes essentially from the particular, because this case here, when we pass from A to a field of fractions of A over P, P being a prime ideal, you see, this is a particular case of what I said, dividing by an ideal and then localizing with respect to a set of elements, namely the non-zero elements of this integrated domain. So I didn't check that things behave well for the topology in this general case. I'll leave it as an exercise. But this implies that the spectrum of a fiber here is just as a topological space, the fiber of the net on the spectra at the particular point here. This here would cover, K prime would be kappa y in fact, where y is this point of the spectrum. So, are these statements kind of clear? So all these are cases where the tensor product of fields that describe the relations between the setsodic tensor product and the setsodic fiber product and the fiber product in the sense of algebraic spaces where these tensor product of fields are trivial. One of the factors is just those with you downstairs. Now there's the last compliment I want to give to it has been said before concerning the map on spectra defined by the homomorphism of rings. There's a formula which will express for a closed subset z of x, which will express phi of z, or rather the closure of phi of z. It's a useful formula in terms of ideal theory. So if you have a closed subset of z of x, this will be the closed subset defined by an ideal j in B. And we would like to define the closed subset phi z bar as being defined by a certain ideal in A, and what ideal can be defined in A in terms of an ideal j in B? Well, we have the inverse image. And the formula which one might guess is true indeed. Namely, phi of z bar, namely phi, if you want, of Vj bar is equal to V of phi minus 1j. Of course, if j is a radical ideal, then the inverse image is a radical ideal also. If you want to respect radical ideals throughout, take the limit. I'm sorry? V of, oh yes, of u minus 1j, yeah. I have different letters for the big things. And alright, so how are we going to prove this? Alright, let's describe the image phi of z bar, the closure of this image, as being the largest, no, the smallest closed subset of Y, which contains phi of z. Smallest closed T contained in Y, such that T contains phi of z, id est, such that z is contained in the inverse image of this closed set T. Now, closed subsets of Y correspond to ideals K in V. Let's say radical ideals, let's say. And the larger the ideal, the smaller the closed set. So taking the smallest closed set here is taking the largest ideal K, such that, now we have to express the property here in terms of ideal theory. Now phi minus t, phi minus 1 of t, when t is a closed subset here, is a closed subset of x. And we have seen that this is equal to V of the ideal K B generated in B by K. So we have to express now that V of j is contained in V of kb, and we have to say that we take the largest ideal k such that V of j is contained in V of kb. What does this mean? This means that j contains, or rather j tilde contains kb. Or that means also that k is contained in phi minus 1 of j tilde. That means that the set we are looking for can be described as being the set associated to phi minus 1, to the ideal phi minus 1 of j tilde. So if the ideal j is a radical ideal, so j equals j tilde, we are done. But the formula is true, I guess, in the general case. So all we have to show is that phi minus 1 of j, which is smaller than phi minus 1 of j tilde, however, defines the same closed set. So I have only to prove that every element in phi minus 1 of j tilde has a power lying in phi minus 1 of j, which is clear. If we have an element in here, that means that we have an element x in A, such that, but I'm always writing these damn phi's instead of u's. I'm sorry. Alright, so take an element in here, that's an element x, such that u of x is an element in j tilde. That means that some power of it is in j, which means that u of xn is in j. That means that x to the n is in phi minus 1j. Alright. So that's a handy formula. It's proved now. I will give it an essentially equivalent formulation in terms of a criterion for phi to be dominating. Phi is dominating, by which we mean, it's a pure topological notion, that phi of x is dense in y, phi of x bar is equal to y, if and only if the kernel of phi is contained in the nil ideal and the nil radical of A. Because phi of x bar is defined by this formula as the closed set associated to the kernel of U. And here again it's not phi but kernel of U. And to say that the closed set associated to such an ideal, to an ideal in A is the rule of y means that this ideal is contained in the nil radical. So if we assume A reduced, that is, the nil radical is reduced to 0, then this means that phi is dominating if and only if U is injective. So, except for the nilpotent elements, remember that dominating morphisms, dominating maps on the spectra are interpreted in terms of injective maps for the rings. I mean, everything being ruled as something, it's kind of the natural way of expressing things. That's the first statement that comes to mind. In fact, you see, in this formalism, and what I'm going to explain with these formulas of sheaves associated to modules, I mean, in every situation, there is just one natural statement that comes to mind for interpreting geometric things in terms of, let's say, quantitative algebra. And this is always true. So that's really very, very pleasant, you see. It's a situation where really you can't have any bad, provided the statements make really sense, you see. They are true. And I think we should stop. Yeah, what about, so finally I didn't even start with the subject I wanted to go on with the sheaves. So what should we do afterwards? Groups or? Sheaves. Is there any objection to going on with sheaves and not and not doing groups as yet today. It won't be much groups anyhow. Alright, so let's so make a break for 10 minutes. And then we start continuous sheaves.
Next way, we should do one for the exercise.
So let's come back now to these sheaves. So for the time being, I fix the ring A. You may view this being algebra K, although the algebra structure will not take really any significant role. And I look at the spectrum X of A. The topological space, as we have seen. There's a basis of open sets which are the XFs. F element of A. We have seen how the inclusion relations between the XFs, or the fact that an XF is covered by others XFIs, can be interpreted in terms of multiple algebra. So just forgetting about topological spaces, or pretending to forget, because the way to understand what one is doing is, of course, looking at topological spaces. And we interpreted sheaves on X in terms of functors with respect to the XFs, that is essentially with respect to the Fs, that constraint functors that have certain properties of exactness. And we have seen that if N is any A module, and if you look at the assignment which to every F in the spectrum associates the localized module MF, was M tilde of F, you get in fact a sheaf on X, which is a sheaf of A modules. Well, it's a little better than this, because if you do this for M equals A, you get that A tilde, which is a sheaf of A modules, is in fact a sheaf of A algebras. It's a sheaf of A algebras, or therefore a sheaf of rings, if you want, endowed with a homomorphism of A into the ring of sections of A tilde, but A tilde, the sections of A tilde over X, that's just A lower 1, that is just isomorphic to A, so this here is an isomorphism. The homomorphism that comes from the algebra structure. Alright. And in fact, coming back now to the MFs, these are in fact algebras over, so A tilde is just, let's say, call it corresponds to the pre-sheaf F goes to AF, which turns out to be a sheaf. And the MFs are modules of the AFs in a functorial way parallel MF. Therefore, this is a sheaf not only of A modules, it's a sheaf of A tilde modules. Alright. So, is the situation clear? Now, this sheaf of ring A tilde is very generally denoted by O lower X. It's the sheaf, so to say, of rings associated to the spectrum X. Of course, we don't know it when we know only the topological space X. It comes from the ring A in terms of which we have constructed the spectrum. And it's called the structure sheaf. Structure sheaf of X, that is a structure sheaf on the spectrum. And henceforth, we will consider the spectrum as being a ring space, a space endowed with a sheaf of rings, which is just this rings. And I promise that in terms of this ring structure, we can reconstruct the ring A. And in fact, we have just seen that A can be recovered as being the ring of sections of the structure sheaf over X. So to the ring we associate a ring space, the spectrum, and it turns out that we recover the ring from the ring space. So we have here now, we expect to have the beginning of a perfect dictionary between rings on the one hand, or let's say algebras over a given ring K, let's say, with a ring Z if you want. Any ring is Z algebra. Alright, so a dictionary between the rings, let's say, and topological spaces, certain topological spaces endowed with a sheet of rings. You have to see which we obtain in this way up to isomorphism ring spaces. And we will carry this dictionary along for a little while, including, for instance, what happens if you have morphisms between rings, if you have ring homomorphisms, what it does when the corresponding ring spaces. But maybe before varying the spectrum, before varying the ring, and see what happens to the spectrum as a ring space, let's perhaps say a little more about modules over the spectrum, sheaves of modules over the spectrum. We have therefore seen that we have a functor m goes to n tilde going from the category of modules over the ring A to the category of modules over the sheaf of rings OX. That means sheaf of modules over the sheaf of rings OX. And we will have to get a few properties of this functor, to list a few properties. Let's see. Well, this functor is additive, and in fact better than this, it's even exact, it's stronger than the additive. Additive just means that it commutes with finite products, or what amounts to the same, commutes with finite sums, being functor from an category into another, so it's in fact an exact functor. Yes? It commutes with tensor products, and let's say also that it commutes with direct limits. So I guess that means that it's a joint of something, but never mind, let's not dwell on this. With arbitrary direct limits. It commutes with tensor products. What else important can be said about this functor? Commutes with form in certain cases. Form m tilde is the sheaf form underlined m tilde n tilde. If m is of finite presentation, I guess. If m is of finite presentation, that's an essential restriction. We call that for a Newtonian ring A module of finite presentation if and only if it is of finite type, if it has a finite number of generators. So these are the main properties of these m tildes when the spectrum remains fixed. We have better things also. It's exact. And now what about the faithfulness properties? It's fully faithful. That means that the category of modules over A can be viewed as being a full subcategory of the category of modules over OX. So we have a perfect dictionary. Operations which we make on modules over A can be viewed as any kind of things we do with modules over A can be viewed as being particular cases of things which we can do with sheaves of modules over X. We have, of course, if you want to be perfectly happy, we have to say which are the modules over X which are isomorphic to modules of the type M tilde, namely what is the essential image of this functor. And these modules are the so-called quasi-coherent modules, which I will say perhaps a little later, a word about how they can be characterized. So for the time being, let's prove these statements here. And that is a probably that tells a story about what happened, what of these M tildes when the spectrum is fixed, when something is fixed. So recall that the sections of M tilde over XF is MF, the localizer of M with respect to F, and we know that M goes to MF is an exact functor. So in fact, this we have noticed an hour or so ago. Therefore, not only the functor M goes to M tilde is exact with values in the category of sheaves, it's even exact with values in the category of pre-sheaves on the basis of open sets we have considered. So that's much stronger than this here. So that's the exactness here. What about commutation with limits? Well, it's the same story. This functor M goes to MF as a base change functor, and therefore it commutes with filtering Dieck limits. And this means that the functor M goes to M tilde commutes with Dieck limits even if it's viewed as being a functor with values in pre-sheaves on this basis of open sets, which is a lot stronger than to say that it's so this values in the category of sheaves. So that's about filtering Dieck limits. And on the other hand, as the categories which we have here are additive finite Dieck limits, result from filtering Dieck limits and, let's say, sums, finite sums. Yes.
How do you define the sections
Of whom?
on the sheet of modules?
Of M tilde? Or an arbitrary open set?
Yes.
Well, I mean, if you have a sheaf M tilde, that's just a contrarian functor going from open subset of X to, in this case, to a Abelian group, something like this. And so it associates to an open set, U, let's say, M tilde U, which is an abelian group. And the elements of this abelian group are called sections of the sheaf over the open set. Is this the question? Was this
Sorry, I was thinking about the sheaf in the Lorentz sense. Sheaves defined by Lorentz.
By what? By Lorentz?
Yeah.
Yes, I mean these are the sheaves of Lorentz in a way. And I mean there's particular kind of pre-sheaves, you see. There are contrarian functors from open sets into sets which have certain exactness properties, and the element of the set associated to an open set is called a section of the sheaf over this open set. So this here gamma xf M tilde is a synonym for M tilde of xf. And by definition, this was also, by the construction of M tilde, this was M lower f. So exactness is proved. Commutation with arbitrary Dieck limits is proved true. So let's not speak about the adjunction formula. What about commutation with tensor products? Here again, it's in fact commutation with tensor product as a functor going from module to pre-sheaves over the spaces, because M goes to MF is a functor, or base change functor from A to AF, and this commutes with tensor products. So what we get, let's make things explicit on this case, is that M tensor, if you look at M tilde tensor M tilde, if you look at this tensor product, not in scale of sheaves but of pre-sheaves, so let's call it lower P in here, over of course always A tilde, over the structure sheaf. You see? Then we have seen that this is just M tensor M tilde. That's an isomorphism. But by construction of tensor product of sheaves, this here, this tensor product of sheaves is a sheaf associated to the sphere sheaf. Now this sphere sheaf turns out to be already a sheaf. You see. So it's, in a way, it's stronger to say that we have compatibility with tensor products when we do SM tilde as being pre-sheaves on the category of special open sets XF. Alright, so this is trivial, commutation with tensor products. What about the relation with the Holmes? If M is a free module, M is A to the N of finite type. Of course, then M is also supposed to be a finite permutation, so it should be A to the N with a finite N here. Then taking the home of AN with values in N is just this module here is capital N to the N. And when I take the tilde, because tilde is an additive functor, we get here N tilde to the N. And what do I get here? M tilde, you see, is that's AN tilde, and because tilde is additive, that's A tilde to the N. So that's just the free module of rank N over A tilde. And then so the sheaf homomorphism of this into N tilde is just N tilde to the N. So I get twice the same thing. So in the case of a free module of finite type, this is clear. And from this we get the general case by just writing M as being a cocanol of homomorphism of free modules of finite type and making a little diagram chasing. Writing this sum of. In fact, this property is true whenever we have a homomorphism of ringed spaces, you see. We can say that we have a homomorphism of X and out with the sheaf of rings OX into the space reduced to one point and out with the ring A. And let's say it this way, yes, perhaps that's another formula. And that if you have a module M over A, that's just a sheaf of modules over this ringed space reduced to a point, that's just taking M tilde is just taking the inverse image in the sense of sheaves of modules of this M by this morphism of ringed spaces. What does this mean? This just means, in fact, that here again it's a formula that is true in the sense of pre-sheaves. Because in the sense of pre-sheaves, this means that MF is just a tensor product of M over A with AF by VF. It's even a stronger result. So, passing from M to M tilde can be looked as being a particular case of making a base change in modules for a morphism of ringed spaces, and then it's known that such a base change commutes with tensor products and commutes with home sheaves. Home sheaves, of course, here are just home modules, provided the first sheaf is a finite presentation. Can be written at least locally as a program like this. So I mean, this commutation with tensor products and the commutation with homes is just a general story about morphisms of ringed spaces. So I think we have proved everything and a little more, because we proved also this formula here, which we can also write as M tilde, let's recall it, is just a tensor product of M over A with OX. So we can look at the constant sheaf of rings A on X and the constant sheaf of modulus M over it, and we extend the basis from A from the constant sheaf of rings A to OX, because OX is a sheaf of A modulus. Alright, and so all we have got to prove still is that the functor which we have M goes to M tilde is fully faithful. In other words, if M and N are two A modules, if I look at the set of homomorphisms of A homomorphisms from M into N, this is mapped to the set of OX homomorphisms of M tilde into N tilde, I want to prove that this is bijective. This will, and this again is kind of trivial. I will define the map in the opposite direction here. If I have a homomorphism from M tilde into N tilde, So this map here, let's call this alpha, that's because tilde is a functor. And let's define that in the opposite direction, beta. All right, if you have a homomorphism from m tilde to n tilde, let's say u, we will define beta u with the corresponding homomorphism for the sections over x. Now this here is just m, and this here is just n. So we get a homomorphism from m into n. Now, all we have to say is that the compositor here, the two ways are the identity. But if we start with the homomorphism of m into n, because call it v if you want, we consider the corresponding homomorphism for the sheaves. If we look at what it does on the sections, of course, it is just the d we started with. And if we go the other way around, hey, now maybe we have to be a little careful. No, not even. If you have a homomorphism from m tilde to n tilde, so call it u, defines the homomorphism from m into n, call it v, what is deduced from u by passing over two sections. And now let's look now at v tilde, which goes from m tilde to m tilde, and let's show that v tilde is equal to u. Now is this evident or isn't it? I think it should be. So we have to prove that u equals gamma u, v is equal to, which is deduced from u by passing over two sections, gamma u tilde. All right. In other words, we have to show that u is known when we know its effect on global sections. Yes, because u for every f, u lower f is a homomorphism from mf into nf. And because u is a homomorphism of sheaves and therefore of p-sheaves, this homomorphism makes this diagram commutative. Where here we have canonical morphisms, which are just restriction homomorphisms for sections over x to sections over xf. And here we have the homomorphism on global sections. But on the other hand, we know that there is a unique map from mf into nf, which makes such a diagram commutative. It's deduced from this thing which we have here v by localizing an f. Alright, so I think that does it. So it looks like magic, but everything comes out trivially. The only thing you see, which wasn't trivial, was this business about these NFs really forming a sheaf. And all the rest, I mean, is sheer triviality. Now, I promised that I would say a word about which are the sheaves of modules on the spectrum which come from modules over A, which are isomorphic to sheaves of the type M tilde. Now here the answer again is nice because it's a purely local property on a sheaf, and these are so-called quasi-coherent sheaves. So let's give the definition if X is any ringed space with structure sheaf with sheaf of rings OX, and let Grothendieck M be a module over OX, then we say that M is quasi-coherent if and only if, that's the definition, for every point X in capital X, or well, let's be more fancy and say that there exists a covering of X such that there exists a covering of X by open subsets Xi such that the restriction of M to each of the Xi's, which is now a sheaf of modules over OXI, can be written as a co-kernel of a homomorphism of three sheaves of OXI modules. Where this here L0 F3, but not necessarily of finite type. it's OXI at a certain power, let's say j, where j is a set of indices, which might be infinite, and L1, or J0 if you want a set of indices, and L1 is OXI to the symbolic power J1, where J1 is another set. Symbolic power means direct sum of copies, not products. So that means that M is a quotient of a free sheaf, so that M is generated by its sections. It's a quotient of free sheaf, just means that M is generated by its sections over Xi here. It's a subsheaf generated by its sections over Xi. And that the relations between these sections form again a sheaf which can be globally generated by sections over Xi. Just the definition of quasi-coherent sheaves, which makes sense on any ringed space. And the theorem is now with X in the spectrum, if X endowed with over X in the spectrum of a ring A, then a sheaf of modules M is quasi-coherent if and only if M is isomorphic to some M tilde. So let's prove it in one direction and let's drop the question on the other. It's not very hard. So show that if M is isomorphic to M tilde, then M is quasi-coherent. In fact, it's not only quasi-coherent in the local sense, it satisfies a condition globally. Because M itself can be viewed as being a co-kernel of a homomorphism of three modules. Because, well, I mean, that's true for any module. M is a quotient of a free module. That just means that M has a set of generators. Can take a set of generators to M itself. And the kernel of that L1 goes to M is again the image of another homomorphism of three module to it. Alright? Now this exact sequence, by passing over to the tildes, gives us an exact sequence like this. And it's clear because the functor tilde communes with forming of sums that transforms three modules into three sheaves of modules. Therefore, M tilde certainly is going to be here. So all that is to be proved now is the following. Of course, conversely, if we know that globally a sheaf F, a sheaf of modules M, admits such a presentation as a co-kernel of three modules with Grothendieck Ls, let's say, then it will follow that M comes from an M, that M is isomorphic to M tilde. Why is this? Because by definition, more or less, a free module L1 comes, sheaf of modules comes from a free module. That's clear, isn't it? And the homomorphism from L0 into L1 comes from a homomorphism of modules from L0 into L1 because the functor tilde is clearly faithful. Now let's look at the co-kernel of this homomorphism. M. Now the tilde of M is isomorphic to the co-kernel because the functor tilde is exact of the homomorphism, that is to this here. Therefore, all we have got to do now is to see the following. Let M be a quasi-coherent sheaf on X. This means that if we cover X by a sufficiently small open subset XFI, the restriction of M to each of the XFIs has a global presentation as we just saw, and therefore M restricted to each of the XFIs can be written as Mi tilde, where Mi is a module over the localized ring AFI. And now what we have to prove is, well, I think, yes, that with this assumption that M itself is isomorphic to module M tilde. That means if we have these such modules, now what does it mean that these modules Mi come from a global sheaf on X? That means that if you look, so that kind of touching data, you see that if we look at Mi, the base change by AFI mapped into AFIJ, and so MI gives now a module MIJ by base change, and if we do the same thing permuting the J and I, and if you look at the same thing here, MJI, then we get an isomorphism between the two things here. That means that we have, I'm just expressing that to give a sheaf on a space which is a union of open subsets, XFI, it's the same, it gives us sheaves on the XFIs and matching data in the intersection, of course with a possible relation. And what we have to prove is that if you have such data, now everything is expressed in terms of commutative algebra. You can forget about the spaces. But then there exists a module M over A giving rise to the MIs by a base change from A to AI. So that's an exercise in commutative algebra, which in fact here can be proved using the same trick you see of descent, because the same of faithfully flat descent. It essentially means the following. Let's write it down in terms of descent. It's kind of true. So we have this thing A and you have A prime, which in our particular case would be the product of the AFIs. You can assume that the number of FIs is finite. And now the product of the AFI FJs, you see, can be viewed as being just the tensor product of A prime by itself. Now, the data, namely the set of the MIs and the matching data satisfying a certain co-sector relation, can be viewed as being a module M prime over A prime, together with an isomorphism between the two inverse images of M prime by these two base changes. So as we have an isomorphism between them, just call these two inverse images by the same letter M second, let's say, in such a way that a certain relation holds when we look at what happens over A third. It just means in fact that we have a simplicial module, with a simplicial ring. So that there is an M third here in such a way that we have in such a diagram, let's say. Alright, and the question which arose here in terms of geometric terms, you see, when we write it in terms of homological nonsense, means that there exists an M over A, which will have to be the kernel of this pair of morphisms here, in such a way that this situation comes from base change by this, of this model M over A. So what we do is the following. We define M to be the kernel of this set of morphisms, called as M naught. That means that we define M to be the set of elements in the MIs, you see, which match in the intersections. That's what it would mean. But forget about the MI, now look at this one-to-one situation. And now, because of the way in which it was defined, when we make the base change in all these here to get modules of A prime and A second and A third, you see, they have morphisms like this. And what we want to prove is that these are isomorphisms. In fact, that this is an isomorphism, the others then will follow. Now this is a purely linear question, and therefore, again, if we know that this will be true after we make a faithfully flat base change, it will be true before. And now A prime I over A is already faithfully flat in our case here. And therefore, we make the base change by A prime itself, B equals A prime. But then we are reduced to the case when moreover there's a section. But in this case, I mean the same general nonsense which I said will ensure that every descent data on an object M prime over A prime is effective, that it comes from an M over A. So again, the existence of this
Could you repeat that last part?
Yes. So the statement is the following: if you have, let's be real systematic in our statement so that you don't feel lost. We have in algebra A over A prime. In fact, we could do things in arbitrary category after all. Why don't we do this? So which correspond to an object X prime over an object X in some category, the category of an algebraic space over some K, let's say. All right, and then we construct here the fiber product of x prime over itself, x second, and the threefold product. In fact, we have, as we saw, a simplicial object in the category C over x, which corresponds in sense on this direction here to taking tensor products of algebras. But we can go out as long as we want. Now assume moreover that we have what is called the fibered category over C over x, namely that for every object, let's say z lying over x, we associate to this a category fc which depends complementary on z with transitivity. For instance, for every algebra b over a, let's say, we associate the category of b modules. And we have base change between these categories. So this category depends covariantly on the ring, but consequently it's of an algebraic space. All right. So in particular, I have the category fx, the category fx prime, the category fx second, the category fx third, etc. And base change functors which go in the opposite direction, like this. Whenever I have an object over x, it defines an object over x prime, and I have an object over x prime, it defines two objects over x second, by these two arrows, etc. Perhaps I should put in the arrows, you see, but when we go over to the rings, they are reversed. Alright? Now, if I have an object on x, it defines as an object over x prime, but the two inverse images of this on x second are isomorphic because they are just the diagonal inverse image of x second goes to x. So this object on x prime has an extra structure, which is called a gluing structure, namely an inverse image, namely an isomorphism between the two inverse images. And this extra structure satisfies a certain transitivity relation on x third, which I could write down. I mean, it's the one nature relation one might write down in x third, which is also a relation one writes down if one wants to express a fiber bundle or a sheaf on a space which is covered by xi's in terms of sheaf on the xi's, matching data in the intersection, and then a cocycle relation, the threefold intersection. So this stands for the threefold intersection, if you want. All right. So we get a functor from fx to the category of objects of fx prime together with descent data relative to x prime over x. So it's written like this. dx prime over x on fx prime, these are the category of objects on fx prime, and that is an extra structure in descent data. And the question is this an equivalence of categories? First of all, is this functor faithful, fully faithful, or an equivalence of categories? I mean, going by increasing stringency. If this is faithful, we say that this morphism is a morphism of zero descent for f. If it's fully faithful, it's a morphism of one descent for f, and it's an equivalence of categories, it's a morphism of two descent, I think, for f. So the strongest thing is that we have here an equivalence. Then we say that x prime goes to x is a morphism of effective descent for f. In the case here, when we have the category here of affine algebraic spaces, namely here over k, namely here the category of algebras over k. With this diagram, taking for fb for every module b over a, for every algebra b over a is the category of b modules, let's say. The question would be the following. We have a functor going from the category of a modules to the category of a prime modules together with the descent data on this I prime module, namely an isomorphism between the two inverse images, satisfying the transitivity condition there. And the question is this functor in equivalence of categories? All right, now let's come to the general situation in any category. The problem is that whenever x prime over x has a section, it's a morphism of effective descent for any fibered category, whatever. We don't have to be careful about what f is, modules or algebras or relative spaces over x or whatever, sheaves, species, anything. All right. That means here that if the algebra a prime over a has a homomorphism of a prime into a, then certainly to give a ring, to give a module over a is the same thing as to give a module a prime over a prime together with descent data. Now, next step is to say the following. If a prime over a is faithfully flat, then it's a morphism, then you see VA prime lying over VA will be a morphism of effective descent for the finite categories of modules or variable rings. So I say that in this case, to give a module over M, and module M over A is the same thing as to give 1 over A prime together with descent data. Now let's give the proof. I mean, it's the one I indicated. Because in order to prove that this is so, it's enough to prove that it becomes so after a faithfully flat base extension. And that's true whenever we have an algebra. In order for A prime over A to be of effective descent for the kind of all modules, it's sufficient that, that this becomes true after a faithfully flat base extension. Because we have to express some certain linear things. We have to express that if we have descent conditions here on A prime over A prime, and if you look at the kernel M naught of this descent condition, and if you look at the corresponding module with descent data here, and if you look at the map here which we have here, we get an isomorphism. But in order to know that the homomorphism of A module is an isomorphism, it's enough to show that after tensoring it. With D it becomes an isomorphism, D being faithfully flat. So, and when now I take B to be equal to A prime, taking this particular extension, A prime now being assumed to be faithfully flat over A, so that making this particular base extension, it will be a faithfully flat base extension. A modules, which is of much larger scope. It's very important. And it's a statement that you use all the time in algebraic geometry. But I didn't notice. In fact, when we wrote down the proof of this thing on spectra, I think this was before the descent theory was worked out. So I just discovered that it's then it's a particular case of this general descent business. Alright, so we actually gave the proof that M was then tilde induce an equivalence between the category of A modules and the category of quasi-equivalent sheaves on the spectrum. So I think really here we have set the whole story of this formalism, correspondence between modules and sheaves. When we have a ring that is fixed, that means a spectrum that is fixed. Now let's see what happens if we vary the spectrum. Now this is, again, very basic. Situation to investigate, to be very clear about. So, assume we have a homomorphism of rings, A goes to B, and we have seen that this defines a map for the spectra associated to every prime ideal of B, its inverse image in A. And now I want to define a homomorphism sorry, maybe. Yes, I think I'm sorry. I'm not quite through yet with the situation when X is fixed, when A is fixed. Because I should now investigate the stalks of these sheaves and say something about them. It's quite important. So, if we have any sheaf F on topological space X, recall that the stalk of F at a given point X in capital X is defined to be the direct limit of the sections of the sheaf on smaller and smaller open neighborhoods of X. Now, in our case, we will take F to be the sheaf M tilde associated to an A module. let's see, and x will be associated to a prime ideal in A. So m tilde at the point x will also be denoted by m lower p. I mean, it's consistent notation, certainly. And this now is the Dirac limit of the sections of the sheaf on all open subsets containing x, and of course we can take them of the special type x lower f, which form the basis of the topology. And the sections of m tilde over this open set is m lower f. Now, what does it mean that xf contains the point x? This means that f, the contrary would mean that x belongs to the variety defined by a relation of f. This means that f is element of p. And now we have to write that f, the opposite, that f is not element in p. That means that f is an element of the complement of p. So it turns out that these modulus mf, when f runs over the complement of p, they form a filtering family of modules. It's pretty clear in a way, because if f and g are both in the complement of p, p being a prime, this implies that fg also is in the complement of p. And on the other hand, we know that both mf and mg are mapped into mfg. Just expresses that the open set xfg is the intersection of xf and xg. All right, and so these mfs you see, they form a directed system of modules, A modules, and I take the Dirac limits. That will be the storm. And in particular, if I take M to be equal to the ring A itself, you see that the storm of the sheaf of rings, the structure sheaf, at the point X, is just the Dirac limit of the rings AF for F running over the complement of P. Now, what we just use in order to ascertain that we have a directed system of modules, or here a directed system of rings, is that the complement of P was stable under multiplication. And now, if you have any subset, call it T, in a ring A, stable under multiplication, Fg in T implies that Fg is in T. Then, if you look at the system of all MFs, they form a directed set, and we can look at the Dirac limit of these, call this mt minus 1. We call this module the module localized of M with respect to the system T. If by chance T was not yet stable by multiplication, then we would replace it by the subset by the smallest subset of A containing T which is stable by multiplication. For instance, T may be reduced to just one element, for instance, element F. And we may want to localize with respect to this element, and then we just localize with respect to the sequence of Fn's. It's really the same. So in this case, we get M over F. All right. And if you look at the Dirac limit of the A lower F's for F and T, where M is equal to A now, this is called AT minus 1. This now is an A algebra. So it's an operation which can perform both in the sense of algebras or in the sense of modules. Of course, MT minus 1 will be an algebra by AT minus 1. Now, we can describe these new modules that are formed by this passage limit as solutions of universal problems if you want. First, let's look at this problem from the point of view of modules. We have, of course, a canonical homomorphism of M in each of the MFs. For instance, M is just M1. And therefore, into the Dirac limit, all these homomorphisms are compatible with the transition morphisms. And we see, moreover, that in this direct limit here, in mt minus 1, so we have a morphism of m into mt minus 1, and in mt minus 1, moreover, any limit of t induces an homogeneity which is bijective. And now, it's pretty clear to see that this map of M into a module where every element of T becomes bijective homogeneity is universal. In other words, if you have any module N such that Fn an isomorphism for every F in T, then there exists a unique morphism of M into N. I'm sorry, if you have such a morphism from M into N, there exists a unique morphism from mt minus 1 into N that factors it. That's pretty clear, you see, because to say that every F and T becomes invertible means that this morphism can be factored through each of the MFs in just one way, as we know, and therefore it can be factored through the direct limit. So that makes all this tautological. And the analogous problem for this algebra is the following. In this algebra, at minus 1 over A, the elements of T become invertible, and now A mapped into this ring, so that to make the elements of T invertible, that's universal, namely for every ring B, such that, what should I say? For every ring B, let's say, and any homomorphism of A into B, such that the elements of T become invertible in B, there exists a unique map of A minus 1 into B, which factors it. It's the same story, because for every particular F and T, to say that this here maps F into an invertible element means that this map here can be factored through AF. And to say that this is true for every F just means that it can be factored through the direct limit of the AFs. So this is the notion of localization of modules with respect to a system of elements multivariably stable. Now let's interpret it from the point of view of sheaf theory. We can say the following, that if we associate to every F in T the corresponding open subset X, F, and X, then the fact that T is multiplicably stable means that these open sets form a basis of filter. Because if XF and XG are such open subsets, then XFG is also of the same type, and this is just an intersection of the two. And therefore, this direct limit can be interpreted as mt minus 1 as being the direct limit over all these XFs, over all these open sets of MT of this open set. So that's pretty standard construction. In topological space, which we have a base of field of open sets to associate to this, and you see for every sheaf the direct limit of the sections on these open sets. So that's what this really is. And the same if you take the structure sheaf. And the particular case which we started with here, starting with the point, is to take a base of filter, the filter base of neighborhoods of the given point X. So in the case when we have a prime ideal P, and if we take T to be the complement in the ring A of this prime ideal P, then the corresponding localized modules are called MP, and if we look at the localization for the ring A itself, it's AP. So these are things that have been dealt with for a long time without having any topological interpretation for them. But now we interpret these as being just the stalk of M tilde at the point X, and the stalk of OX at the point X, where X and P correspond to each other. All right, so we know how the stalk can be interpreted in terms of two-matrix algebra. They are just the so-called, localized module, but now in the very strict sense, localized at a prime. That's MP is called the localization of M at the prime P, and AP is the localization of the ring at the prime P. NP is an AP module. I could say, of course, also quite generally that MT minus 1 is just reduced from M by making the base change from the ring A to the ring AT minus 1. So in fact, the particular case of localizing in A allows us to localize in any module, which was tensor. Now I have to give an important property of these rings AP equals Stokes of the structure sheaf at X. These are local rings. Each of these rings is a local ring, I say, with residue field kappa X equals the field of fractions of A over P. So maybe I have now to define what a local ring is. Let's see. Let A be a ring. Now I have to give a definition. Maybe we shouldn't call it A because it will be maybe O. O is kind of initial of standard initial of local ring. Let O be a ring. Everything commutative with unit as usual. So O is said to be a local ring. If there exists one and only one maximal ideal in the A. If there exists at least one maximal ideal, just means that the ring is not zero, according by Kohle's theorem. And then we want moreover that there should not exist any more than one maximal ideal. Now let's look a little bit what this means. Here, in terms of the spectrum, if we like to do things symmetrically, maximal ideals correspond to closed points. So it just means that there exists one and only one closed point in the spectrum. Now let M be this unique maximal ideal. Then we find that O star, the group of invertible elements of O, is just O minus M. This comes from the fact that an element of O is of any ring O is invertible if and only if it doesn't belong to any of the maximal ideals. And if there's only one maximal ideal, it just means this here. An element F of any ring O, whether local or not, is invertible if and only if F doesn't belong to any maximal ideal. That's, you know, if it's not too familiar, I can give the proof. I mean, it's pretty trivial. That F is invertible means that the ideal FO is the unit ideal. In other words, that F is an ideal, that F is invertible means that the quotient rings O where FO is a zero ring. But that means that in ORF there doesn't exist any maximal ideal, like Holt's theorem. If it wasn't zero, this quotient ring would have a maximal ideal. But the maximal ideal of this quotient ring just corresponds to maximal ideals of O which contain F. So the maximal ideal of A that contains element F. So that gives the implementation. Therefore, here for local rings, we have this very nice situation of the invertible elements being forming just the complement of one ideal M. Now, if we have a pair of the ring O and the ideal M and O, yeah, O being a ring and M an ideal. What does it mean that O is a local ring having M as its unique maximal ideal? Then O is local with M its unique maximal ideal. Well, this is true if and only if. I guess that's it. Yeah, if and only if. O star is equal to O minus M. I guess that should be true. Let's see. Yeah. So you have seen that this is true. If O is local and M is unique maximal ideal, then O star is equal to O minus M. Let's assume the converse. So that O star is equal to O minus M. This means that in O over M, every element, call this here, what do I know? Call this B if you want, something like, or call this K if you want. Every element which is not zero, namely which comes from an element of O minus M, a passage quotient, is invertible because it's the image of an invertible element of O. That means that K is a field. That means that M is maximal ideal. So already we see that M must be a maximal ideal. Now, if there was another maximal ideal, then M, it wouldn't be contained in M. And then there would be an element which is not in M, which belongs to it. Now, this element would be in O minus M and wouldn't be invertible. All right. Therefore, I mean, the situation of a local ring together with the maximal ideal of it is just a situation of a ring and an ideal for which we have this equality. So that's just another way of describing local rings. Now, this field here, K equals O over M, that's called the residue field of the local ring. And let's see, another way still of stating that F is a local ring is, I leave it as an exercise. O is local if and only if for every element F and O, F or 1 minus F is in O star. So either F is invertible or Y minus F is invertible. Right, so that's the notion of a local ring. I think that's all we have to know about it in general. And now what I claim is that the stalk of the structure sheaf of a spectrum at a point X is a local ring. And in fact, its prime ideal is the ideal generated by P. You see, P is an algebra over A, so by every ideal here we have an ideal generated in it, which we call J is ideal here. We have the ideal JAP. So we can look at the ideal PAP. I claim that that's the maximal ideal. All right. How are we going to prove this? And the residue field AP divided by PAP by its maximum idea is isomorphic, as I have said here, to the field of fractions of A over P. So that's the situation which I want to describe. So how can we do this? Well, let's prove, for instance, under this form, let's prove that AP star is equal to AP minus the ideal PAP. Alright, now, we call that AP star. AP is just the stock of the structure sheaf at the point X. So we have to prove that if you have a germ of a section of the structure sheaf, it's a neighborhood of X. That means a section over some neighborhood of X. Then it is invertible in the neighborhood of X, if and only if it doesn't belong to this idea. Now, use this. Should be trivial. Let's define a homomorphism to start with of this localized ring AP into the field of fractions of A over P. In order to do this, we have to define a homomorphism of A into this field, which transforms the element of the complement of P into invertible elements. Well, I mean, I just take the canonical homomorphism, which factors through A over P, and here it's the passage to the field of fractions. The elements of A minus P are those which are not zero in the open A over P, and these are those which become invertible in the field of fractions. So certainly I have a natural homomorphism of AP into kappa P. And let's see. This is surjective because every element of kappa P can be written down as a quotient of an object element of A over P divided by an element of A over P which is not zero. Now, so it can be written as being F point over G point, where F and G are an A and G is not in P. But if I look now at F over G, this can be viewed as being an element of A localized in P, because G is not in P. And the image of this element is in kappa P is the element we started with. Alright, so that's the surjective. Gosh, and I guess it will be pretty evident that the kernel of this is just the ideal PAP. Let's check it. Well, I thought I had the fancy way of doing things, but apparently I haven't, so I really first have to check it. So let's look at the kernel of this. I claim that's the ideal PAP. Of course, PAP is contained in the kernel. So let's take the contrast. So let's take an element of A over P, which is F over G, being an element of the complement of P, and assume that its image in here in kappa P is equal to 0. Now this element is F point divided by G point. The F point and G point are the images of F and G in A over P. And to say that this is equal to 0 just means that F point is equal to 0, that means that F is an element of P. Therefore, this here element can be written as being F multiplied by 1 over G. 1 over G is an element of AP, and F is an element in P. So there we have it. All right, we already see that this is maximal ideal in AP, and that the residual field corresponding to this maximal ideal is a field kappa P of fractions of A over P. And now, how will we prove? Well, let's again do it in the Delaire way. Let's take an element in here, assume its image in here is not zero. In other words, that the image doesn't belong to this ideal. Let's show that it's invertible. All right? So we still take the same element, the same way of writing the element of A. F over G, so the image in kappa P is F point over G point. Now we assume that it's not zero. But to say that it's not zero means that F point is different from zero. That means that F
You have shown PAP is maximal ideal, right?
yes.
And AP modulo PAP is a field which is KP, so
No, I want to prove that any element, I want to prove that any element in this ring which doesn't belong to PAP is invertible.
if you look at the fraction, the numerator and the denominator are both outside P.
Yeah, well, that's what I'm going. That's what I'm doing, I think. You see. So to say that if you have an element here, which is not in PAP, I mean, whose image here is not zero. So this is an element F over G such that F point over G point is not zero, namely that F point is different from zero, namely that F is not element of P. Then G over F is another element of A over P because the denominator doesn't belong to P, and it's the inverse of F over G. All right, so I think that does it. So we see that our sheaf of rings on the spectrum has an important extra feature, namely that the stalks of this structure sheaf at any point x is a local ring. Now a topological space endowed with a sheaf of rings whose stalks are local rings is called a locally ringed space. And we will see that the fact that these stalks are local rings brings about number of makes the situation kind of different, you see. In a way, the interest of having passed from the ring A, which was something pretty simple to define, to a topological space with a sheaf of rings, which looks in a way more intricate. Although I claim that one understands better what is happening, one has better insight in the situation by looking at this ringed space, rather than looking at keeping the ring A as it was. This comes precisely from the fact that this has an extra feature, namely that the stalks of the sheaf of rings on the space are local rings. In a way, one has broken up a ring A, which is something pretty global, and you see this continuous collection of local rings, whose residual fields, by the way, are just what we called already the residual fields of the spectrum at various points. And these field of fractions of the various A over P's. Now, what we will do tomorrow is to show how this locally ringed space, the spectrum, varies with respect to the ring A, and how to reconstruct the category, let's say, which may sound kind of silly, of commutative rings from the category, certain full subcategory of the category of locally ringed spaces. So yesterday we made explicit the correspondence between modules over a commutative ring A and sheaves of modules on the spectrum of A. When we view the spectrum of A, the set of all prime ideas, as being a topological space endowed with a sheaf of rings OX equals A tilde. And we have seen that through this functor, the category of A modules can be identified to a full subcategory of the category of all sheaves of modules over OX. It's a full subcategory of the so-called quasi-coherent sheaves on X, which is a purely local condition on sheaves of modules on any ringed space. These are those that can be locally written as copairs of homomorphisms between three sheaves of modules. And this dictionary between A modules and sheaves of modules on X is compatible with most things one can think of, with tensor products, with, of course, it's I already said that the functor is fully faithful, it's compatible with tensor products, it's compatible with homes, provided the first term is a finite representation. The functor, of course, is additive, it's in fact exact, commutes with arbitrary limits. There's one point, perhaps, the one point where the functor doesn't work so nicely, which I should have cautioned about, namely this functor does not compute with arbitrary products, only with finite products. So it is not true that I have an arbitrary family of modules Mi, not necessarily finite family. It's but true in general that the canonical homomorphism of the tilde of this product to the product of the tildes in general, that is not an isomorphism. This comes from the fact that taking the tilde corresponds to localizing with respect to Fi. So this is an isomorphism. It's if and only if it is true for every F in A that the localization of the product of the MI's with respect to F mapped into the product of the localizations is an isomorphism. Now, this, of course, is not true. Localization is just a particular case of extension of the ring extension from A to AF, and ring extension doesn't compute with arbitrary products. Takes the MI's to be all equal to the same, let's say, to A itself. So the question is it true that A to the power I localized in F is isomorphic by the natural homomorphism to the product to the ith power of A localized in F. Now let's just check what it means. This here is the family of all elements of A over F parameterized by I, indexed by I. That is families of elements that can be written as xi divided by F to the power ni, where ni depends on the index I here, the xi's being in A. Whereas in here we have elements of this localized module, which would be taking an element in here and then divide by a power of F. This would mean that here we get the elements which are of the type yi, the families which are of the type yi divided by F to the n, where here we have a fixed exponent. And it's clear that you cannot in general write such a family in such a way that these exponents in I should be bounded. So it's practically never the case. Take already one. I guess would be the case if and only if F is new. If and only if I'm sorry, F is invertible or neutral or important, something like this. I guess that this isomorphism holds I being infinite if and only if the ring decomposes into product of two rings, so that F is nilpotent in one of the pieces and F is invertible in the other. which are the two cases where the property is trivial, because in one case, localizing with respect to f is just keeping things as they are, and the other localizing with respect to f is making everything zero. Alright, so that means that practically never will our functor, provided the elements which are neither invertible nor nilpotent. So, if we have, for instance, an integrity domain A, which is not a field, then the functor will not compute with products. And forms, we should be careful also that formation of forms does not commute with taking the tildes. Here we have arrow like this, and this in general will not be an isomorphism, because if we take M to be the free module of rank I, as before, then taking Holmes with respect, where the first term is A to the I, and here it would be OX to the I, this corresponds to taking powers of n, and therefore our previous remark that taking infinite powers doesn't commute with functor tilde here means that taking Holmes doesn't commute with the functor tilde, taking of course underlined Holmes here, sheet of Holmes. If M is not supposed to be at least of finite type. In fact, the right assumption is M representation. So this is the only caution that has to be made when working with this. And as I explained, the advantage of dealing with a sheet of modules rather than with modules is that the ring space on which we are working is a locally ringed space. Namely, that the stalks of the structure sheaf are local rings. I recall that the ring O is a local ring if and only if either one can say there exists one and only one maximal ideal, or one can say also that the invertible element, that the non-invertible elements are stable under sum, namely form an ideal. Of course, if you have a non-invertible element multiplying by another element, it's still more non-invertible. So it's stable under sum, but they form an ideal. And this ideal will then be automatically the maximal ideal. The complement of this ideal is a set of invertible elements. So this also equivalently can be phrased that in the following way, that if you have two elements f and g, such that f plus g invertible, then f or g must be invertible. And multiplying this by the inverse of the sum, this amounts to saying that if f plus g is equal to 1, then f or g is invertible. All these are equivalent conditions. So this means, so f plus g equals 1, this means that g is equal to 1 minus f. So this means that either f or 1 minus f must be invertible for every f. Or replacing f by minus f, this means that f or 1 plus f must be invertible for every f. 1 for every f or 1 minus f or 1 plus f as you want is invertible. So all these are different ways of saying that the ring is local. And so here modules over a ring, which seem kind of simple, are replaced by sheets of modules over a sheaf of rings, which seems more intricate, but here the rings here are local rings, and we can kind of decompose this global situation into what happens locally around every point of X. That's what is interesting. And which makes this geometric language technically so useful. In fact, makes it much more intuitive.
Can I ask a question?
Yes.
You corresponded the sheaf of modules which is quasi-coherent and modules the correspondent ring which is quasi-coherent, or module over correspondent ring for the X corresponds to the sheaf of modules which is quasi-coherent. What was the correspondent? I probably didn't understand that.
We have a functor which goes from the category of modules over A to the category of modules over the sheaf of rings OX. Now this functor is fully faithful. That's the first thing we have seen. That means it allows to identify the category of modules here to full subcategory in here.
And which
Now the fact this question is, what are the elements in here in the essential image of this functor, namely what are the sheaves on X which are isomorphic to a sheaf of the type M tilde, and the theorem is that these are exactly the quasi-coherent sheaves of modules. So that in fact our functor induces an equivalence between the category of A modules and the category of sheaves of OX modules that are quasi-coherent.
And the proof is you use the descent to construct the sheaf of modules.
This proof is essentially descensory. You can do it, in this particular case, by playing around with Fi's and Gi's, such as sigma Fi Gi is equal to 1. But I gave an indication of a proof which has a much larger scope, as being a proof of descent theorem for faithfully flat descent whenever you have an algebra A prime over A, which is faithfully flat.
Yeah, and about that faithfully flat, I want to see the example like if we make the additive topology or something, when ring is netted, the completion becomes faithfully flat. And
If you have a local Unitarian ring,
yeah.
the completion is faithfully flat over it, yes.
Right. And
That's very useful.
I just didn't understand the idea of descent, which is it's important. So could you give me some examples?
So in this case, if A is a local Nessarian ring, if A hat is a completion of it, then the idea would be the following. We want to construct a module over A. Quite often we can't do things directly over A, but we can do it over A hat, which is the inverse limit, by definition, of A divided by powers of its maximal ideal, or just Artin rings. And quite often we may be able to construct modules over A hat that by, for instance, taking inverse limits of modules over these rings here. And then quite often it comes from the problem we started with, namely that there was a problem over A. It will turn out that this module, call it M hat, although we don't know if it is a completion of some M, we don't have an M yet. You see? We will know that if we look at the tensor product of A hat by itself over A, we will know that the two inverse images of M hat by the two base changes which were from A hat to A hat tensor A hat, that we have an isomorphism between these two, M hat 1, let's say, and M hat 2, two base changes. We have an isomorphism between the two, having the usual transitivity condition. Now when this is so, we know, because A hat is faithfully fit over A, that there exists a unique module M over A up to canonical isomorphism, so that M hat is deduced from this by base change from A to A hat. And so that the descent data which I had on M hat comes from the canonical descent data which I have from M A hat, which has been obtained from M. And when M is of finite type, which means also that M hat is of finite type, because faithful, when the algebra is faithfully flat over another, we have a module over A, then this module is of finite type, if and only if the inverse image here it's a finite type. All right. Now, if M is a finite type, then M tensor where A hat is just a completion of M hat. So I mean, then it's amounts to the same to say that M hat is a completion of M, or to say that it's the base change. Now, this situation arises quite often, you see. Also, with one is not a finite type, by the way. I mean, if you have schemes that you want to construct over A, you first may construct over A hat, for instance, currents and such things, currents over A hat. And then you may be able to descend it, because the initial problem which was on A. And so it's not that, because if you have a problem which
module which is finite generalizable, then how does one come back from if we had a module of completion model, and how to come back to the module which is not complete corresponding module? I think you
well,
said
that's
something.
precisely through this descent. This
Yeah.
is descent data. And that's
So
exactly it. That's the total story. But I think you shouldn't worry, because for what we are really doing here, I mean, it doesn't matter too much. I refer to this descent yoga for indicating quickly a fancy proof of the characterization of sheaves that are the type M tilde, you see. But, well, you may as well admit this. The theorem, I'm not sure that we are going to use it by the way. This characterization of the sheaves of the type M tilde. What is really still more important is you see that, I mean, we have this functor which has such nice properties, and the essential image is what it can. Turns out that it can be characterized by local property. Never mind. So, if you want a reference to the yoga of descent, there is one of my Buraki talks on descent, which kind of gives the philosophy of it, and gives some main statements concerning descent. But here really we are speaking of, in a way now already, in a rather different. context. So the space is locally ringed, for instance, can be interpreted in the following way. It means that whenever we have sections of, I say locally ringed, so is that the sheaf of rings is a sheaf of local rings. So that can be interpreted in the following way. Whenever we have an open subset of X, and if we have sections Fi of this sheaf of rings over U, such that the sum of the Fi's is equal to the one section, and if you look for every I to the subset U lower Fi of U consisting of all points in U, such that Fi at the point X is invertible in the store, in O capital XX, which also means that the image of this element of the store in the residue field of this local ring, which is generally designated by kappa X. So, and this image of the value of Fi at X viewed as being an element of the store in the residue field is generally called by Fi of X. So don't confuse Fi lower X, which is an element in the stalk, and Fi of X, which is an element in the corresponding residue field. I'm here carrying over the notations which I have used for affine algebraic spaces so far. So, if we take those for which Fix in kappa x is different from 0. So this is the definition of UFI. So that's in fact, it checks with our definition when u is equal to x of xFi. You see, it's a set of points where Fi of x, you see, in the residue field is not 0. All right. Then if the sum of the Fi's is equal to 1, then this implies that the union of the UFI is equal to u. This is in fact equivalent to saying that the sheaf of rings is a sheaf of local rings. And we have seen that if we associate to every ring A, we associate its spectrum XOX, then we can recover the ring A as being the ring of sections of the structure sheaf gamma XOX. So here now we feel pretty secure that we have recaptured every information that is contained in the ring, or what amounts to the same in the upper algebraic space that this ring stands for, in terms of this geometric object. But in order to feel still better at ease, we have to see what morphisms between rings, or what amount to the same morphisms between upper algebraic spaces, how they can be interpreted in terms of the spectra. So let's give now a homomorphism of rings. A goes to B, U, and look at the corresponding map between the spectra. X goes to Y, call it, what do I know, F, or Phi, perhaps F will be elements of rings, which carries every prime allele of B into its inverse image by U. Phi of P is equal to U minus 1 of P. And we have seen that this is a continuous map from X into Y. And now I want to see how this map relates to the sheaves on Y and X associated to modules M over A and N over V, say. Now, so there are several things to say. Let's speak first, if you want, of the sheaves of rings themselves. The sheaf of rings OY on Y and OX on X. I say that we have a natural homomorphism of sheaves of rings that goes from OY into OX in the opposite direction of Phi. Or it amounts to the same, that we have a natural homomorphism of sheaves of rings of OY into the direct image of the sheaves of rings OX. Ring homomorphism. Now, in order to define such a homomorphism, I have to define it only for the pre-sheaves. So I have to define for every F in A, I have to define a homomorphism which goes from gamma OY. I have to define for every F in A homomorphism of rings which goes from gamma YF OY to gamma inverse image of by phi of YF and OX. This here are the sections by definition of the direct image of a sheaf of this direct image phi star of OX. In order to take the section of the direct image of a sheaf on an open set, I take the inverse image of this open set in X and the section of the sheaf over it. So that's here. And now we have to make explicit what these here mean. This, by definition, is A localized in F. We know that this open set phi minus 1 of YF, that's just X localized with respect to UF. That's the points of X where UF doesn't vanish. And this here is just the localization of B with respect to UF, or also the localization of B with respect to F that amounts to the same. Maybe I should have said, if B is an A algebra and if F is an element of A, then localizing B with respect to the image of F and B, so that we get the localized algebra as the same thing as localizing B as an A module with respect to F. Should I prove it? I mean, it certainly comes out of one of the universal properties. I think it's good. Maybe I need to prove it. All right. And of course, because A is mapped into B, AF is mapped into BF. And these homomorphisms are, of course, compatible with the restriction maps, with transition maps between the AFs. If you have a G such that YG is contained in YF, so that we have a diagram like this, with vertical restriction maps, and here you have the maps we have just defined, then this square will be commutative. So we have a homomorphism of sheaf of rings. So phi can be viewed as being a morphism of ringed spaces. Now, we will give some properties about this homomorphism for the sheaf of rings a little later. For the time being, let's not worry about more special properties. And let's see. Let's remark, however, that the homomorphism for the rings can be reconstructed when we know the morphism for the ringed spaces, because U can be viewed as being the morphism from gamma Y OY to gamma X OX induced by the morphism of ringed spaces phi. Because when we just apply the previous definition to the case when the open set down here is y itself, then we get that this map here is just the given map from A and to B. Therefore, we already see quite trivially that ring homomorphisms can be interpreted as being certain homomorphisms of ringed spaces from X and to Y. The set of ring homomorphisms from A and to B is a subset of the set of all homomorphisms of ringed spaces from X and to Y. Before we bother which are those homomorphisms that come from ring homomorphisms, let's first see what happens for the modules. I think this can be seen independently. So take a module N over B. It's a sheaf of OX modules. And because this is now, phi is now a homomorphism of ringed spaces, a morphism of ringed spaces, if you look at N tilde, which is a sheaf of OX modules, phi of N tilde can be viewed as a sheaf of OX modules. Of Y modules, I'm sorry. Of OY modules. So the image of a sheaf of modules by a morphism of ringed spaces, and again a sheaf of modules. And now I will give a formula for this, which is again the one handy formula which I might remember. And I would like this to come from a module over A and to be of the type M tilde, let's say, where M is a module over A. Which module could we possibly hope for? Well, N is a B module, and we would therefore restrict scalars to A and get N as an A module, and take that phi of N tilde is equal to n. Let's call it now restricted to A in order not to write the same n. N, where the module structure is restricted to A, tilde. So I claim that we have a canonical isomorphism like this, which means that direct images of sheaves of modules is interpreted in the dictionary to commutative algebra in terms of restriction of scalars. Now, let's give the, what is 5n tilde? It's in terms of pre-sheaves on Y, and working again with the basis of open sets defined by the open sets of the type YF, F being an element of A. That's the pre-sheaf. F goes to sections over phi minus 1 of YF of n tilde. And you have already noticed that phi minus 1 of YF, that's x over F. That's x localized with respect to, let's say, UF, if you prefer. And so, this here is just the localization of n with respect to UF. And we have already noticed, well, special case, that that's the same thing as the localization of n with respect to F, and n is viewed as an A module. So let's see, that's what we really need. If you have an B module n, then if you localize n with respect to UF, it's the same thing. And if you restrict then the scalars to A, it's the same thing as if you restrict first the scalars to A and then localize with respect to F. That means that making F invertible in N as a B module or as an A module is the same thing. It comes from, for instance, from the fact that we have written the localized module in terms of the argument of copies of F of N, and this doesn't depend on which is a ring or which we consider N. It just depends on the multiplicity F that is defined in N. All right, and of course, this isomorphism is functorial with respect to n, and therefore we get this formula here. Now, let's restate this formula perhaps a little differently. Start with a sheaf of modules f on x and assume it's quasi-coherent, assume that f is isomorphic to some n tilde, where then n will be an B module which is determined up to isomorphism. Maybe I should write higher up that f, yeah, I like to write the things you see which are on x over x, and let G be a sheaf of modules on Y, which is quasi-coherent. That means that corresponds to A module M. And I want to determine the homomorphisms of sheaves of modules from G into F compatible with the continuous map phi, which can be described either in terms of homomorphisms of G into the direct image of F or as homomorphisms of the inverse image of G into F. All right. Now, if you use the first thing, this means that hom over phi of G into F, but being understood that we want to respect the module structure, that's the same thing by definition of homomorphisms of sheaves as hom of G into the direct image of F. Now, G is equal to M tilde, and the direct image of F is equal to n restricted to A tilde, and therefore, because the tilde functor is fully faithful, this is the same thing as the set of homomorphisms over A of M into N. Therefore, to give a homomorphism, if we have these sheaves F and G here, to give the homomorphism of G into F compatible with the continuous map F phi, we viewed as being a morphism of ring spaces, is the same thing. If we look at the situation in terms of multiplicative algebra, with the module n here and the module m here, to give a homomorphism of m into n, which is alinear, which is compatible with this homomorphism on the scalars. So, but this can be interpreted either as mapping m into the A module reduced from n by restricting scalars to A, or it can also be described as being a homomorphism of M tensor AB into N. This homomorphism being taken now over B, which we can also write, because the tilde functor now on X is fully faithful, as a set of homomorphisms of sheaves of OX modules of M lower B tilde. M lower B is just the M tensor AB reduced from M by base change into N tilde, which is just the sheaf we started with, F. And if now we use the notion of the inverse image functor for sheaves of modules, this means that if we look at the inverse image by the morphism of ring spaces phi of the sheaf of modules G equals M tilde, that this inverse image is canonically isomorphic to M lower B tilde. That means that taking inverse image of sheaves of modules is interpreted here when we come back to the modules that are associated to the quasi coherent sheaves in making the ring scalar extension from a ring A to a ring B. So direct image of sheaves corresponds to restriction of scalars. Inverse image of sheaves of modules corresponds to extension of scalars. So that sets up the dictionary of variance of for variable rings, that is variable spectra, of sheaves of coherent quasi-coherent sheaves of modules. Now, let's come back now, let's forget about the modules again, and let's come back to the sheaves of rings. So we have said that if A and B are two rings, then the set of homomorphisms of rings from A and to B is mapped into the set of morphisms of ring spaces of the spectrum X of B into the spectrum Y of A. And we have seen that this map is injective. And now we want to see what are the special properties of the homomorphism of ring space from X into Y, which express that they come from a ring homomorphism. Now here we have to recall that X and Y are locally ringed spaces. That's the stalks of the structure sheaves are local rings. So here the stalks here are local rings, the stalks here are local rings. Now the fact that we have a homomorphism of ring spaces implies that for every point small x in capital X and small y in capital Y that correspond to each other by the map that we have. So phi is a map if y is equal to phi x. Then we get in the opposite direction a homomorphism for the stalks, a ring homomorphism. And now when we have a homomorphism between local rings, I mean, this homomorphism is kind of reasonable. If it's a so-called local homomorphism, that means if the inverse image of the maximal ideal here is equal to the maximal ideal there. In other words, if the maximal ideal here that's it. So let's give a definition. If you have a local rings O and O prime, and if you have a homomorphism between these rings, call it U. U is said to be local if and only if the inverse image by U of the maximal ideal M prime in O prime is the maximal ideal M of O. So this inverse image of the maximal ideal will be, how should we say? I want to express this differently.
The image of M should go.
A priori, you see this inverse image is contained in M. In M minus 1 of M prime must always be contained in M. Why is this? That means that if you have an element in O whose image in O prime is an M prime that is non-invertible, then this element here must be in M that must be non-invertible. Because if it was invertible, then its image in O prime would be invertible too. Alright, so in all cases we have that the inverse image of M prime is contained in M, but we want it to be equal to M. And why do we want this? Well, that just means that that's essentially the necessary and sufficient condition in order to be able, for instance, to deduce from U by passage to quotient a homomorphism from, let's see how. This also means that U of M is contained in M prime. So this condition here just means that U of M is contained in M prime. That's it. And this also means that there exists a homomorphism which goes from the resolute field into the field of O, into the field of O prime, that is induced by U, maybe, that makes this diagram here commutative. Or still another way to say it is that if f is an O, then f is invertible if and only if U of f is an O prime star. Of course, if f is an invertible, whether we have local rings or not, whether U is local or not, UF must be invertible O prime star. And here, it's we're interested in the converse. So this is the notion of a homomorphism of local rings that is local. And now if we have locally ringed spaces x and y, a morphism of ringed spaces from x and to y is said to be a morphism of locally ringed spaces, or it's said to be local, if for every pair like here, the corresponding homomorphism between the local rings here is a local homomorphism of local rings. So phi is said to be local, or a morphism of locally ringed spaces if and only if for every x in x, if y is its image, the homomorphism between the stalks is local. Now I can express this without using points, without using the stalks, in the following way. That means also that for every section of the structure sheet of Y, over, perhaps not necessarily over Y itself, we may not have sections of the whole of Y, but let's say over any open set. If you look at its inverse image by phi, let's call it phi star of f if you want. This is the section of the structure sheet OX over the inverse image of U, call it x over U if you want. This part of x induced over U. Now I have the open subset UF in U of the points where f in the residue, where the value of f in the residue field is not zero, as I described before. UF is defined as the set of points y in U such that f of y element of the residue field kappa y is different from zero. That means also that this element of the stalk of the sheaf, structure sheaf defined by f and y is invertible. So look at the subset, and in the same way in XU, call XUV if you want, we have the corresponding subset where phi star of f is invertible, or it doesn't vanish in the residue fields. And of course, we have that without any other condition on phi, whether phi is local or not. But the inclusion which we have is the following. We want to compare V of phi star f and with the inverse image by phi of UF. So what's the relation? Well, wherever f is invertible, then on the inverse image phi star f will be invertible too. Therefore, we will have this inclusion here. Phi minus 1 of UF is contained in V phi star f. And to say that the homomorphism of ringed space is local just means that this inclusion is always an equality. This corresponds to the characterization of local homomorphism of local rings, saying that an element in O is invertible if and only if, and an element in O is invertible if and only if its image in O prime is invertible. Therefore, recall this important formula for morphism of ringed spaces. Let's take for simplifying notations, the case where U is equal to Y. The inverse image of Y over F, where F is a section of the structure sheaf, is always equal to X lower phi star of F. So that's essentially characteristic of local morphisms of ringed spaces. the part, I will have to use this homomorphism is local. So I claim that this homomorphism from AQ into BP is a unique homomorphism from AQ into BP, which makes the square commutative. When I have said this, I'm through. But I'm a little confused now because this argument seems to work without making any assumption on phi, so there's something tricky. So let's see again. Where is there a unique homomorphism of AQ into BP? A ring homomorphism, which makes this diagram of rings commutative. I said this 5 minutes before. And apparently I was wrong. I should have added a local homomorphism. Now let's see where I was wrong. So,
There you using the fact that the image of an XY view was contained in the order.
let's see. So certainly this,
Because I said that the denominator was well defined.
so it is true that BP viewed as being an A module, that's elements of A minus Q, operates there. Invert so as to be isomorphisms. That's true.
That's because
And
it's our home.
therefore, having a homomorphism of A into this, you get a unique homomorphism of A localized in Q into it, which should be a linear. Now I'm a little, I know quite, I'm proving more than is true. That's a little painful. Now where am I wrong? There's something. Some trivial mistake I must have made here. Nobody can point it out to me. So I seem to be proving here that every morphism of ring space from X into Y is local. So I seem, because any homomorphism from AQ into BP, which makes this diagram commutative, is the canonical one, which is local. I mean, that's what I'm. But I know it's. I mean, I can give easy contact examples. So. So what's? I'm mixing up things, I'm afraid.
Maybe you have to use the locality you did that diagram.
No, it seems that there is a unique homomorphism of A modules from AQ into BP. You see, that we can find two such. Where's the trouble then? BP is an A module.
You can only know that if
The elements of QI of I minus QI invertible in it. I have a homomorphism of A into it, and therefore it extends uniquely to a homomorphism of A localized in Q. BP. Now what's wrong? Maybe I should give the counterexample and we'll see what is wrong.
You also use the fact that restriction
Which
there.
one will be PTA? Give us the counter sample and then will be PTA.
No, I think that let's give the counterexample after all. We will take the following spaces. I take a discrete valuation ring, for instance, and that's the first counterexample that comes to my mind. I take a discrete valuation ring V. That means in fact, it's a local ring which has just an integrity domain and which has no other maximal ideal except 0, no other prime ideal except 0 and the maximal ideal. So, for instance, V may be what's the best known discrete valuation ring? Z localized in P or the periodic integers or something like this. Or else, no, I think there's a nicer one which is better known to everybody. Power series in one variable. Alright? So the spectrum has just two elements, one closed point and the general point. I mean, the clone of this general point is here. So we can also do it like this. There's 2 points and this point here, A is that's the closed point, is a specialization of eta. Alright? And we will take, that's it. Alright, and we will take its field of fractions, capital K for instance, which would be K of T like this. And I take its spectrum, so this here would be A. And this here would be B. I have to take, that's it. And now I will define a homomorphism of spectrum of K, which is X, which is just 1 point. So X, the spectrum of P, has just 1 point with capital K on it. And I will define the homomorphism from X into Y. Here's Y, which sends the only point of X into the closed point of Y. So now in order to define a homomorphism between the sheaves of rings, I have just to define a homomorphism of the stalk of the sheaf here to the stalk of the sheaves there. And I will take now the stalk of the sheaf here at the center. It's just A itself. So I have to define a homomorphism from A into K, and I just take the inclusion of A into its field of fractions, which is a homomorphism of rings, but not a local homomorphism. All right. And I claim that this here doesn't come from the, well, because this is not a local homomorphism, that this doesn't come from a morphism between the rings. So this morphism between the rings, we have no choice. It should be A goes to K. But if you look what the morphism it induces between the spectra, you see, well, there's just 1 point in the spectrum of K. It's a point here, and it's a 0 prime ideal, and the inverse image of the 0 prime ideal is a 0 ideal of A. So that this point must go to this point here. And now let's see what is wrong in the argument here. So let's replace the rings by their values. A is the power series, you see. B, that's the field of fractions capital K. B, localized in P. P was the 0 ideal. That's just K. Here we have K. Let's see. And here A localized in Q was just A. So that's so what's that? We certainly have. That's me.
Where are you localizing A? At the ideal generated by T.
Oh, no, I see where the mistake is. In fact, it's not on the rings. It's because I tacitly assumed that the set theoretic map from X, there it is, yes, That's very silly. That's a set-theoretic map from X into Y. We started with a morphism of ring spaces. So a continuous map plus morphism on the rings. And I wanted to show that if you look at the homomorphism between the rings from A and to B that is defined by phi, I wanted to show that the morphism from X into Y that is defined by this homomorphism of rings, call it psi if you want, it's the same as phi, but I assumed already in my argument that phi and psi coincide set-theoretically. But that was the once I have proved this, I'm through because of this argument here. But I have to prove first that they coincide set-theoretically. Oof. So this I kind of skipped because I was just silly. Now, so therefore that's what we have to prove. We have to prove that first the set-theoretic map defined by phi is known in terms of U. That's it. And we know that phi is local. And now I think we can do it because any point. That's it. How will we define? So we have a point X in capital X, which corresponds to a prime ideal P in B. We have its image Y equals in Y. And what we want to prove, that's precisely the main point, is that Y is equal to the inverse image of P. And now, this now should be pretty clear, because we know, because this morphism is a morphism of ring spaces, that if we have 2 points that correspond to each other, then, and if you have a section of the structure sheaf of Y, called a section F, then F is invertible in Y, if and only if its inverse image here is invertible in X. Now, call the ideal which we want to find here Q. We don't know as yet if it's the inverse image of P. But what this shows here is that F belongs, if F is an element in A, then F does not belong to Q, which means that F is invertible at the point Y, if and only if U of F does not belong to P. Just because the homomorphism is a local homomorphism. But this means also that Q, we have described Q through its complement here. We have here written that the complement of Q is the inverse image of the complement of P, which means that Q is the inverse image of P. Alright. So that does it, I think, yes?
So have you shown that there's a way of associating to the ring space locally, the morphism of ring space, is that morphism locally, local morphism?
If you want, if you have a morphism of ring spaces, it defines in the opposite direction a morphism between the global sections. And when we pass to the spectra of these rings, we get a morphism, local morphism of local ring spaces, but these local ring spaces need not be the same as X and Y before. But if X and Y were already spectra, then we would get another morphism between X and Y, which need not be the same. But in fact, when we have local ring spaces, I mean, it's very rare that ever a morphism of ring spaces between them will turn up, which is not a morphism of local ring spaces. I mean, that's the whole. So we should recall that in this yoga of replacing rings that are kind of global things by a spectrum and a sheaf of rings on it, where this sheaf of rings is a sheaf of local rings. In this yoga, when we speak of homomorphism of rings, we should restrict homomorphism of local ring spaces that are with respect to the local ring structure that are local homomorphism. And then everything will be nice. And here you see really how it mainly comes is used this property that phi is a morphism of local ring spaces through this formula here. Yeah. Now, the main technical and also intuitive, psychological advantage of introducing these spectra, these ring spaces, one main advantage is that it will allow us now to define more general objects than just affine algebraic spaces, to enlarge the category of affine algebraic spaces, which now is interpreted as being equivalent to the category of low-covariant spaces that come from ring up to isomorphism. So let's call these affine schemes if you want. So let's call affine K-scheme just a low-covariant space of locally K-ring space that is isomorphic to some A tilde, where A tilde is in K algebra. So these affine K schemes, they are now from an equivalent category to the category of affine algebraic spaces over K. Now we are able to enlarge this category into a category of schemes which would correspond to algebraic varieties, let's say in the classical sense, which are no longer affine. For instance, an important example is, let's say, projective space, for instance, projective number over, let's say, the complex numbers. This is an algebraic variety in a certain classical sense, and it just refuses to be affine. It doesn't have any functions on it, except constant functions. Functions that be everywhere defined, except for constant functions. So the idea is to describe, let's say, schemes. These are the things that will generalize affine algebraic spaces, schemes over K if you want, to describe them as being local ring spaces having certain property which will generalize affine K schemes and will define a scheme, let's say, first to be a local ring space that means a topological space X endowed with a sheaf of rings or X on it, which locally is an affine scheme. That means such that X is the union of open subsets Xi, every Xi being an affine scheme, which means, I recall, that Xi is isomorphic as a ring space to some AI tilde, where AI is some commutative ring. So here, the spectra of commutative rings are, so to say, the models which we work with, the local models of schemes, and schemes globally are obtained by catching these together. So the definition of equals is pretty trivial. And we will say that we have a K scheme if you want. If we have a locally ringed, a locally K-ringed space, namely the sheaf of rings is a sheaf of K algebras, which has the same property. But if you have just a scheme that means a sheaf of rings, to put a structure of a sheaf of algebras over it just means that we give a homomorphism of rings of K to gamma XOX, so that's a rather trivial extra structure. Which will then imply, of course, because gamma XOX is mapped into each of the gamma UOX, where U is an open subset of X, that each of these rings will be an algebra over K. Now, we described, on the other hand, our main yoga when we were dealing with affine algebraic spaces here, was that these were interpreted as functors on the category of K-prime algebras. And we would like to interpret also K schemes as being functors on the category of K-prime algebras, so that we just have described known functors that are a little more general representative functors. Functors that are schemes, we would say. So we still have to, if X is a scheme now, let's write a little diagram. Now the category of affine algebraic spaces over K, which we more or less identify with the category of affine schemes over K, henceforth we will not really distinguish between the two, has been written as a full subcategory of the category of all functors on the category of K algebras, according to the category of sets. And I would like to interpret the category of schemes over K, call it. Where of course the morphisms of schemes are the morphisms of locally ringed spaces, namely the morphisms of ringed spaces that are local moreover. This must be understood. I want to view it as being, of course, a category that contains this category as a full subcategory, but which is also embedded as a full subcategory in the category of K algebraic, of functors from K algebras to sets. So if X is an object in here, I will have to describe what is a functor with respect to a variable K prime that it defines. I have to define the K prime points of X, where K prime is any K algebra. Then the 2 points of view, the point of view of schemes, of locally ringed spaces, and the point of view of having something which has points in with values in any K algebra, these 2 points of view will match. Now x of K prime, how will I define it? Let's first see what we should do if X is an affine scheme, if X is in fact in the subcategory. Let's recall what we did in this case. So assume first that X is equal to the affine algebraic space, let's say, defined by a K algebra A. Then xk prime was just the set of homomorphisms of K algebras of A into K prime, or equivalently the set of homomorphisms. Now we will use the fact that homomorphisms of rings correspond to homomorphisms of the spectra in the opposite direction. So we can say that these are also the homomorphisms of locally K-ringed spaces of whom into whom of the spectrum of K prime into the spectrum of A, or the spectrum of A, that's just X. So I mean, it's just to X as a functor, we associate the functor represented by X, but this functor represented by X would be a covariant functor of this category, but this category being opposite to the category of rings, it's a covariant functor of the category of rings. Now we come back to the contrariant way of viewing it. All right, now this here makes a sense, this last expression makes a sense, whether X is in the subcategory or not. So we will write in general that xk prime is just equal to the set of homomorphisms compatible with the K algebra structures of spec K prime into X. The home now, it's understood once and for all, if I write a homomorphism of schemes, it just means homomorphism of schemes, namely morphism of locally ringed spaces. And if I write a subscript K, it means that I want that the K algebra structure should be also respected. So what we did was at least to define a functor going from the category of K schemes to the category of functors on K algebras, as well as in sets. Because of course, the functor associated to an x defined by this formula depends functorially on x. If x varies, then this depends in a covariant way on x. And now, in order to be satisfied that we have here really an interpretation of k-schemes in terms of functors, we have to show that this functor going from k-schemes to functors on algebras is fully faithful. That then will mean that the category of k-schemes can be interpreted as a full subcategory of the category of functors on k-algebras. Now, why is this so? In other words, that we know a scheme when we know its points as well as in any k prime, for any k prime. Let's see. If we have time, that should be pretty easy to prove, I guess. So we want to show that if we know the functor associated to x, we can reconstruct x. So we could do it, of course, by doing something analogous to the construction of the spectrum. I think that would be a little lengthy, perhaps. First, describing the points of x as being equivalent classes of points of the functor with values on fields, then defining a topology on it in an analogous way of what we did before. However, it would have to be a little careful, I guess. But maybe it would be easier to prove directly the full faithfulness by proving that if x and y are two schemes over k, and then the map which goes from home x, y to home, let's call the functors for the time being x tilde and y tilde. No, that would be x prime and y prime if you want. First, once we know that the functor is fully faithful, we will just identify the schemes with functors they define. Let's say home x prime, y prime. X prime and y prime are the functors on k algebras associated to x and y. Maybe we can prove directly that this is bijective. So, yes, I think we can do it the following way. First of all, it's true if x is affine. Because if x is affine, then instead of if x is equal to v lower a, if you want, then the morphisms of x into y, in this case, they just correspond to the points of y with limits in a. That's the definition of y of a. And what about this here? All right. So we could call this y prime of a, I'm sorry. And here, this functor x prime here is a representable functor defined by x. And therefore this here also is equal if the morphism of a representable functor into any functor are just the elements of y prime of the object that represents it. So in this case, our formula is kind of tautological. It's essentially the definition of the functor associated to. All right, so we know it already if x is affine. But on the other hand, we know that x, in the general case, x can be covered by affines. Let's say x is a union of affine open sets xi, And
In general, you care if the union is,
uh,
is that union always final?
no, I don't assume anything such. Now, the intersections of the xi's may not be affine, you see, in general. But let's first assume that they are. Assume xi and the xx, xj is affine for simplifying the argument. So that we know that for both, call these xlj, we know that for xi and for the xilj's, that this, if you replace x by either of them, then this bijectivity will be true.
I think xi is opening x. I think xi is opening x.
Are the xi's open? Yes, always. Yes, I mean by definition of a scheme can be covered by open subsets, such that these open subsets are affine for the induced structure sheaf.
There's an intersection at 12 times. Opening intersection.
Not-
open.
no. If x is separated, yes. If it's a separated scheme, but it need not be separated. Now, it will turn out in fact that x can be viewed as being the direct limit of the xi's of the following diagram. I have xij's that are mapped into both xi and xj. And this for every index I and for every index j. Alright, so I have here a certain diagram. And in the category of locally ringed spaces, x can be viewed as being the direct limit of this diagram. Which just means the following thing. I mean, here I set things in a fancy language, but in down-to-earth language, this means that in order to give a morphism from x into any locally ringed space y, well, when we say morphism, we assume k-morphism. Right? It's the same thing as to give a morphism of x into each of the xi's into y in such a way that they measure the intersections. It means that the diagram here I take the product over all i's of hom xi y, and here I take the double product hom over indices ij of hom xij y, and that this is exact. Now that's pretty clear. I mean, first of all, to define a continuous map from x into y amounts to the same as to define it on the xi's in such a way that they measure the intersection. And the same is true for the homomorphisms of shields, which is a local affair too. So, in the category of schemes, x is the direct limit of the xi's by the xij's. And for the xi's and for the xij's, we know already that if you replace x by z, that this map here is bijective. So all we have to do is to prove that we have the same kind of exactness here, with putting primes everywhere. Because we have a diagram, quantitative diagram of sets, and if you know that we have bijectivity here and there, then we have bijectivity on the kernels. Therefore, all we have to prove is that this diagram is also exact. In other words, we have to prove that x prime is, which we have here, so x we said is the direct limit of the xi's by this diagram of arrows. We have to prove that x prime is the direct limit of the x prime i's under this diagram of arrows. Alrighty, and now I guess it requires a little proof. And I guess you maybe should stop. So let's reserve this for next week. So there's a slide proof to fill in here still. And however, I once again insist on the conclusion, which is quite important for the general yoga. We have described the category of schemes in terms of certain very specific structures, namely local spaces, and this seems to be pretty far from the original setup of defining geometric objects in terms of functors on the category of K-algebras, and now we have seen that any scheme defines a functor with respect to variable K prime, and that the scheme can be reconstructed from knowing this functor, namely that the functor which goes from schemes to functors on algebras is fully faithful. It gives an embedding of the category of schemes in the category of functors. So henceforth we will just identify according, to the context. We will either be happier to view a scheme as being a local space or to view a scheme as being a functor going from K algebras to sets. So let's stop for 10 minutes, and then I will go on with algebraic groups, so far. Are there any questions about last lecture? Last time we finished explaining the correspondence between rings and the spectra viewed as local spaces. We saw that the category of rings, or if you prefer the category of affine algebraic spaces over a given commutative ring K. So this is just the opposite category essentially, which is equivalent to the opposite category to the category of K algebras, can be embedded in the category of local ring spaces. Where this category is a category whose objects are topological spaces X endowed with a sheaf of local rings, I mean a sheaf of rings, all of whose stalks are local rings, and the morphism from such an object into another are the continuous maps from X into Y endowed with no morphism for the sheaves of rings in the opposite direction, such that for every point X in capital X, if Y is the point below it, so that we have a homomorphism for the stalks, we want it in the opposite direction. For the stalks of the structure sheaves, we want that this homomorphism should be a local homomorphism. Which means also that maybe we rather call phi the continuous map as we did the course. That means also essentially that for every F section of the structure sheaf of Y, if we look at the set Y lower F, where F is invertible, which is an open subset of Y, the largest open subset of which is invertible, which consists of those points of Y where the value of F at the stalk is invertible, which means because the stalk is a local ring, that its image in the residue field, its value in the residue field, is different from 0. So we have Y of F, and we look at the inverse image of YF. This certainly should be contained in all cases, whenever we have homomorphism of ring spaces in XF. But to say that we have homomorphism of ring spaces means that we have equality. And the same will replace X, will replace Y by an open subset. So if we have F over a section over any open subset of Y. The same equality will hold, where YF is replaced by UF, U being the open subset on F, which F is defined. All right. So this gave us a geometric interpretation of affine algebraic spaces over K, namely certain functors over K. In terms of these local ring spaces, and we have used this fact in order to enlarge the category of affine algebraic spaces into a subcategory of local ring of the category of all local ring spaces, the category of so-called schemes. So we can put as the category of schemes in between, which is the category of the full subcategory schemes over K, let's say here. Embedded in the category of local ring spaces over K, I could put the structure of K algebra of these local ring spaces because we have the K here. Alright? Which are those local ring spaces in K algebra, such X, OX, such that every point of X has an open neighborhood, which for the induced structure is an affine scheme, namely is isomorphic to the spectrum of a commutative ring, which is a K algebra. So this we have seen last time. So I just repeat, just summarize what we have seen. And now, and then we started looking for an interpretation of schemes over K in terms of functors from K algebras to sets. I would like, before taking up this point, I would like to give a compliment, which is a little before. We have seen that if X and Y are the spectra of two rings B and A, that then the homomorphism of ring space from X to Y correspond to the ring homomorphism from A and to B. I mean, this was the starting point of our interpretation. This category here is subcategory of subcategory from there. Now this can be generalized by assuming that only Y is an affine scheme. So let's see. Assume that X is just a local ring space. Over K in K algebras, and let's assume that Y is an affine scheme, the spectrum, therefore isomorphic to the spectrum of some ring A. And I'm interested in determining the set of all local homomorphisms from X into Y, homomorphisms of local ring space from X into Y. Now what I contend is so K local ring spaces is that this set is in one-to-one correspondence with the set of all K algebra homomorphisms from A, which is just gamma Y O Y, into gamma X O X. So that was essentially what we stated before when X and Y are both affine, but now I say that X should not be affine for this statement to rule 2. With the homomorphism of a local ring space in K algebras into the spectrum of a K algebra, not the same as to give a homomorphism in the opposite direction of a homomorphism of K algebras of A into the ring of sections, algebra of sections of O of the structure sheaf of X. That is equals the set of algebra structures of A algebra structures on OX that extend the small K algebra structure. if we forget about k in the story, then if we take k to be z, so that we're just speaking of rings, not of k algebras, then this would mean that's a set of morphisms of the ring space X, of local morphisms of local ring spaces, of the local ring space X into local ring space Y, can be identified with a set of ring homomorphisms of A to gamma X over X. That means with a set of A algebra structures that we can put over OX. So to give over the local sheaf of rings OX, sheaf of local rings OX, to give moreover an A algebra structure where A is some ring, is the same thing as to give a morphism from the local ring space X into the spectrum of the ring A. Morphism of local ring space. Now, the proof of this bijection here is essentially the same as in the case of affine that we did when X was also assumed to be an affine scheme. I will just quickly indicate how this is done. So we have, of course, an arrow from left to right, because when we have a morphism from X into Y, we have a homomorphism in the opposite direction between the rings of sections of the structure sheaves and the ring of sections of Y is just A. Alright, so we have an arrow in this direction. So all we have to do essentially is to define an arrow in the opposite direction, and it will turn out quite evidently that the two arrows will be inverse of each other. So I start now with an element in here, in the second term, namely a homomorphism from A into gamma XOX, and I will define in terms of this a morphism of rings, local ring spaces from X into Y. So I have to do it in 3 steps. First, to define the set-theoretic map, then to prove it's continuous, and then to define the morphism on the sheaves. Alright, so the morphism for the local ring spaces associated to U I will call phi. So when I will have defined phi, I will have defined the arrow in the opposite direction. So first, set-theoretically, phi of X, if X is any point in capital X, well, it should be an element of Y which is a spectrum of A, so it should be a prime ideal of A, and we will take phi of X equals the kernel of the compositum A goes to gamma X OX. Now, a section of the structure sheaf of OX, you see, defines an element of the stop of the structure sheaf at this point small x. That's capital X at the point small x, and I take phi of X to be the kernel of this. So this defines the map from X into Y. Now I have to prove that phi is continuous, and therefore I have to check that the inverse image by phi of any one of the open sets YF and Y, which make a basis for the topology, F being any element of the ring A, of sections of Y, I have to show that these subsets of X are open. But what is phi minus 1 of YF? That consists of those points X in capital X such that phi of X, which has been written down here, is in the such that phi of X is in YF. That means such that F is not in the prime ideal that describes phi of X. That means such that the image of F under this compositum is not 0. But this means if F is the element here, and here we have the homomorphism U, UF is the corresponding element here, that means that we look at all points X such that the image of UF in kappa X is not 0. That means that UF, its image in the store small x, O capital X small x, is invertible. But this is a set which we have called X lower UF. That's just the largest open set of X where UF is invertible. As it should, of course, if phi is to be later a morphism loop clearing spaces. All right. So therefore, the inverse image of YF is an open subset of X. Now I have, moreover, to define the homomorphism for the sheaves of links in the opposite direction, and that means that for every F, I have to define a homomorphism from gamma of YF OY into gamma inverse image of YF, namely X UF and OX, in a way compatible with restrictions to open subsets for every F in A. So I have still to define these maps in a way compatible with restrictions. They would be K algebra homomorphisms, I guess. And what do we do? This here is just A localized in F. And to define a homomorphism of A localized in F into some ring or algebra, you have just to define a homomorphism from A into this algebra, so that F becomes an invertible element in here, by the universal property of A over F. Now, A has been mapped already by you into gamma X or X, and by composing it with restriction map to this open subset of X, we get a homomorphism of A into here. And what is the image of F under this? Well, we have to take UF here, and we take the restriction of UF to the open subset X UF, which is precisely the largest open subsets, where UF is invertible. So therefore, the image in here is invertible here. Therefore, we have a unique factorization, like this. And because of uniqueness, this shows that for variable f, for variable open subsets yf of y, these maps here are compatible with restrictions. All right, so I have defined a morphism of loop-filling spaces from x into y. I'm not quite through yet. I have defined the homomorphism on the sheet of things. I have still to prove that it's a morphism of loop-clearing spaces. So that's the first point. But that's essentially one way of viewing it. This relation here. Except that we have to restate it when you replace f by a section of a y or a smaller open set. All right, but you can also look at what the induced map on the stalks is, and you will find it's a local homomorphism. Never mind, it's trivial checking. All right, so this finally gives us this arrow in the opposite direction, and it's a mere triviality to check that these two arrows are inverse of each other. Now, this shows in fact that the spectrum of a ring can be described intrinsically without making a stepwise construction as an adjoint of the functor going from loop-clearing spaces in K algebras to rings, which is a congruent functor in fact. Never mind, perhaps it's safer to write it with an O over here, which associates to every x gamma x OX, which is a functor which transforms sum with respect to f x into product, I guess. And now this formula just says that the functor going from rings to local ring spaces, which is the spectrum of the ring. Let's write here the spectrum of A if you want, in this formula. Spec A is never, well, that's this functor is right adjoint, I guess. Whatever knows. No, left adjoint if you take a functor 0 here, because this formula is reversed. Left adjoint of this functor. So there exists a unique functor going from, call it A goes to spec A, going from rings to locally ringed spaces, or K algebras to locally ringed spaces in K algebras, in such a way that we have this bifunctorial, such a bifunctorial mapping. So in a way, provided you grant that the notion of a locally ringed space is interesting, and in fact, the notion of a differentiable variety or of an analytic variety, whether real or complex, can already be described in these terms, then in a way, then by the same token, you grant that the spectrum of a ring is interesting because it's a unique universal construction associated to a ring, a locally ringed space. Such space has such a nice formula. Now, let's turn again to schemes now, which are particular locally ringed spaces. In particular, if X was a scheme, particular case of a locally ringed space of K algebras, let's say, if X was a scheme over K, then to give a morphism from X into Y is the same thing as to define the structure sheaf of X as being a sheaf of A algebras. I'm just repeating what I said before, except that X now is a scheme. Now, therefore, in the first place, don't speak about any A, but let's say to give a scheme over K, which means a locally ringed space where the sheaf of local rings is in fact a sheaf of K algebras, is the same thing as to give a scheme X over Z, just a locally ringed space with no extra algebra structure, with no K involved, and moreover, to give a morphism of schemes of X into the spectrum of K, call it S if you want. So in this sense, the K in a way is in a way kind of irrelevant. It can be described by a more satisfactory, intuitive geometric picture, namely K be just replaced by its spectrum, which is just a scheme in the absolute sense, over a scheme over Z. It's a locally ringed space. And to give a scheme over K is the same thing as just to give a scheme X, and then to give an arrow of X into S. It's what we would call a scheme over S. That is, that the category of schemes over K can be viewed as being reduced from the category of all schemes, in the absolute sense, schemes over Z, by taking the reduced category over S. And when we make this picture, then we have the intuition of X being viewed as something like a fiber space over S, and the way we are going to work with a scheme over another S is exactly the same way as if one works with a topological space over another. And it's quite important to deal with situations of a scheme over another, where S is not at all assumed to be affine. And therefore, quite systematically, one will replace the context of a scheme given over a ring K by the context of a scheme X given over another scheme X. Now, if S is affine, if S does correspond to ring K, what is the interpretation then of the category of K algebras, so that a scheme X over S will define a functor on the category of K algebras, from K algebras to sets? Well, a K algebra K prime is the same thing by the same token. If S prime is a spectrum of K prime, as an arrow, as being a scheme an affine scheme in the first place, namely a ring K prime, together with an arrow from S prime into S. Therefore, the category of K algebras now is, up to the array reversing, is namely taking the opposite category, becomes equivalent to the category of all rings K prime lying over S, as we will say, namely all rings K prime together with an morphism from spec S prime into S. It can be viewed also as being the category of all affine schemes S prime lying over S. Therefore, if we like to interpret schemes in the relative case, X over S, schemes over S, as functors on rings which look like algebras, you see, we would consider it as a functor on the category of all rings K prime lying over S in the sense I just said, which one could call them S algebras in a way. But let's for a little while perhaps still conserve, in order to investigate the situation, the relation between schemes and functors, let's for a little while still conserve the ground ring K. Now, I want to interpret schemes over K as functors on something. Now there are various ways of doing so. First of all, there's the most evident way of all, namely to apply the general setup which says that if you have any category here, it would be the category of scheme over K, then the object of C can be interpreted as being consequent functors from C to sets which are representable. So the category of schemes over K can be viewed as being a subcategory of the category of schemes over K head of the corresponding category of functors. And this is quite often done, quite systematically. If you have a scheme over K, we look at the consequent functor it represents and we identify the scheme with this functor. Now, of course, I can also, for having this functor, I can restrict this functor to affine schemes over K. Or affine algebraic spaces over K. Now I have the interpretation of affine algebraic space over K as being equivalent category to the category of affine schemes, how would you call it? Schaff over K, schemes affine over K. And so every scheme over K defines a consequent functor from affine schemes over K to sets, a consequent functor, or what amounts to the same, a covariant functor, going from K algebras to sets. And what we stated last time was that the compositant functor here is fully faithful, so that the schemes over K can be interpreted as being forming a full subcategory of the category of all functors going from K algebras to sets. We know already by the general nonsense that this arrow here is fully faithful, but this, I should say at once, is not fully faithful, but the compositum is. Now I will have to explain why. Now, therefore, we will first introduce an important.
What is the algorithm for scheme K to affine?
Here,
Yeah.
it's not a. It doesn't go from schemes over K to affine schemes over K, but from the category of functors, consequent functors on schemes over K to the category of functors on affine schemes over K. It's a restriction functor. As you have an inclusion of categories here, whenever you have a functor on the bigger one, its restriction is a functor on the smaller. Now we have to introduce an important property of those functors, let's say, from schemes to from K schemes to sets in here that come from there. So let X be an object in here, a scheme over K, and look at the functor. It represents y goes to home of K schemes of y into x. Now, whenever y is covered by open subsets yi, it's clear that the morphism from y into x is known when we know its restrictions to the yi's. To give a morphism of local length spaces, to give a continuous maps plus a morphism on sheaves, that's a local affair on y. And in fact, so this morphism from y into x is known when you know the corresponding morphism from y into x, which I induced. And if we call this morphism here, what do I know? F. So F is known when we know that the Fi's. And when we are given a set of morphisms from the yi's into x, and if you wonder when do they come from morphism f of y into x, then the answer is that this is so if and only if the restriction of fi to yi intersects yj is the same as the restriction of fj to yi intersects yj for every pair of indices yj. That's pretty clear, I think. So, in terms of the functor x of y defined by x, this means the following. This means that an element of x of y is known when we know the restrictions, the corresponding elements of the x of yi's, and that an element, that is, if we know the corresponding element in the product of the sets x of yi's, and that an element in this product of sets comes from x of y, if and only if the two evident images that we have in the twofold product of x of yij is just intersection, are the same. That means that this diagram here should be exact whenever we have a covering of y by open subsets. Now, this condition you recognize the typical shape of the condition for a functor, let's say on open subsets of a topological space, to be a sheaf. In fact, this condition means exactly that the functor u goes to x of u, which is a restriction of the functor x to open subsets of y, that u goes to all open subsets of y, let OY be the category of open subsets, O lower y, let's say, that this functor is a sheaf for the given topology of y, of y, but as coverings we take, as covering families we take the covering families in the usual sense. Now we will say that the functor going from schemes over K to sets is a sheaf for the Zariski topology if this condition is satisfied for every y, namely if for every scheme y, if you look at the variable open set u in y, and if you look at the induced pre-sheaf by x, u goes to x of u if this is an effective sheaf. So this condition is for every y, this condition can be expressed by saying that x is a sheaf for Zariski topology. So this suggests that there is such a thing as a Zariski topology somewhere on something bigger than just a particular space. And in fact, this terminology makes perfectly good sense in the language of sites and topoi, which I have described, but those who have not in the course on little course on topoi, those who have not attended, I don't think it is. That this will prevent them from understanding, but I make just a comment that if we take on the category of all schemes over K, if we consider a family to be covering, if the Yi is a family of morphisms within this category, Yi goes to Y is covering, when the Yi's are, that Y goes to Y are open inversions, namely this for I can be identified to open subsets of Y with inclusion map, in the sheaf of rings of Yi being induced by the sheaf of rings on Y. And when the Yi's cover Y in the set theoretical sense, then this notion of covering morphisms satisfies the condition ABC of a topology on a category of a site, not the last condition of saturation. It's not yet saturated. And it's clear that if we call this topology the Zariski topology, then the topology I just introduced, X is a sheaf for the Zariski topology, which means exactly this, means also that X, as a pre-sheaf on our side, is in fact a sheaf for this particular topology, which we call the Zariski topology, on the category of all schemes over K. All right. Therefore, now this makes a sense. Whatever the functor x you see, x need not be representable by a scheme over K. And what I have just shown is that the functor, if the functor is representable, then it is a sheaf. Now let's designate by SCH tilde the subcategory of the category SCH lower k head of all functors from K schemes to sets, which are formed only by those complement functors that are sheaves that satisfy this particular exactness condition. Now we can consider the same condition when the argument y, instead of going over all schemes, goes only over the category of affine schemes. In this case, in our covering of y by open subsets yi, I will assume that the yi's are affine schemes. Then it turns out that the intersections are again affine. If they were not, we would replace every yij by a covering of yij by affine schemes again. And we could still express our exactness condition without using in effect then the section of two affine open subscripts again affine. So in this case, we get a subcategory of the category of all functors, complement functors going from affine schemes to sets, namely the category of those functors that are sheaves on the category of all affine schemes. So for this, aff lower k tilde. And our functor here, which embeds schemes over S into functors from affine schemes over K into sets, can be obtained also by composing this way around. A scheme over S defines a sheaf on the category of all schemes over K by taking the functor tripotence, which turns out to be a sheaf. This by restriction to the subcategory of all affine schemes over K defines a sheaf over the category of affine schemes over K, which is included as a subcategory, full subcategory, the category of all functors from affine schemes over K to sets. Now, the different inclusion signs which I have written down here just mean that the functors considered are fully faithful, let's say, up to equivalence, that they are full embeddings of full subcategories. Now, this arrow here I have said is not a full embedding, but what will be more or less evident is that this one here is again a full embedding. Namely, if to every sheaf on the category of all K schemes I associate its restriction to just affine K schemes, then I would get a fully faithful functor. Or, intuitively speaking, that a sheaf on the category of all affine schemes, of all schemes over K, can be reconstructed when I know its values, just on affine schemes. Now this is pretty evident. Let's not give the formal proof, you see. but let's just give, which would be easy enough, it would be very straightforward, but let's just give it the idea. I want to show that if we have x, a functor going from schemes over K to sets, congruent functor, which turns out to be a sheaf, which has this exact property I stated, so which is in here, that we can reconstruct this functor, namely its values for any y, when we know its values for an affine y. All right, any y is covered by affines yi, and x of y, therefore, can be viewed as being a subset of the product of the x, y, i's, which I already know. Now, which subset? All right, it's a subset, which is a kernel of this arrow of maps, of this double arrow of maps into the product of the x, y, I, j's. If by chance I know already that the y, I, j's are affine, then I'm through. If they are not, then I cover every y, I, j by affine open sets y, I, j, k, which is possible because y, I, j again is a scheme. You see, there's one point, yeah, I should perhaps make clear that if x is a scheme, then every point not only has one neighborhood which is an affine scheme, but also it follows that every point has a fundamental system of neighborhoods which are affine, because this is true in the case of an affine scheme, because the open subsets xf of an affine scheme x make up a basis of the topology. Therefore, the intersection of open subsets of a scheme, in fact, any open subset of a scheme, let's say, for the induced structure, is again a scheme. All right. So the yij being a scheme can be covered by affine schemes yijk, and therefore x of yij is contained in the product over all k's of the x, yij k's. And therefore, this twofold product is contained in this threefold product over all indices yj and k of x of yijk. And therefore, if you take the compositum arrows here, we see that this diagram is exact, namely x of y can be reconstructed from knowing this double arrow. In other words, if I look at the diagram yijk goes into yi and goes into yj for every set pair of indices y and j, which goes into y, x transforms this diagram into a, or let's say without, how can I say, yes, x is a functor that has a property of transforming this diagram into an x of y, which is the inverse limit of the transform of x by x of this diagram here. X is constant transformed like system into an inverse system. So x of y is known when we know x of y prime for every y prime which is affine. And all right, I mean, when we work out this argument for the Holmes, what we see in fact is that this functor is fully faithful. And now the functor which goes from schemes over k to congruent functors from affine k schemes to sets is therefore the compositum of this and this functor, which are fully faithful. Therefore, it's fully faithful. Which means that a scheme can be reconstructed up to canonical isomorphism, which implies that a scheme can be constructed up to canonical isomorphism when we know the corresponding functor here. But this functor can also be interpreted, if you prefer, as a covariant functor going from k algebras to sets. So schemes over k can be interpreted as particular functors going from k algebras to sets. And as I already said, the value of this functor on a k algebra k prime is called the set of points of the scheme x is coefficient in k prime. If you want to kind of drop the k to reintroduce it later, what we can say is the following, that the scheme over k is first of all a scheme, namely a functor going from commutative rings to sets having certain extra properties, which we call X is a scheme. We identify schemes to particular functors on the category of just commutative rings, namely Z algebras. And moreover, we should give a morphism from X into S equals spec K. Now, in this interpretation, interpreting schemes as functors, S is just Z covariant functors on rings represented by K. And to give such an arrow is just to give a morphism from the functor X into the covariant functor represented by K. Now, of course, the next question that arises is to see which are the functors going from, let's say, K algebras or Z algebras, whichever point of view we adopt, to sets that are representable. Maybe we can find a characterization which doesn't make use of any of this notion of topological space and ring topological space, locally ring topological space, morphism of locally ring topological spaces, etc. So it's kind of an involved construction. So we are going to find such a characterization which is very close to a tautological characterization. So I mean, it's not well. There are much more deeper theorems which give a non-tautological characterization of these functors more or less. But here we are going to give something which is pretty tautological, which however gives, I mean, all existence theorems of schemes which are really trivial. But before doing so, we should perhaps expand a little bit on this interpretation of schemes in terms of sheaves. I said that I interpret schemes in terms of functors, complement functors from schemes to sets, or complement functors from affine schemes to sets, or covariant functors from algebras to sets. But here it's quite important to, from this point on, to interpret these functors not as just mere functors, or as we would say, free sheaves on the categories involved, but as being sheaves. So throughout, we are working in the category of sheaves on the categories considered, so sheaves on the category of K-schemes or sheaves on the category of affine K-schemes. That is, functors satisfying certain exactness property. And a number of constructions that we will perform on schemes will have initial interpretation in terms not of the category of all functors, but in the category of those functors which are sheaves. So let's give an example or two. Let's look, for instance, at the sum of schemes. Let xi, I going through an index set capital I, be a family of schemes. Then I claim that the sum of these schemes exists in the category of all schemes. In fact, it exists even in the sum in the category of all locally linked spaces. And what we do is to take the disjoint union of the xi's with the sum topology. So we take the sum of the topological spaces xi. So each of the xi's can be identified to an open subset of the space X, which we have just constructed, these open subsets having for union X and being multiply disjoint, and having the induced topology. And on the other hand, as we have a sheaf of rings, of K algebras if you prefer, on each of these on each of these xi's, this defines us in a unique way a sheaf of rings on OX which restricts to the xi's. And now I claim that this X is, of course, we have the inclusions from the xi to X, which is the morphism of locally linked spaces, and I claim that X is the sum of the xi's in the category of all locally linked spaces. Also, it is a sum in the category of all linked spaces, because if Y is a linked space or a local linked space, and now it is a structure sheaf OY, then to give a first of all, to give a continuous map from X and to Y is the same thing as to give continuous map from each of the xi's into y. That's pretty evident. On the other hand, to give a homomorphism of the sheaf of rings OY into the sheaf of rings OX on X compatible with a given continuous map is the same thing, essentially, as to give a bunch of homomorphisms of OY to each of the OXI's compatible with these homomorphisms. That's also trivial in terms of general nonsense on sheaves. And it's also immediate that the morphism of ring spaces here is the morphism of local ring spaces, if and only if the same is true in here. You got something that is checked for every point of X. A point of X is in this one of the xi's, and some condition that the homomorphism on the stalks here should be a local homomorphism. Here's a y. Just means the same thing when X is replaced by xi, where xi is a unique component that contains small x. All right. And moreover, it turns out that this solution of the universal problem concerning sums within the category of all ring spaces or within the category of all local ring spaces is already a scheme. Because, X can be covered by open sets xi, each of which perhaps is not affine, but each of which can in turn be covered by open sets which are affine. Therefore, X itself can be covered by open sets that are affine. And therefore, this X, which is a scheme, is the sum of the xi's in the category of schemes. Alright? Now, what about the functors? Of course, if the xi's lie over scheme S, then the sum in the category of all schemes over S or in the category of all schemes is the same. S may be a spectrum of offering K, so that we are working with K schemes. Now, in terms of functors on the category of schemes S prime over S, associating to every S prime from S prime X. That's for X, and it's the same for the xi's. Each xi is identified with a functor. S prime goes to home lower S prime xi. And because xi is mapped into X, therefore this functor is mapped into this for every I, and therefore the direct sum of those functors is mapped into this functor here. Now is this bijective, and we are just speaking of functors. So this would mean this question is the following: if you have a scheme S prime over S, does it amount to the same to give a morphism from S prime into X? Or let's say this means the following: does every morphism from S prime into X factor in a unique way so a morphism of S prime into one of the xi's? That's what it would mean. Does every morphism from an every S morphism from a scheme S prime over S into X factor in a unique way so one of the xi's? Well, of course not. For instance, if you take S prime to be X and this here to be an identity, let's say, well, the identity map of X into X will not factor through one of the xi's, except if all the xi's are empty with the exception of one. So that's not what is true. What is true is that to give a morphism from S prime into X amounts to the same. Let's assume first we have such a morphism from S prime into X, call it F if you want. Then the inverse images of the xi are open subset S prime I and S prime. And S prime will be the disjoint union of the S prime i's. Alright, and on the other hand, F induces for every I a morphism of S prime I into xi. Therefore, if you have a morphism from S prime into X, then S prime will be decomposed into a direct sum of some open subsets S prime I, and for every S prime I we will have a morphism from S prime I into xi. And of course then F can be reconstructed as being the direct sum of these morphisms from the S prime i's into xi. So to give a morphism from S prime into X is the same thing as to give a decomposition of S prime into disjoint open subsets indexed by the same set of indices or in categorical terms, to give a decomposition of S prime as a sum object of a system of object S prime I indexed by the same set of indices, plus a morphism from each of the S prime i's into the corresponding xi. So that wouldn't be the sum functor, that would be something different. However, when we take things in the category of sheaves here, in the category of sheaves SCH over S tilde, then the arrow which we get here is bijective. Taking sums, in other terms, I claim that taking sums of schemes in the categorical sense within the category of schemes is compatible with taking sums of the associated sheaves they represent. Now, this is a pretty trivial exercise to check. What does it mean? Call these, now let's write, for instance, xi tilde and x tilde, if you want, for the sheaves associated to xi and x. For the time being, as we want to identify the schemes to the sheaves before having proved our statement. Otherwise, we would the terminology would be kind of awkward. All right. So we have these morphisms here. We want to prove that x tilde through this family of morphisms is the sum of the xi tildes. This means three things, in fact, when we are working in the category of sheaves. It means, first, that these morphisms, call them alpha I tilde if you want, which they correspond to the morphisms alpha I here, that the alpha i's are monomorphisms. Now that's pretty clear, because we have an open subset here. And second, it means that if we take the fiber product of xi tilde times xj tilde over x tilde for I different from j, we get the initial sheaf, which we call the empty sheaf, or it's empty tilde. And third, it means that the xi tildes cover x tilde, namely that x tilde is the largest subsheaf of itself, which contains the subsheaves xi tilde. All right, what about B here? Well, the fibered product of sheaves associated to objects commutes, of course, with is obtained by taking the fibered product of xi and xj over x and taking the sheaf associated to it. In order to make a sense out of this, we need not know that the fibered products exist in the category yet. We only have to know that the fibered product of xi and xj over x exists in the category. And it's clear that if you have a morphism of the scheme S into X that factors both through Xi and Xj, well, it has to factor through the intersection of the two, which is the empty set. Therefore, the fibered product of these two is in fact the empty sheaf, is the empty scheme, the empty space, I should have said, with the unique sheaf of rings on it as a scheme, because the condition on a scheme is empty. Every point has a neighborhood such that there is no point. All right, and therefore we find that this fibered product here is indeed the sheaf associated to the empty scheme, and it's pretty clear that that's also the empty sheaf. All right, I mean one just checks it. The empty sheaf is the one which associates to every scheme the empty set, except if the scheme is empty, in which case it associates to it the set with just one element. So that's in fact this is actually the sheaf represented by the empty scheme. So that's all right. And last of all, what does it mean that the xi tildes cover x tilde? Well, maybe I can erase this. More generally, let's take the situation of F, a sheaf, going, let's say, from the category of all schemes over K to the category of sets. Instead of this, we can also take the category of all affine or all schemes over S. We can also take the category of all affine schemes that lie over S and take a factor to sets, which is a sheaf. There's two categories of sheaves here or of sheaves there. In fact, I wrote down that it's fully faithful. In fact, it's an equivalence of categories. That's essentially the comparison lemma. It's the same lemma which says that sheaves on topological space are the same thing when we don't change, when we replace this head of all open subsets of the space by basis. On that category, that's essentially equivalent. And assume that you have subsheaves Fi. What does it mean that these subsheaves cover F? That F is the supremum of the Fi's. In the category SCH over S tilde, or equivalently in the category F over S tilde. By definition, this means that the family of inclusion morphisms from Fi into F is an epimorphism. So let's say more generally, if you have any morphism from B into F, when is this morphism covering? When is this an epimorphism? So we will apply this to the direct sum of the Fi's mapped to F. Then in order to know what it means that Fi goes to F is covering. So that's what does it mean if G is another sheaf. What does it mean that such a morphism is covering? That means the following, that is an epimorphism. If it was in the category of all functors, this would mean that it's an epimorphism argument by argument. This would mean that for every S prime in the category, every scheme S prime over S, or every affine scheme lying over S, the map which goes from GS prime to FS prime to an epimorphism. So this would be the criterion if we are working in the category of all functors, not in the category of sheaves. But what if you're working in the category of sheaves? Then it's a smaller, then it's a bigger condition, namely not that every element of F of S prime can be lifted to G of S prime, but that every element of F of S prime can be lifted locally to G of S prime. For every S prime, so we have a map like this, and for every element phi, let's say, in F of S prime, there exists a covering of S prime by open subset S prime I, such that therefore there exist such open subsets such that the union of them should be equal to S prime. And for every I, index I, there exists psi in G of Si, S prime I, I'm sorry, such that the restriction of psi to then such that, I'm sorry, I could give a name to this morphism, U, such that the image of psi, which is an element therefore of F of S prime I, should be equal to the restriction of phi S prime I. So every point of F as well as in S prime should belong perhaps not to the image of GS prime, but should locally belong to the image. While we replace S prime by sufficiently small open subsets covering S prime, this condition should become true. And therefore, if we now revolve to the situation when we have subsheaves fi of f, when will the fi's cover f? If we had it in terms of, if we said they cover them in the sense of pre-sheaves instead of in the category of all functors, this would just mean that if you look at the maps from fis prime to fs prime for a given s prime in the category, that this would mean that every object in here comes from is contained in one of these subsets fi of s prime. But now we have to weaken this condition because we are working with epimorphic families of sheaves, and we have to weaken it into saying that every element in here comes locally from one of the fis primes. Namely, for every phi in fs prime there exists a covering of s prime over open subsets, and for every I there exists, no, now I will say it differently, is such, it's not the same I's here, so let's call them rather alpha c, the indexing, the indices for this covering. And for every alpha, there should exist an index I of alpha depending on alpha, such that the restriction of phi to S prime alpha should belong to the subset f I of S prime alpha. That's the condition. These two conditions we can also express in terms of usual sheaves, let's say, on usual topological spaces by saying the following thing. If F is a sheaf on the category of all schemes over S, or on the category of all schemes over S that are affine, then for every S prime in the category here or there, if we look at the variable open set U and S prime, then U goes to F of U is a sheaf in the ordinary sense on S prime. For this functor, F lower S prime, it's a restriction of the functor F to open subsets of S prime. So the F of S prime should be sheaves. Now, of course, if we have a homomorphism of functors here, it defines your homomorphism of the restrictions to open subset of S prime, whatever S prime, so we get a homomorphism from GS prime into FS prime. If FFG are in fact sheaves, then FS prime and GS prime are sheaves on the topological space S prime in the usual sense. And to say that this homomorphism of sheaves, that is an epimorphism of sheaves, means that for every S prime, this homomorphism of sheaves in the usual sense on S prime is an epimorphism of sheaves on S prime for the Zariski topology of S prime. And the same thing here. To say that the Fi's cover F, subsheaf of F, means that for every S prime, if you look at the subsheaves I lower S prime of Fs prime, these subsheaves should cover Fs prime. I'm just making some gymnastics with terminologies. There's really practically no real mathematics, no mysteries, nothing involved here. It's just. And now I come back to the situation of sums. I claim that if we take schemes xi and the scheme x, which is the sum of the xi's, that then the sheaf x tilde represented by x is the sum of the sheaves xi tilde. I already proved the two first characteristic properties of a sum of sheaves, and now I have to prove the last, namely that the xi tildes cover x tilde. That means that for every S prime scheme over S, and every element of x for S prime, that means for every morphism from S prime into x, we can cover S prime by open subsets, such that the morphism, call them S prime alpha if you want, such that the induced morphism S prime alpha into x factors through one of the xi's. But what we do, we take for S prime alpha the inverse image is S prime I of the xi's. They cover even in a disjoint way. We don't need that much. So the embedding of the category of schemes in the category into a category of sheaves, therefore, is compatible with taking sums. Of course, it is compatible with taking more generally the last argument which I made showed the following: if X is a scheme, and if UIs are open subsets of the scheme X, they were the XIs just a minute ago, and if I consider the union of the UIs, which is just the supremum of the UIs within the category of all open subsets of X, that then the sheaf represented by U is just the supremum of the subsheaves UI tilde within X tilde. The same thing. This just means that if we have an morphism, if U is this union, we have just to prove that if you have a morphism from S prime into U, then S prime can be covered by open subset S prime alpha, such that each of the induced morphisms factors through one of the UIs, and I will just take a set of indices the same as the set of indices here. I will take the i's, and S prime I will take the inverse image by the given morphism of UI. And because the UI cover U sets-retically, the S prime I cover S prime sets-retically. So here these things work quite satisfactorily, provided we are working not in the category of all functors on schemes over K or on algebras over K, but in the category of sheaves. So you see how important it is to work with sheaves now rather than with functors in some context. Essential contexts which involve not only inverse limits, but which may also involve at the same time some types of like limits, like taking suprema, speaking of epimorphisms, or taking direct sums. This is clear.
That's a question.
Yes.
The map you define from the sum of home S prime to Xi prime. You dropped it up.
Let's see. As there was a morphism from
You had S prime going to
S, I guess.
going to the sum of the final sum over home S prime Xi.
From S.
Xi.
Yes.
And then you said it wasn't by get to.
From this
Yeah.
into home as X.
Yes.
Yes. In other words, that if you have a morphism from S into X, it does not factor in general through one of the Xi's.
So look at what you did. Does it factor in the case of sheaves if we restrict to the category of sheaves?
It factors locally, that's the point. It doesn't focus. I mean, the embedding of sheaves and pre-sheaves is a fully faithful functor, so it doesn't factor either. I mean, it doesn't factor. I mean, to give a morphism from S into X is the same thing as to give a morphism from S tilde into X tilde, and the same for these arrows here. So to find a global factorization is the same whether we speak of schemes, whether we speak of sheaves, or whether we speak of pre-sheaves. I mean, the arrows, the set of homomorphisms of one of these things into the other, are just the same under these 3 points of view. But the criterion for which we are looking for is not that it factors for the here in terms of sheaves, but that it factors locally over S. I mean, when we speak of sheaves, that means that we have introduced again the topological element of that we are considering properties that may be true only locally instead of being true globally. You see. That is, what is true is that any morphism from S into X doesn't factor through the xi's, but at the neighborhood, if you prefer to say it this way, for every point of x of S exists the neighborhood of it, call it S lower x, let's say. So the indexing set would be now the set of points of S if you like it, such that the induced map here factors through one of the xi's, but this I will depend on the choice of x. And I mean, the universal example or counterexample, if you want, is when you take S to be X itself, and the identity from X into X does not factor through one of the components. It does only if one of the xi's covers already X. And this implies that the others, xj's, must be empty. So let's recall that when you look at the inclusion of sheaves into pre-sheaves, so whether you're working with sheaves of the category of schemes over K, or they're working with sheaves in the category of sheaves on the category of affine schemes over K, doesn't make a big difference here. These two anyhow equivalent. The inclusion which goes from sheaves to pre-sheaves, sheaves being particular cases of pre-sheaves, of just functors, in here and there, this inclusion is compatible with taking inverse limits. This comes from the fact that if we have functors fi depending on an index I and forming a certain diagram, if the fi's are sheaves, then the inverse limit of the fi's corresponding to this diagram are necessarily sheaves, because we have exactness conditions, which are left exactness conditions on a pre-sheaf to make it to turn it into a sheaf. And these are stable under taking inverse limits. For instance, a product of sheaves is again a sheaf. A fibered product of two sheaves over a third is again a sheaf. And therefore, when we take this product or fibered product, or more generally this inverse limit, if we view it as being an object of the category of sheaves, this object will be an inverse limit inside of the category of sheaves also. So the inclusion from sheaves into pre-sheaves is compatible with arbitrary types of inverse limits. Whereas it will not be compatible with, in general, with any type of Dirac limit. But in fact, it's the Dirac limits constructed in here that are interesting, not those which are constructed in here, which are mostly much too strong conditions, for instance, for something to be a sum of objects. I mean, the condition here is just too strong. This condition here is a good one. Let's turn the exercise over in a slightly different way. Assume that we have sheaves fi, so objects in here, objects in there, that amount to the same. And a family of sheaves, and look at the direct sum of these sheaves. Call it F. So it's the direct sum in the category of sheaves. Now, what's the description of the functor? So it's not the direct sum of the functors. It's something a little more subtle. So you should say, what is it? An element of f of s in terms of the fi's of s. So that's a little exercise we are going to deal with. A little exercise in the language of sheaves. All right. F of s we can just view as being hom of s, hom, I'm sorry, s was already the ground scheme which was fixed once for all, so let's call it rather s prime then. It's the set of homomorphisms of s prime into f in the category of free sheaves. Because to give a morphism of a representable functor into a functor is the same thing as to give an element of f being the functor of s prime. So we can interpret f of s prime as this form. I mean, we did this a number of times already, I think. To take the norms in the getter of all sheaves or in the getter of free sheaves is the same, because sheaves are just full subcategory. It turns out that we know already that the function called by s prime, let's call it rather s prime tilde in order. Maybe that will make it clear that this is, we know already that this is a sheaf. So both here are sheaves. Alright. Now, what is it? A morphism of s prime tilde of the sheaf s prime tilde into the sheaf sum of the fi's. This corresponds just to subsheaves s prime tilde I with an s prime tilde, so that the s prime tilde will be the sum of those subsheaves, and in such a way, in the system of morphisms of these subsheaves into their fi's. So in terms of general sheaf theory, that's how we get a morphism from a sheaf into a direct sum of sheaves. Now the exercise, which I think I won't do because I think you should go a little further, but I recommend it to you to read at home if you are not at ease with this terminology. The exercise would be the following: to show that the decomposition of the sheaf s prime tilde into a sum of sheaves is the same thing as the decomposition of s prime into the sum of open subsets as a sum of objects within the category of schemes. Of course, we have already seen that if s prime is decomposed as a sum, then s prime tilde is decomposed as a sum of the s prime I tildes. Well, the converse is true. We get in this way all decompositions of s prime, of s tilde. I propose this in exercise. And when we admit this point, then we see that to give the morphism from this into fi is the same thing as to give elements of fi of si. Therefore, a point of f with coefficient in s prime, an element of fs prime, is the same thing as a decomposition of s prime into a sum of schemes s prime I, indexed by the same set, capital I, as the one that appeared in here, and for every index I, an element of alpha I of fi of si. And this, of course, there is contrary for if s prime, I'm sorry, it's s prime I, if s prime varies, or this set of data associated to a given s prime. Now, I wonder, is this kind of clear or kind of abstract? Or do you think? It's all right?
Exercise again. You state the exercise again.
Yes. The exercise is the following. Let S be a scheme. S prime be a scheme over another S, but in fact the S is irrelevant extra data. And let an isomorphism being given between S prime tilde and the sum of sheaves Fi. So I assume that the sheaf S prime tilde represented by S prime in the case of all schemes over S has been decomposed as a direct sum. These possible decompositions, in fact, they correspond to a nice Pine order of the sheaf S prime tilde. I mean, you can say something. It's just intuitively it looks like a set that is decomposed into disjoint, into the sum of mutually disjoint sets. All right. So that such an isomorphism is given, so that the sheaves Fi can be viewed as being subsheaves of S prime tilde that are mutually disjoint, namely their mutual intersections are the empty subsheaf, and such that the supremum of the Fi's is equal to S prime tilde itself. So Fi intersects Fj is the empty subsheaf, and the sup of the Fi's is equal to the whole of the S prime I. So that's what it means, that S prime tilde has been given as a sum. So that's the data, and the conclusion is, these are the assumptions. The conclusion is, for every I, there exists an open subset S prime I in S prime, open, such that Fi is equal to S prime I tilde. It's clear that this open subset is uniquely determined, by the way, and moreover, that's really important, that's really the key step. All the rest is now an immediate conclusion. Moreover, S prime is just the disjoint union of these open subsets. Therefore, the decomposition of S prime tilde into a sum of sheaves corresponds to a decomposition of S prime into a sum of sheaves. And in fact, this exercise will be a consequence of a series that I'm going to say now about open inversions of sheaves, which we will need in order to give our characterization of those sheaves that are schemes, that are represented by schemes. But before going further, I should perhaps formulate the sheaf property of a functor in terms of quantitative algebra. So far, if X was a scheme over S, so I associated to this a functor X of K prime on the category of all rings lying over S to the category of sets, and all rings K prime to spectrumlize over S into the category of sets. But I did it by the arrow reversing, by associating, in fact, by taking schemes S prime over S that turn out, that happen to be affine, and taking the functor S prime goes to XS prime, which is contrariant, with home over S of S prime X, and having a contrariant functor from these S primes to sets amounts to the same as to have a covariant functor from the K primes to sets. All right. And in order to express the sheaf property of our functor, what I did was to express it in geometric terms, not in terms of ring theory, by saying that whenever S prime is covered by open subsets S prime I, then we have an exact diagram F S prime product of the F S prime I double product of the F S prime I intersects S prime J. Now, open subsets of S prime, I mean, they make not such a nice immediate sense in terms of the ring, except through the spectrum, but I mean this is a little long. And of course what we could say is that we can restrict to covering of S prime by affine open subsets. And it's easy to see that the two properties are equivalent because the affine open subsets of S prime, they contain, for instance, the subset of the type S prime F, they make up the base of the topology. So in fact, we could express the property in terms of affine subschemes alone, which in fact we have to do if S prime is restricted to be if you want to express the whole thing in terms of functors on the category of S primes which are affine. Then I will have to restrict here to S prime i's that are affine, and I will have to use the effect, which is unpleasant, because we would first have to prove it, that the intersections of the S prime I and S prime j is also affine. Otherwise I will have to cover it by S prime ij, each of these open sets by affines. And again it becomes more intricate. But in fact, we can go further. We say that it's enough to consider coverings of S prime by affines. But in fact, we know certain types of affines that form a basis of the topology of S prime. Namely, the affine sets of the open subset of the type S prime F, where F is an element of A prime, the ring of the affine scheme S prime. And we know what it means that if now we have various elements Fi and A prime, so that we have open subset S prime, lower F prime in S prime, we know what it means to say that S prime is covered by the S prime Fi's. S prime equals union of the S prime Fi's, if and only if, that's just a reminder, the ideal generated by the Fi's is unit ideal. Namely, if there exists a linear combination of the Fi's which that is equal to 1. This we have used several times. And now, the condition that F is a sheaf, F now a functor on S algebras phi da say on these rings K prime, or call it an A prime if you want. Now it becomes the following. Means that for every such ring, but A prime instead of K prime looks a little small. One thinks of a field of so. And for elements Fi and A prime, generating the unit ideal such that sigma Fi A prime is equal to A prime, the diagram F of A goes into the product of F applied to the localized rings AFI, goes into the double product of F applied to A localized with respect to the product Fi Fj should be exact. Now this here makes a perfectly good sense without speaking at all about spectra, about ring spaces and the like, just speaking about functors going from rings to sets. And that's the sheaf property we are interested in. And when we have such a functor going from rings over S into sets, then a sheaf, then this functor extends in a canonical way up to unique isomorphism into a functor going from SCHS to sets which are sheaves, because sheaves on this big category or sheaves on the smaller category consisting of affine objects are essentially the same things. But here, once again, this property is independent of any constellation of topological spaces or such funny things. Sheaves of rings, which is kind of involved notion. And what we would like to do is to give a characterization of those sheaves that are represented by schemes in terms of commutative algebra. This would mean that we have reconstructed then the character of schemes without speaking of topological spaces and the like, just in terms of functors on the vector of planes. In fact, functors that have some extra property. Assume S to be affine, for instance. Assume S to be the spectrum of K. So that our category we are working with here, the category of rings over S is just the category of K algebra. So everything is expressed in a purely algebraic way. The most important case being K equals Z, being a ring of integers. So I thought I would do this today, but doesn't seem I will. Because it's 3, and I think I have to go on with groups, unless you think it's better that I go on to get through with this general setup. I could next hour and a half I could go on speaking about this. I don't mind if it's the same. What are there any patterns? You think it's better to go on? All right. So let's say we make a break of 10 minutes and then we go on with this. So I'm going to define the notion of open immersion of sheaves. So the context is again that I fix myself a scheme S, which might be an affine scheme, for instance, the spectrum of ring K. And I'm looking at the category of our schemes over S and the category of functors, conjoint functors on this to sets that are sheaves. So that's the category STH over S tilde, which is equivalent to the category of affine schemes lying over S tilde, the category of conjoint functors on affine schemes lying over S that satisfy the sheaf property, and we have described this, in fact, at least when S was the spectrum of the ring K in terms of commutative algebra. Or if S is viewed as being a function of the cache of all rings, let's say, then we have to describe it in terms of commutative algebra too, because it's never mind. Alright. Now let F goes into G, be a morphism in this category, which may interpret either like this or like that category. And I will describe what it means that it is an open immersion. And what I'm thinking of as a model of an open immersion is an open immersion of schemes. Namely of a scheme and an open subset of the scheme induced endowed with induced topology and the induced sheaf of rings. And of course, if we have a scheme X and an open subset U of X, then U tilde, the sheaf represented by U, is contained in the sheaf represented by X, and this inclusion I will take as being the model of open immersions. Now I will generalize this to a case of a morphism of sheaves. I will define when a morphism of sheaves is an open immersion. will imply, for instance, the axioms that I'm going to state, properties, that this is a monomorph, that F can be viewed as being a subsheaf of G. So, let's say, well, we will distinguish two cases, first a particular case and then a general case. No, let's go at least, let's do it at once with the general thing. That means, by definition, this is said to be an open immersion if and only if, for every morphism of a scheme S prime over S into G. Now, schemes over S I identify to the sheaves they represent. And to get a morphism from S prime into G, call this U if you want, is the same thing as to give an element of G of S prime. Right? When I take the fibered product of F and S prime over G, so called here the fibered product F lower S prime. F is viewed as being a sheaf over G, and I pull it back to a sheaf over S prime. Then I want that this here, Fs prime goes to S prime, should be an open immersion in the sense of our models here, namely that Fs prime should be isomorphic, that this inclusion should be the inclusion of an open subset of S prime. So if you feel better, maybe for the time being, if we distinguish between schemes and the sheaves they represent, and let's put a tilde over it, then this would mean that Fs prime is just as a sheaf lying over S prime tilde should be isomorphic to U prime tilde, where U prime is an open subset of S prime, which will be endowed with induced topology and induced sheaf of rings. Now, all right, so that's the definition. In fact, I should say that this type of definition is very frequent when we have a category like the category of schemes over S, or a category of affine schemes lying over S. And if we are looking at the category of sheaves on this category, like here, if you have already a certain notion of morphism, open immersion or homomorphism or whatever, in this category we are starting with, the category SCH, S, let's say, or the mean of all affine schemes lying over S. Then we extend it to a property, to a class of morphisms within the category of sheaves by saying that F goes into G has this property. If I have a base change here with a representable sheaf here, the inverse image of this arrow by this base change is an arrow within our basic category we started with, which has a property we said. Which has a property we started with within here. So this would make a good sense, provided the property we started with is stable under base change itself. It would make a sense otherwise too, but not a very good one. Wouldn't have good properties. So let's check that this is so for the notion of open immersion. So let's show that if we have a morphism of schemes over S, which is an open immersion, so which corresponds to S prime and an open subset U of S prime, and if we have a morphism from S secondary to S prime in the category of schemes over S, and if you look at the inverse image, let's rather call U prime perhaps the open subset. That's what I did here. Yes, and if you look at the inverse image of this open subset U prime, which will be an open subset U second and S second, if we endow this with induced topology and with the induced sheaf of rings, that then this square is Cartesian in the category of all schemes, namely that u second is the fiber product of u prime and s second over s prime. Well, that's kind of evident. In fact, it's the fiber product in the category of all locally ringed spaces, or if you want, in the category of all ringed spaces. Because what does it mean? It means that if you have any, let's say, local ringed spaces, because we are really interested in local ringed spaces, X, and if you have a morphism from this into S second into U prime such that this square here commutes, that means that the composition X goes to S second goes to S prime factors through U prime. Namely, that's just a set theoretical property, namely that this map set theoretically factors through the subset U prime of S prime. That then there exists a unique way of lifting this set of maps into morphism from X into U second, so that this here is this composition and this here is this composition. But that's pretty clear, because what does it mean that this composition here factors through U prime? That means that this morphism factors through the inverse image of U prime, namely through U second. Now this turns out to be open in S second, and if it factors through U second, then just as before, this means that this factorizing continuous map will automatically be endowed with a morphism in the opposition between the sheaves of rings, because the sheaf of rings here is the one by definition that is induced by S second. So within the category of schemes over S, the notion of open immersion is stable under base change. And now, from this it follows formally that the notion I have described here for open immersion of sheaves is also stable under base change. In other words, if F goes to G is an open immersion, I could perhaps also say, yeah, all right. And if G prime goes to G is a base change, arrow in the category of sheaves, so that now we have a Cartesian square. It's an F prime over G prime. I want to show that this is an open immersion. Now let's apply the definition. We have to take a morphism from S prime into G prime, take the pullback of F prime into a sheaf over S prime, and view whether this here is an open immersion in the initial sense within the category of schemes. So we put this tilde here, so that this here is in fact of the type U prime tilde. where U prime is an open subset of U as S prime. But the pullback of F prime over G prime coming from this base change is just what you obtain by changing the base twice. So it's just the fiber product of F S prime tilde over G, and therefore just follows from the definition of F goes to G being open immersion. On the other hand, I claim that the composition of two open immersions is an open immersion again. And this again will follow from the same property, I guess, in the category of schemes over S. In this category, the composition of open immersions is an open immersion, which is clear. Transitivity of induced topologies of induced sheaves. Now let's try to prove this. Let's assume that F goes into G as an open immersion and G goes to H as an open immersion. And let's look at the composition, and let's show it's an open immersion. All right, let's take a base change. S prime tilde goes to H, where S prime is in the category of schemes. Now that G goes to H as an open immersion means that we have a commutative square, that we have a Cartesian square by putting in a U prime tilde here, where U prime is an open subset of S prime. That's because this here is an open immersion. Now what about this here? This being an open immersion, as I have a base change with a representable sheaf here, this means that we can find an open subset, call it, or do I know, U second and U prime, such that we have a Cartesian square like this. Now this our condition satisfied. identities, modern isomorphisms are often inversions. So this is a very handy process of extending properties of morphisms from a category to a category of sheaves on this category. And now I come to the criterion of representability of a sheaf, that's it. So the problem is the following. We have the category of schemes over S, which is embedded in the category of sheaves on the category of schemes over S, or equivalently in the category of sheaves on the category of affines over S, or equivalently the category of sheaves of covariant functors going from algebras over S, if I dare say, to sets, having this exactness property I've written down half an hour ago, which I call to be sheaves, let's say. Zariski, sheaves for Zariski topology. And I want to characterize the objects in here which are isomorphic to images of objects there. And the proposition that we get is the following. Even maybe we call it even a theorem, although it's pretty tautological, but it's very useful. That F be an object of the category of sheaves, then F is a scheme, by which I mean it's isomorphic to a sheaf coming from a scheme, it's representable. If we take things in here, it wouldn't be representable, of course. Here or there, it's represented by a scheme. It is representable by a scheme if and only if it satisfies the following two conditions. First, when F is a sheaf, we don't even have to state it. It would be if this was a functor. So if we start with a functor, not with a sheaf, then as the first condition we would have to state that it's a sheaf, but we had already assumed it. All right. Therefore, we need no longer state this exactness property, and we proceed if and only if there exist subsheaves Fi and F satisfying the following properties, indexed by a certain set capital I, not necessarily finite, I don't care, such that A, Fi goes to F is an open inversion, B, the Fi's cover F, the supremum of the subsheaves Fi is the whole of F, and third, each Fi is a scheme over S, namely is representable by a scheme over S. Now, you will say that this, we will prove it in a minute, you will say that this is not a nice characterization because with this condition C here, we seem already to assume the notion. You use already the notion of a functor represented by a sheaf. Therefore, we will have to give a corollary in order to state it in terms where where this subcategory is not as assumed to be known. And it's pretty easy because let's state the corollary. In the criterion above, we may replace C by C prime. All Fi's are representable by affines. By affine schemes, they are affine schemes over S, which would mean, if for simplicity, for instance, we assume that S is a spectrum of a ring K, so that our sheaf can be viewed as being a functor going from K algebras to sets. This just means that these functors Fi are representable functors, representable now by K algebras. All right, and now this, if we do this corollary, then the category of functors from K algebras to sets that we have described here is described essentially in a way independent of the consideration of such funny things as ring spaces, etc. Something to express in terms of quantitative algebra, except perhaps that I still have to say what this means, which is pretty immediate. What does it mean that the Fi's cover F? That means not, once again, that for every K prime, when we look at the subsets Fik prime of F of K prime, that doesn't mean that Fk prime is covered by the subsets, but it's covered locally in the sense that there exists F alphas in K prime, generating the unit ideal so we think of them as defining open sets in the spectrum, which cover the spectrum, but we don't say this, such that for every alpha, there exists an I of alpha what should I say now? Let's see. No, I have my quantificators slightly wrong, so we don't want to say that these cover F of K prime, that for every element in Fk prime, that for every element, what do we call it, A in Fk prime, this element belongs locally to one of the Fik primes, namely there exists a family of F alphas generating the unit ideal, such that for every alpha, an index I of alpha, so there exists a map, you could say, from the set of indices I, from set of indices alpha to the set of indices I, such that the image of A in F of the localized thing at F alpha is in F lower I of alpha of the same localized thing. So that's what it means that the Fi's cover F. And what does it mean that Fi goes to F is an open immersion? Here we have to be a little careful, because let's take the definition again. In this definition now, we would like to take for S prime tilde goes to F and S prime which is affine. And the definition which is stated when we took S prime to be any scheme was that there exists an open subset U prime and S prime, so that the Cartesian product here, that the fiber product here, is just U prime tilde Sn, object over S prime tilde. But this U prime, of course, may not be affine. So if you want to express things without at all going out of the cut of affine things, then we have to describe subfunctors of the functors represented by S prime on the category of algebras, let's say, which come from open subsets of the spectrum, without speaking of the spectrum. And that's pretty easy. So one can either say the following. Now we are going to express A. We can either express it well, let's forget about indices. Let's just put here a G goes into F. We are still expressing what it means that homomorphism of sheaves is an open immersion in when we're working with arguments which are restricted to being affines throughout. So we can either say that we can either use the fact that u prime tilde itself is a supremum of s prime f alpha t. G alpha G lambda tilde z. This open set, if you have any open set of this open subset of the spectrum, this open set can be written as being the union of open sets of the type S prime lower G lambda, where G lambda goes over the affine ring, where the G lambdas are elements of the affine ring A prime of S prime. And therefore, as we have seen, the sheaf associated to u prime tilde, is just the supremum of the subsheaves S prime lower G lambda tilde. Now these subsheaves can be expressed in terms of commutative algebra. Namely, the subfunctor here is just the functor represented by the quotient, by the localized K algebra K prime localized in G lambda. So that's one way of expressing a subfunctor of the functor S prime tilde, which is represented by an open subset of S prime in terms of commutative algebra. Now this is a little, perhaps slightly awkward, because we have to use the notion of supremum of subfunctors here, which I already made explicit. It means that locally every point of u prime tilde belongs to a point of this. That means also that it's a subfunctor whose points with values in some k second, let's say, are the points of S prime with values in k second, which locally belong to one of these subfunctors. Alright, but I can say things differently by noting that to give an open subset of S prime is the same thing as to give the closed complement. Namely, it's the same thing as to give, therefore, an ideal, which we may assume to be equal to its radical ideal, J in K prime. And now, in terms of an ideal J in K prime, what is a subfunctor, all right, of the functor S prime, described by S prime, namely represented by K prime? Let's first say it in terms, geometrical terms. U prime is equal to S prime minus V of J, which is contained in S prime. So, if you have a scheme T over S and an S-morphism of T into S prime, what does it mean? That it factors through U prime when T is affine, T equals the spectrum of the ring, what do I know? B, let's say, algebra B. Well, that means that the inverse, that T factors sets radically, or else that the inverse image of the closed set Vj in T is the empty subset. But this means if S prime, again, is made explicit as the spectrum of K prime, what is the inverse image of the closed set Vj in spectrum of B when I consider this morphism as stemming from homomorphism of algebras from K prime into B? This is a closed set defined by the ideal GB generated in B by J. I have J and K prime. I take the ideal GB. And what does it mean? That V of GB, you have to express now that V of JB is the empty set in T, the empty subset of T. And this just means that J of P is equal to B. That is, we give an ideal in J and K prime, and we take the subfunctor of the functor generated of the functor represented by K prime of the functor, let's say B goes to home lower K, homomorphism of K algebras of K prime to B. Within here, I consider the subset of all those homomorphisms from K prime into B such that the image, such that the ideal generated by J and B, set of all U's going from K prime to B, such that Uj B is equal to B. That's the subfunctor. And these subfunctors are one-to-one correspondence with the radical ideals in K prime. If J is generated by generators G lambda, by elements G lambda of K prime, then the description of the subfunctor is just the set of all homomorphisms of K alters of K prime into B, such that the images of the G lambdas in B generate the unit ideal. That means just that the inverse images in the spectrum. But I precisely don't want to speak of the spectrum. I want to express everything in terms of quantitative algebra. Therefore, the notion of an open immersion, I mean, makes a pretty good sense working with functors of algebras throughout. So therefore, our theorem here, in the shape of the corollary, really does give a description of the category of schemes over K in terms of pure quantitative algebra. Now I have to prove the theorem, and in the corollary, of course, the conditions stated here are necessary for F to be a scheme, because we take, for a family of things covering F, we take the family reduced to F itself. And the identity is an open, and with the identity. The identity is an open immersion, the supremum of F is F, and F is a scheme. I mean, that's tautological. So what we have to show, in fact, is the opposite. And if these conditions A, B, C are satisfied for some subsheaves Fi of F, then F is representable by a scheme. On the other hand, how will we prove that the condition is necessary here, but under this weak shape? How to prove that it's necessary under the strong shape? Then we assume that the Fi's, when we here demand that the Fi's be affine. That's pretty clear. If F is of the shape X tilde, X being a scheme, X can be covered by open subsets Xi such that each of them is affine. And now X tilde is covered, the sheaf X tilde is covered by the subsheaves Xi tilde. And the inclusions of Xi tilde into X tilde are open inclusions by construction, are open immersions. And each of the Xi tildes is an affine scheme, is represented by an affine scheme, I over S. And that's essentially the definition of schemes. So what we have really left, to prove is that F is a sheaf having subsheaves Fi satisfying the conditions A, B, C. Then F is a scheme itself, is represented by a scheme. All right. So let's see. Let's look at F. We have the Fi's in F. And therefore we have also the intersections Fi and Fj, which are also in F. And in fact, and I claim that each of the inclusions Fi and Fj goes into Fi is an open immersion. This comes from the fact that it's reduced from Fi goes to F, which is an open immersion. I'm sorry, from Fj goes to F, which is an open immersion, by the base change Fi goes to F. All right. Now all of these Fi's, they can be written as Xi tildes, where Xi is a scheme. That's the assumption. C, we have already used A. That's the Fi goes to Fi, open immersions. Now, this here is an open subsheaf of Fi, and therefore it corresponds to an open subset of Xij, because now Fi is itself implementable. Therefore, this can be viewed as coming from an open subset, Xij in Xi. Here the order in which we take the indices I and j is and does make a difference. Xij is an open subset of Xi, not of Xj. Alright, so what we have is a bunch of topological spaces Xi, together with shield of local lengths on them. They are in fact schemes. And for every set of indices ij in this order, we have an open subset xij of xi. Moreover, if you look at what happens if you reverse the order of I and j, then we have an open subset xji of xj. And moreover, we have an isomorphism, canonical isomorphism between these two. Because the tilde of this and the tilde of this, they are both isomorphic to the intersection of fi and fj. And an isomorphism between the tildes comes from an isomorphism between the objects, because the functor something goes to something tilde is fully faithful. Alright. So we have essentially what is needed in order to stick together topological spaces xi, the xi's by the common open subset xij's in xi and in xj, by identifying xij and xji, except that we have to satisfy a transitivity relation between these isomorphisms, which is a relation in terms of triple indices ijk. Maybe what we have to prove is the following, that if you have three indices ijk, now let's look at the open subset xik and xi. There's xij, but there's also xik, and let's look at the intersection of these two. Call this now xijk, lies in here. Alright? And we can do the same thing here. In the xj we have xji, but we have also xjk. And the intersection of the two, they are called xjik. Alright? So what we have to check is, let's see, the fact that this isomorphism here, called this phi ij, transforms this into that, and that we have transitivity when we look at phi ij, phi jk, and phi ik restricted to xijk. Well, it's kind of messy to write down, but I mean it's a usual business when you want to match, when you want to glue together spaces of a right or whatever, endowed with geometrical objects like sheets and open local relation essentially. So we have to check that this open subset is mapped into this open subset, and that we have a certain transitivity relation that I don't want to write down. But this comes from the fact that we know already that the same is true when we put tildes over the whole story. Because there everything comes from an object in the sub-object fi. And what all we want to do is to show that the conditions here that will ensure that the xi's also come from a global object x as sub-object, and the xij's are just in the satisfied. But it's already true here. That all the transitivity conditions are true, then we put tildes over our symbols here. But because the functor tilde is going from a scheme to the sheet it represents, is fully faithful, that shows that things are right here. That means that there exists a topological space X, first of all a set if you want, but if you want to do it first separately, and in such a way that the xi's can be identified to subsets of X, and in such a way that xij should be just the intersection of xi and xj, and the isomorphism which we have here between xij and xji So it would be just identity when we make the previous identifications of xi to subset of x and xj to subset of x. And moreover, in such a way, we know also that the topology of xij is induced by the topology of xi and by the topology of xj. And therefore there exists on X a unique topology that restricts to the given topologies of the xi's. So I'm just reproving that topological spaces can be described by gluing data. Alright, now what about the sheaf of rings? We have a sheaf of rings, or K-algebras or whatever, or OS algebras, where S is the thing downstairs, which we don't speak much about. OXI on XI, OXJ on XJ. On the other hand, there are restrictions to the intersection. There's a given isomorphism between them, because here you have not only an isomorphism of topological spaces, like a homeomorphism, but an isomorphism of ring spaces over S. Alright? So we have gluing data for these sheaves of rings on the xi's. But of course, these gluing data, we don't just have the isomorphism, we have also transitivity in the threefold intersections, which is just corresponds to the transitivity relations, which I haven't written down here. Alright, so I got a sheaf of rings on X, so that for every I, xi as a ring space is induced by the structure of a ring space on X. And of course, if we didn't do it alongside, we do it now. If each of the xi's lies over S, and that the isomorphisms which we had here were ice isomorphisms, this shows that we have a morphism from X into S, because we have morphism from Xi into S that match in the intersections. So X lies over S in fact. Alright, so we have constructed, on the other hand, X is a scheme, because it's covered by open sets that are schemes. And being a scheme is a local condition. So we have constructed a scheme X over S, covered by the xi's. And the morphism from X into S, of course, the morphism of local ring space, and the morphism of schemes, because it's so on the xi's. Alright, so far we have only used A and C. Now, what I claim is that without using B as yet, I claim that this scheme X which I have constructed can be viewed as being a subsheaf of F. In fact, the subsheaf which I'm going to take is the supremum of the Fi's. So when the supremum of the Fi's is equal to F, then I will have shown that X tilde is equal to F. In other words, that F is represented by X. Now, how am I going to define this arrow from X into F? Well, I mean, in order to define an arrow, because X is covered by the open, how should I say? It's just the same thing as to give an element of Fx. And because of the sheaf property of F, let's say, it's the same thing to give elements of the F of Xi, namely to give homomorphisms of the Xi tildes into F, which mention the intersections. But these Xi tildes, they were already equal to the Fi's. So these homomorphisms, I have them already. In fact, they are inclusions. And they do match on the intersections by construction. Therefore, I do have a morphism from X tilde into F. And why is it? Well, I say that it's an open inversion. let's see. Now I guess we should be about 2. We want to prove it. Of course, as x tilde was the supremum of the x tilde I, as we have already seen, it's the upper bound of the subsheaves x I tilde. The image of x tilde in F is the upper bound of the x I tildes in F, which are just the F tildes. So it's this factors through an epimorphism through the supremum of the Fi. So we have an epimorphism here. And all we have to show is that it's an monomorphism also. Alright, why is it a monomorphism? Should be trivial. We can, I think, simultaneously that's the monomorphism. Because from the very way we have described x by the xi's, whenever we assume x which is covered by open sets xi's, then we see that x tilde getting mapped into its xi tildes, which get mapped into them the xij tildes. So we have this diagram. Right, this diagram turns x tilde into the direct limit of the diagram of the xi tildes and the xij tildes. Just look what it means. It means that for every sheaf F, the morphisms of x tilde into F are just the sets of morphisms of these into F such that, etc. It means that the element of Fx is just a set of units of the Fxi such that. Alright. But the xi tilde are just the Fi's. And here, these here are just xij tildes, are just the Fij equals Fi intersects Fj. And we do know, I mean, that's, if you want a sheaf story, whatever you want, I mean, that's pretty trivial, that if you have sub-objects Fi of a sheaf F, then the supremum of the sub-objects Fi is the direct limit of the Fi's according to this, and the Fij's according to this diagram. It means that the supremum is obtained by matching together the Fi's, if you want, according to the Fi intersects Fj, if you want to say it this way. So that proves the criterion. And we are now going to apply it in order to get the most basic elementary representability theorems in the matter of schemes. So what we want to do is to define the projective spaces as schemes, the standard non-affine schemes, to define inverse limits in the category of schemes, whichever inverse limits exist, at least the finite ones will exist within this category. And we are going to define, let's say, also the spectrum of a sheaf of algebras. A quasi-coherent sheaf of algebras, or a scheme S. So, let's see what time it is. Maybe we won't have time to deal with all these examples, so what should I treat first? I think they're logically independent. A, alright, projective spaces. So let's first start with the well-known definition of projective space over a field. So let K be a field for the time being, and let V be a vector space over K. Then projective space associated to V. P of V is generally defined as the set of homogeneous lines, and the set of one-dimensional vector subspaces in V. And in order to relate this to affine spaces, to standard affine space, what we do is to choose a basis in V so that V is identified to K to the I. We assume that V is a finite dimension first. Well, we better do this finite dimension. So we take a basis V1 up to En and V, and being the dimension of V, we have an isomorphism between V and Kn. And P of V, we will cover it, call this X if you want. It's for the time being it's just a set, something pretty naive. We will cover it by subsets Xi, I between 1 and N, each Xi being in one-to-one correspondence with affine space of dimension n-1. P of V is viewed as projective space of dimension n-1. How are we going to do this? Well, here projective space can be viewed as being a line is just generated, any line is generated by any vector x1, xn, which is not, where all the xi's are not 0, and two vectors are define the same line if and only if they are proportional. If the x prime i's can be deduced from the xi's by multiplying by some scalar, some limit of k which must be non-zero. And so you can say that P of V is also the quotient set of V star, the set of non-zero elements of V, divided by the action of homotopy, it's K star. So it's in terms of this that we will write down perhaps what the subset Xi is. Xi then will be the set of all classes, of all points x1 up to xn, such that the i's coordinate xi is different from 0 up to multiplication by scalars. So in geometric terms, this means that the line is not contained, that the one-dimensional vector space that we're considering is not contained in the hyperplane spanned by the basis vectors except EI. That's what it means. All right. Now, when we look at this subset, then by normalizing this vector in a unique way so that xi becomes equal to 1 by multiplying it by the scalar so that xi becomes equal to 1, we see that's in one-to-one correspondence with the set of vectors where all coordinates are arbitrary except the i's should be equal to 1. And therefore there is a bijection called this ui between xi and kn-1, which is also the set of k-valued points of affine space of dimension, standard affine space of dimension n-1. And this being so, we could, if we wanted, but we would kind of lose track of the geometry of the situation, we could describe the set PV by taking how many copies? N copies of the set Kn, k to the n-1, and gluing these together, much in the same way as we have done so we're doing right now. But we would get mixed up in the indices, and I would anyhow. And it's kind of unpleasant to work in this way. We would of course have to define this map, I mean to make explicit, and then to define the intersections xij as subsets in xi identified to kn. So we have to, for every pair of indices ij, we have to define subset in kn. This would be, I think, kn minus 1, I'm sorry, this would be kn minus 2 times k star, where the k star is put, I guess, probably in the j's, something like this place, never mind. One has, yeah, it's a kind of unpleasant to express, which say that it is. If you view kn minus 1 to be embedded into kn by taking x1, x2, xn minus 1 mapped into x1, etc., the i's coordinate being equal to 1 and the others being in the next coordinates you see, then it would just be the intersection. No, that's not true. Well, never mind. I think it's not worth it to really write it down explicitly. Let's do it, however, if v is of dimension 2, you see, so that we have projective space of dimension 1. Yes, I mean that maybe it's a little nicer to write down. Then we have just two pieces. So we are looking at vectors xy, which are not 0. So either x or y is different from 0, and we take one piece is where x is different from 0, it's isomorphic to k, and the other piece is where y is different from 0, it's isomorphic to k also. The intersection of the two now is can be identified with k star. You see, this would be correspond to vectors. Here x, two pairs xy where x, let's say, is different from 0, then we take x to be equal to 1, and then it's identified what we get. The lines we get are identified to any scalars here, and when we write down that the scalar is not equal to 0, we get k star. And the same thing here. We get the subset k star of k. And now we are going to, in order to get projective space, we are going to glue together these two sets k by a bijection between k star and k star. Now this bijection we are going to take is not the identity, but it is lambda goes to lambda to the minus 1. That's what making these things explicit will give. In fact, the coordinate on the one hand would be y over x, and the other coordinate would be x over y. You see, so the product of the two is equal to 1. And now in terms of schemes, we could, if we wanted to, clarifies the whole thing by replacing here those sets kn minus 1, k to the n minus 1, by the schemes en minus 1, defining subschemes in these schemes en minus 1, call these xi. For now these schemes here, well here I have already used the letter xi with usual I. Let's take here the Grothendieck i's. We have schemes xi, and then these schemes we could define open subschemes xij, and we could define now a scheme P of V, if you want, projective scheme associated to V, by gluing together the xi's according to xij's.
In this very particular case, again, this is a unique bijection, which may
separated scheme.
Let's see, what are the isomorphisms between K star and K star first of all? So there are of course others, you see, you can multiply this by a homotopy. It wouldn't make much difference, you see. But it should be an automorphism of the multiplicative group of GM of the line minus the origin, which should not interchange the point at infinity and 0, you see. It should keep 0 fixed. Then you extend it to the projective line, it should keep 0 fixed and infinity fixed. Take homotopy, that will be alright. But taking lambda goes, take homotopy, I mean times this composed with homotopy. This would be alright. In fact, there's, so to say, should I say, two homotopy classes, so to say, of bijections of the line minus the point with itself, in the sense of algebraic geometry. One are just all the homotopes, you see. They have the property of extended to the projective line of leaving the origin and infinity fixed. And the other is homotopes multiplied by lambda goes to lambda minus 1, which interchanges the point at infinity and the point 0. And of course, what's important here is that we are interested in those which interchange the point at infinity. But I mean, all this is heuristics. Never mind. I wanted to say that we could define a scheme which we would call projective scheme of dimension n-1 associated to V over field K or even over an arbitrary ring by doing some unpleasant gluing business, but we would keep track, I think, of the geometric significance, of the global geometric significance of the object we are just constructing. We would do things in a kind of in a blind way. I think what is much better in order to understand what one is doing is to define a functor which has evident geometric significance, then to prove that this functor is representable. And it will turn out that if you apply the general criterion I have just shown, that the representability proof is pretty easy. These FIs, these subsheets of F which turn out directly to be representable by affines, they will be just these XIs here. And the fact, I mean, these XIs, the only role there would be to see us providing one way of covering the projective scheme or projective space, whatever you like to call it. By Now, I want to make a first remark about duality. If B is a vector space, then its dual of finite dimension, then its dual is again a vector space of finite dimension over K. And we can reconstruct V in terms of V Czech as being the dual of its dual. So to give V or to give V Czech is the same thing. On the other hand, I get a line in V by polarity between vector subspaces here and vector subspaces here just correspond to hyperplanes in V Czech. And therefore projective space associated to V, if we define it as a set of all lines of V, as a set of all one-dimensional vector subspaces of V, is in one-to-one correspondence with the set of all hyperplanes in V Czech. Now, in many instances, it's more convenient to work with the set of hyperplanes. You will see technically for what reason, than to work with lines. And therefore, I prefer to work in the space in which it's the hyperplanes that we are considering. And in fact, what I have written down here, PV, in order to conform to standard ways of viewing things, I would rather call PV Czech. So for us, PV will be the set not of lines in V, but rather the set of hyperplanes in V. That is that I will deviate from the traditional traditional terminology by calling projective space associated to V its point over K to be the hyperplanes in V. That means that what I call PV, the old timers would call PV Czech. All right, now with this in mind, now we want to construct a functor going from K algebras, let's say, to sets which would embody, call it P of V or shortly P, let's say. And this function should be such that its k-valued points, of course, should be the points we have just said, namely set of all hyperplanes, set of all hyperplanes in V, id est. In fact, a hyperplane, I view it to like, still another way of viewing hyperplanes in a vector space is to consider that they correspond in a one-to-one way to quotient spaces of V, which are one-dimensional vector spaces. Id est set of all one-dimensional quotient vector spaces. Quotient spaces of V. So that's what we start with, and we want to see a natural way of generalizing the description of these points, k-valued points, to description of k-prime-valued points. Assume that V Czech is a rule of V. So what we have described here is something, so one-to-one correspondence with a set of lines in V Czech. And so I guess that if we now like an algebra K over K over K, what we have to do is to look at the base change from K to K prime in the vector space V over K. Now, of course, the fact that where the vector space gets lost, we have just a module over now an arbitrary ring K prime, Vk prime, and we want to describe something which would correspond to hyperplanes in Vk prime, and but we want, of course, a functor that should be representable, moreover, for variable K prime, represented by a scheme, which should, for instance, be a sheaf, in the sense we had explained. So, the thing that will work nicely is the following thing, is to take all quotient modules of Vk prime, K prime equals set of all quotient modules of V lower K prime that are, so we have to see what replaces one-dimensional vector space over K. What's property? We could, of course, say that they are free of rank 1. Let's try. That means that we are looking at submodules of Vk prime, that the quotient by these submodules is free of rank 1. Now, there's one drawback with this notion, namely that being free of rank 1 is not a local notion on the spectrum, Vk prime. A module can very well be a module, let's call it L, let's say, over K prime, can be such that L localized in Fi as a module over K prime localized in Fi is free of rank 1, let's say, for every I, where the Fi's generate the unit ideal without L being itself free of rank 1. So what we now take the next best thing, locally modules that are locally free of rank 1. So instead of free of rank 1, we just say in order to make the definition a local one, so that we have a chance to get a sheaf, but only a pre-sheaf, such that are locally free of rank 1. These are also called these are also the so-called invertible modules. Let's make here now a little let's open little parentheses. Let K be a ring. It would be K prime in a minute, but I don't like to drag the primes along. Let K be a ring, and L a K module. Then the following conditions are equivalent. Equivalent conditions. Let's say A, the sheaf L tilde on the spectrum on K tilde. Maybe we call the ring A, so it was a little larger than the field. On the spectrum of A is locally free of rank 1. That is, that the spectrum can be covered by open subsets, so that the restriction of the sheaf on each of these is isomorphic as the sheaf of modules to the structure sheaf itself. So this is not, this is expressed not in terms of commutative algebra, properly speaking, because we introduce topological spaces, sheaves, and such things. But we can, in terms of commutative algebra, we can state it the following way. There exist F alphas in A, generating the unit ideal such that for every alpha, L tensor over A is A localized in A alpha, which is just L localized in F alpha, is free of rank 1 over as a module over the localized AF alpha. In the interpretation that A and B are equivalent is trivial to the fact that if X is a spectrum, the XF alpha, the XFs form the basis of the topology. And because of the dictionary between sheaves on XFs and modules over the AFs. Alright, and C, the C will give rise to the terminology of invertible modules. There exists a module M over K such that M tensor L but is isomorphic. I'm sorry, it was A. The module M over A such that M tensor L over A is isomorphic to A. And then this M is unique up to unique isomorphism. And it's called the inverse of L for tensor product. It's called L to the minus 1. In fact, it's equal also, and M must necessarily be equal then isomorphically to Hom over A of L within A. It's a dual. Still another way of saying it, why not, is to say that L is projective of finite type, projective module of finite type, and for every prime, let's say P prime of A, LP, which is a module over AP over the local ring AP, where AP is free of rank 1. It's known that the projective module of finite type over local ring is always free, and we want that the rank of this free module over the local ring should be 1. All right. So that's just commutative algebra. Pretty trivial proposition. I won't give the proof here in minutes. Just a little exercise. In order that the notion of an invertible module over a ring should be well understood. When we interpret things geometrically on the spectrum, it just means that we are dealing with locally free sheaves of rank 1 on locally ring space. So therefore also the invertible sheaves on the local ring space. So Now the functor that we are going to consider is a functor that associates to every algebra k prime over k the set of all quotient modules of v lower k prime that are invertible. So in terms of submodules rather than quotient modules, this would mean that we look at the set of all submodules that are such that the quotient is local flow of rank 1, or also that are direct factors that would amount to the same of v k prime, and that implies, of course, that the submodule is projective of finite type, in such that the rank of this projective module of finite type on k prime is everywhere at every prime equal to, what is it? If v is of dimension n of rank n minus 1. But one has to be careful to, when one expresses things in terms of submodules of v lower k prime, to insist that the submodules should be direct factors. Otherwise, it's not enough to take submodules which are projective of finite type and which have the right rank, for instance. Already if v is of dimension 2, it wouldn't do. Alright, so now that this is a functor, it's pretty clear, because if we have a homomorphism from k prime into k second, then vk second is deduced from vk prime by just making the base extension from k prime to k second. And whenever we have a quotient module L of vk prime, then because tensor product is right exact, that's why quotient modules work better than submodules, then L tensor over k prime with k second is a quotient module of vk second. So if we have an epimorphism from vk prime into a module L, this defines an epimorphism from vk second to L tensor k prime k second. And if L is invertible, an invertible quotient, then it's pretty clear that by base change we still get an invertible module. Any of these conditions here shows that the notion of an invertible module is stable under base change. Therefore, the set P of k prime is mapped in a natural way to the set P of k second, and this is transitive when we have successive homomorphisms of algebras k prime, k second, k third. So we get a functor. And this functor we will call Z projective space, let's say, over V, constructed on V. On the other hand, the fact that K was a field, we have not used it really now. If you have any module V over K, K being any ring, then we have constructed here a perfectly good functor, which we call a Z projective space functor associated to the K module V. And now the contention is that this functor is always representable. We don't even have to assume that our module is free or projective or anything like this. It doesn't have to be of finite type either. But of course, if we want the scheme that represents it to be of finite type over K, that's the notion which we will define a little later, then we will have to assume that the module V is of finite type over K. And of course, the properties of the scheme over K are nicer if V is assumed to be nice over K. V, for instance, is projective of finite type. That's this free of finite type. Then this projective scheme that represents it is smooth over K, so it's something like non-singular relativity to K. It's kind of nice. Otherwise, we may have a lot of singular points. But in the proof of representability, in fact, we won't have to use the fact. We won't see the difference whether V is of finite type or not, and whether V is free or not. All right, now let's give the idea of the proof, which is much the same as the matching together thing, which I said. And So K now is any ring, and V any K module, and P of V is a functor just constructed going from K algebras to sets. Maybe before I pursue, I should notice that this functor is a sheaf. I will say what is the sheaf on the category of all schemes that corresponds to it. That would be kind of nice. Therefore, just that denote S by S the spectrum of K. And let's look at the category of all schemes S prime over S, so up to reversing arrows. That's an enlargement of the category of all K algebras. Now, what would be the natural functor to define in terms of our V that we have over K? To give a module V over K, we have seen is the same thing as to give a module V tilde with M of OS module that is quasi-coherent. So what we start with is in fact a scheme S, which turns out to be affine here, happens to be affine, plus a quasi-coherent sheaf M on S. On the other hand, we have seen that when S prime is affine itself, then to make the base change on the module V for the ring homomorphism K goes to K prime corresponds just in terms of ring spaces, S prime being a ring space over S, corresponds passing to the tildes over here to taking the inverse image of M as a sheaf of modules over S prime. And therefore, PV of S prime should be described in terms of the inverse image of the sheaf of modulus M that we have on S by the structure morphism from S prime to S. And this will be the set of all quotient modules, but now when I say modules, it's with a capital M, it means sheaves of modules on S prime of F upper star of M, which are locally free of rank 1, which are invertible. Modules. We know that if S prime is affine and corresponds to the ring K prime, then this corresponds exactly to what I have described here because of the perfect dictionary which we have between quasi-coherent sheaves and modules by K prime. Because of course a sheaf of modules that is locally free of rank 1, it's quasi-coherent, it's a purely local condition. We just have to notice it's a free sheaf of rank 1 is quasi-coherent, and therefore it comes from a module. Alright. And under this, in this form, it's pretty clear that our functor is a sheaf, because to give a quotient module of a given sheaf of modules is a local affair, and the property that this quotient module should be locally free of rank 1 is also a local affair, also a local condition. So if we replace S prime by varying open subset of S prime, we get a sheaf on S prime. The sheaf of all quotient, invertible quotient modules of the given module here, F star M. So certainly we have a sheaf. That's because I was careful here to take locally free sheaf of rank 1 and not free ones. And now we have to show that this sheaf is representable, and therefore we have to find subsheaves Fi of F, which such that the inclusions are open inversions, so that the big sheaf is the supremum of the subsheaves, and such that each of these subsheaves is represented by an affine. Is a representable functor in the strict sense, representable by an algebra over K. So in order to do this, I take a set of generators, EI and V, set of generators of the K module V. So they need not form a basis. I don't care if V is free or not. And I will describe a subfunctor pi of the functor p in the following way. Pi of p prime, say, if you like to say it in terms of functor on rings, p of k prime equals the set of all quotients of v lower k prime. Now, for these quotients L, if you want, such that the image of EI in L, you see EI is an element of V, it defines an element of Vk prime, and therefore it defines an element of the quotient L of Vk prime, is the basis of L. Which implies, of course, that L is free of rank 1 and therefore also locally free of rank 1. Therefore, this here is a subset of P of k prime, and of course it is a subfunctor for variable k prime. And now, so this is defined, in fact, for every element in V. We can call it a P lower EI if you want. Lower EI of k prime equals P lower A. This defines such a subfunctor for every element in V. And now we have to check the three properties. A, let's say, first of all, the PIs are subsheaves. Of course, we have to check this, that's evident. Are subsheaves, and Pi goes to P's inclusion is an open immersion. B, that the PIs are representable by affine, in fact. Well, representable in the strict sense is a functor from k algebras to sets by k algebras. We will say see which ones. Then the EIs are a basis. We will just find that it's just affine space, standard affine space, on the basis elements I minus I, and see that P is the supremum of the subsheaves Pi in the getter of sheaves. All right. Now, each of these is pretty evident. That we have subsheaves is evident because the fact that a section of a sheaf should be a basis of the sheaf of modules is a purely local condition. So therefore, what we have defined here is a subsheaf. For every S prime, let's say over S, we have a subsheaf. We get a subsheaf of the sheaf of the restriction of the sheaf P to all open subsets of S prime. Alright, so that's clear. That Pi goes to P is an open immersion is pretty clear also, because the condition that a section of an invertible sheaf is a basis is an open condition. I mean, if it is true, should I say? What does it mean? I mean, it's kind of clear, but I could make it explicit. So we have to show that if we have a morphism from S prime into P, and if we take the final product, that this here is represented by an open subset of S prime. So to give a morphism from S prime into P is just to give a point of P besides an S prime. That means it is to give a quotient L of the sheaf MS prime so that L is invertible. And now the subfunctor P prime I of S prime, it corresponds to its values, this values in some S second, are just those morphisms from S second to S prime, such that the given section EI point, let's say, of L becomes a basis on it when we pull back to S second. But if we look at the largest open subset on S prime, where EI is a basis of S, namely where EI does not vanish on the fibers, which is the set which we would call S prime lower E point I, you see. It's just the usual notation, except that L is not the free sheaf of rank 1, but a locally free sheaf of rank 1. Then, these morphisms which have the property I stated are just those which sector through this open subset. For a section of a locally free sheaf to be a basis is purely, it's something that can be checked point by point. It just means that in the reduced fiber, reduced modal maximal ideality of the point, it should be non-zero, this section. All right, so these are open notions, that's quite clear. That the PI are representable will be pretty clear too. Let's first show that P is a supremum of the PIs. That just means the following. If you recall what it means, that is, we have a supremum of sheaves, not of pre-sheaves. That means that whenever we have a point of P, this value is in some S prime, like here. That is, if we have a quotient module L of F star M, which is locally free of rank 1, that S prime can be covered by open sets that on every one of these. The restriction of this quotient sheaf comes from one of the PIs. What does this mean? Well, as the EIs generate V, they will generate, the image in VK prime will generate VK prime, and therefore the images in L will generate L. But if they generate L, then in the neighborhood of any point, one of them will be a basis. Because if you take the reduced fiber at this point, when you reduce the maximal ideal, you have a vector space of dimension 1. The residual field. In this you have a set of generators. So one of these generators, one of these elements must be non-zero. But that means that the section in the neighborhood of our point must be a basis. All right, so this is clear too. So this is clear. Now what about being representable by K algebras, this functor? Well, if we have, let's see. If L has a, if EI is a base, if I defines the base of L, then L can be identified with OS prime itself through the spaces, and therefore the functor Pi can be viewed as being the functor of all epimorphisms going from as being the functor of all homomorphisms from V K prime into, from F star M into OS prime, which carries the given section EI over S prime of this sheaf into the unit section here. And I think the time is a little short now, but in terms of what we have seen, it's pretty evident that this functor is representable. In effect, it's representable by the symmetric algebra of M divided by the ideal EI minus 1. So it's representable by, let's make this more explicit perhaps next time, it takes a few minutes. Symmetric algebra of V divided by the ideal 1 minus EI. So of course, if V is free and the EI form a basis of this, then the symmetric algebra of V is just the algebra of polynomials indexed by, with indeterminates indexed by the same set I, and when we identify EI one of the determinates to 1, this means that we take the polynomial ring with respect to the set of indeterminates Tj, where J is an I but different from I. So then these pieces Pi, these affine pieces, are just standard affine space of dimension capital I minus 1. When capital I is finite, and n is n minus 1. If capital I is infinite, it's just infinite dimensional standard affine space. All right, so next time we are, perhaps, if there are any questions, we are going to prove this representability, which is pretty evident, and deal with the other examples of representable functions, representable by schemes. So give some standard examples of schemes. So last time we have been we started using systematically the language of sheaves in a somewhat unusual context, because sheaves on something bigger than just the category of open subsets of regular topological space. And here we used somewhat freely the notion of epimorphisms of such sheaves, sums of such sheaves, and like constructions. So maybe I should come back a little bit on this notion and try to clarify it a little more. And I think we could collaborate by asking questions about the things that seem obscure, because otherwise I might just go on being obscure and nobody will shout. So here we have the category of schemes over a given scheme S. Ground scheme S might be the spectrum of a ring K, say, that is not so important. So I guess that there's no difficulty in understanding what a scheme is. I mean, that we have such a category. The morphisms, once again, are morphisms of locally ringed spaces. It sits inside of the larger category of locally ringed spaces over S. And most functors in fact that we are considering could be extended to functors to this category. In fact, of course, if we have a scheme X over S, then we can look at the functor Z goes to Hom over S of Zx, where Z runs not only over schemes over S, but where Z goes to the category of locally ringed spaces over S. But never mind. It turns out that most functors that we are going to represent, in fact, in a natural way, they make sense, these functors of the larger category of locally ringed spaces, and the representability by schemes will be true if the argument varies in the starter category. But for the time being, let's restrict to this category, and we are therefore interested in functors from this category to sets, which form the objects of a new category, the category which we noted SCH over S hat, the category of all functors, concurrent functors from SCH over S into sets. And within this category we have distinguished a full subcategory which consists of those functors which we will call sheaves for the Duskin topology. So if need be, the tilde will be qualified by capital Z or ZA, indicates that we are dealing with sheaves in Zariski sense, for Zariski. And if F is an object in this category here, F is said to be in the subcategory, then F is said to be a sheaf. If the following condition holds, for every argument, how will we call an argument in here, S prime or something like this, for every S prime, scheme over S, and for every covering of S prime by open sets S prime I, S prime I is being open, the natural diagram Fs prime goes to the product of the S prime i's and goes to the double product of F S prime I intersects S prime J. This diagram should be exact. Namely, a section of S prime over F, an element of F over S prime should be the same thing, essentially as a collection of a section of F over the S prime i's, namely of elements of the F S prime i's, which match in the intersections. Now, and such F's, they make up this category of sheaves on SCH over S on the category of all S schemes in the sense of Duskin topology. Now, maybe I should make explicit I should explain how to re-explain this notion in terms of usual sheaves. So, if F is a functor from schemes to sets, a continuant functor, I don't assume for the time being that it's a sheaf, then to this functor, we can associate for every S prime in the category of schemes over S, or every S prime scheme over S, we can associate a pre-sheaf Fs prime, pre-sheaf on S. In the usual sense now, S is just a topological, S on S prime, I'm sorry, S prime is just a topological space, and we know what it means, a pre-sheaf on topological space. It's a functor going from open subsets U prime of S prime to sets, and to the open subset U prime of S prime, I will associate F of U prime. That is, I take the restriction of the functor F to the subcategory of, so-called subcategory, to the category of open subsets of S prime with the inclusion morphisms between them, which are S morphisms. Now, this here is a pre-sheaf, and the condition which I have written down here for F to be a sheaf for a given S prime and for variable coverings of S prime by open sets, this means almost that F lower S prime is a sheaf on S prime. It would mean that it's a sheaf on S prime if we take not only S prime but any arbitrary open subset of S prime and take coverings of an arbitrary open subset of S prime. Therefore, altogether, when we let everything vary and both S prime and the covering of S prime, the condition that F is a sheaf in est that F belongs to this category SCH over S tilde just means that for every S prime scheme over S, F lower S prime is a sheaf in the usual sense. So the notion of a sheaf on this huge thing is reduced to the notion, to a certain extent, is reduced to the notion of sheaf in the usual sense. So maybe you will feel better. But however, one could make this still more explicit by saying, all right, so if F is a sheaf on the huge category here, in the unusual sense, so it defines as various sheaves on the S primes, Fs primes, but how can we reconstruct the big sheaf knowing the small sheaves? And that's pretty easy to explain. I will give the result. This will be a certain factoriality property of this sheaf Fs prime associated to S prime for variables S prime. So let's see what happens if we have a morphism from S second into S prime, both objects of our category of schemes over S. So a morphism of S schemes. And let's assume F is just a continuant functor from S schemes to sets. And I will give a relation between Fs prime and Fs second. Well, this relation is the following. Whenever it's that Fs prime, let's this morphism here be F. That Fs prime is mapped in a natural way into the direct image of Fs second, or what amounts to the same, that there is a by definition of morphisms of sheaves on different spaces, that there is a morphism from fs prime to fs second compatible with this continuous map. Let's see how we define this homomorphism. What does this mean? This means that for every open subset u prime of s prime, we give a map of the sections of this sheaf over u prime into the section of this sheaf over u prime, in a way compatible with restrictions. Now, here the sections of fs prime over u prime, they make the set f of u prime by definition. Yes, fs prime of u prime. And what now is the sections over u prime of the direct image of fs second, by definition of the direct image, that's the sections of fs second over the inverse image of this open set, f minus 1 of u prime, and that's also equal, by definition of fs second, to the value of f on f minus 1 of u prime. Now if we have the u prime here, and if we look at its inverse image, u second equals f minus 1 of u prime, then f of course induces a morphism from this into that. Or is f restricted to u prime, something like this, f lower u prime. It's reduced from f by the base change u prime goes to s prime. And therefore, the f of u prime goes to f of u second because f is a continuous functor. So we get this map here. And it's pretty clear that this map from f u prime to f of u second is compatible with restriction maps. So what we do get is the following. This pre-sheaf that we have on an S prime, for any S prime, depends functorially on the variable S prime in the sense we just made explicit. For every morphism S prime goes to S second goes to S prime, we have a morphism from S prime into Fs second in the opposite direction, as it should, for morphism of sheaf on different spaces. And of course, this is compatible with compositions of maps. We can say, in fact, that S prime goes to f of S prime is something like a contrarian functor going from the category of schemes over S to the category of sheaves over variable schemes. And it's pretty clear that when we know this functor S prime goes to Fs prime, we have reconstructed the functor going from schemes over S to sets to give, yes?
I think I'm a bit lost. I'd like to know where you started. You started with an F in scheme R.
Yes.
Right?
F is a functor contrarian from schemes to sets, schemes over S to sets. I want to explain what such a functor, I want to reformulate the notion of such a functor in terms of functors on smaller categories than the huge category of all schemes over S, namely in terms of those pre-sheaves over the various S primes separately. And what we have done is to associate first to every F these pre-sheaves and to show that these pre-sheaves depend functorially on S variable S prime. And now the remark I'm making is that the converse is true, if you have such an assignment which associates to every S prime over S a pre-sheaf Fs prime on S prime, as usual sense. And for every arrow S second goes to S prime, a homomorphism of pre-sheaf of Fs prime into Fs second compatible with continuous map. And in a transitive way, then this comes from a uniquely determined up to unique isomorphism, contrarian functor from schemes over S to sets, because you reconstruct f of S prime, the functor, S being f lower S prime of S prime, that is the section, if you prefer, of f S prime. And this, because Fs prime is a contrarian functor with respect to S prime, turns out to be a contrarian functor also with respect to S prime, but now with values in sets, not with values in sheaves. not with values in, I'm sorry, in pre-sheaves. However, I was a little rushed in my statement. So what I did show is that f is reconstructed in terms of the function s prime goes to fs prime, and in terms of the systems of the pre-sheaf fs prime and the transition morphisms. But I should, however, state a certain property that these have, namely, whenever s second goes to s prime is an open immersion. So that S second is an open subset of S prime with induced topology. We want that the homomorphism which we have between Fs prime and the like image of Fs second, or what amount to the same, between the inverse image of Fs prime, which is just the restriction of Fs prime to S second, and Fs second. This should be an isomorphism. In other words, we want that the sheaf on the open subset S second, or I'm sorry, the pre-sheaf in this general setup, but the pre-sheaf that is associated to an open subset S second of S prime, when you use this as being a scheme in its own right, could be just the pre-sheaf induced by the pre-sheaf we have on S prime. Induced, this means that an open, being a consonant function on open subsets of S second, I consider open subsets of S second as being open subsets of S prime, and I take the restriction factor, the restricted functor. All right, and now what about, therefore, to give a consonant functor from schemes over S to sets, what we call a pre-sheaf on the category of schemes over S, is the same thing as to give such a system of pre-sheaves over the variable S primes with a certain punctuality and this extra condition. And now, what about the case of pre-sheaf on the category of therefore, a huge sheaf, I mean a sheaf, a big sheaf, a sheaf in this, on this big category, is just a collection of ordinary sheaves together with morphisms between the sheaves we associate to different schemes, as I explained here, and the condition that if the scheme S second appears as an open subscheme of S prime, then the sheaf which is associated to S second should be just induced by the sheaf which is associated to S prime. And that's it. And now what about operations on sheaves, like taking inverse limits or direct limits like sums and speaking about epimorphisms and such things? Well, I mean, all these notions, that's something more or less immediate to check in terms of this equivalence of categories. All these notions reduce to the corresponding notions on the sheaves, the usual sheaf Fs prime. Assume, for instance, the same, by the way, would be true for pre-sheaves, but we are interested mainly in sheaves now. So let Fi, for instance, be an inverse system, in some sense, I mean a diagram, of sheaves, in the sense of big sheaves, of objects of this big category. And let's look at the inverse image of these Fi's, which is, by the way, pretty trivial to compute, because this is computed argument-wise. You see, I mean, that's just the inverse limit of functors. And, well, if we want to interpret it in terms of ordinary sheaves on schemes S prime, well, the ordinary sheaf on S prime associated to this is just the usual inverse limit in the category of sheaves over S prime of the Fi lower S primes. And now this is a rather trivial case where, I mean, inverse limits don't offer any problems when dealing with sheaves. I mean, the S interpretation is as trivial as it might, as one might think up. But the same is true also when you take now direct limits. The direct limit of the sheaves Fi is now taken within the category of sheaves not without the category in sheaves of all functors. Therefore, it can no longer be computed argument-wise as functors from schemes over S2 sets. However, the sheaf associated in the usual set associated to S prime, it defines over S prime, is canonically isomorphic to, so I just write equal, to the Dieck limit for the same diagram of the sheaves Fi lower S prime. So in this way, operations, limit operations on sheaves in the big unusual sense, and we'll still have to work with sheaves on big categories larger than just open subsets of a space. They're just these operations identified with their unlocus operations for usual sheaves, except that the functorial character of these sheaves that for variable S prime carry along, you see, because it's pretty clear that for variable S prime, this Dieck limit of sheaves on S prime will depend functorially on S prime, because I mean Dieck limits are something that are functorial. Now what about the notion of an epimorphism, let's say, which you know that notion of epimorphism and monomorphism reduces to notions of limits, essentially. So as a corollary of this description of limits, we find the following. F goes to G, morphism of big sheaves, is an epimorphism in the category SCH over S tilde, if and only if, for every S prime, scheme over S, if S prime goes to GS prime, is an epimorphism. Now, an epimorphism of sheaf on topological space, I think that's well understood what it means. That means that it S for every open subset U prime in S prime, and every section of this sheaf over U prime, and small g element in G lower S prime U prime, which by the way is just G of U prime, but never mind. There exists a covering of U prime by smaller open subsets U prime I, U prime I again open, such that G restricted to U prime I, such that for every index I, for every one of these open subsets U prime I, the restriction of G to it belongs to the image of F S prime U prime I goes to GS prime U prime I. That means to the image of F U prime I goes to G U prime I. That means a section of the sheaf GS prime over some open set maybe doesn't belong to the image of the morphism of the map from Fs prime U prime to GS prime and U prime, but belongs to it locally. And that's in fact that's essentially what I said yesterday by replacing S prime now by U prime. When we replace GS prime of U prime, etc. by their values G of U prime, this just means that for every, well, why not call it just U prime, for every scheme U prime over S, now I forget about S prime, and every G element of GU prime, there exists a covering of U prime by open subsets U prime I, such that for every I, G restricted to U prime I should be in the image of f u prime I goes to g u prime I. That means locally an element of some gu prime, maybe not globally but locally an element of some gu prime should belong to the image of f. Now let's see what this means. Is this clear now? Is it? Let's see what this means in the case when the sheaves F and G are represented by schemes. Assume that F is X tilde and G is Y tilde, so that we have a morphism. To give a morphism between the sheaves, and it's just the same thing as to give a morphism between the schemes, X and Y being just two schemes over S, and I have a morphism like this. So we just look at the statement. It means that for every element of gu prime, that's just a morphism from u prime into y. We can, well, to say that we can lift it globally just means that we can find a morphism of u prime into x, so that the triangle commutes. That is, that a morphism from u prime into y can be lifted. But that's too strong a condition, that we can lift every morphism. This would mean that we have an epimorphism of pre-sheaves. And in fact, this would mean also, by taking the universal case u prime equals y, with the identity, this would mean that x over y is a section. So that's too strong a condition. In fact, that would be an epimorphism of pre-sheaves, the fact that there's a section. But we want to say that we want to express that we have an epimorphism of sheaves, and this means that a given morphism here can be lifted locally. That means that that u prime can be covered by open subsets u prime I, so that the induced morphism by the given one here on u prime I can be lifted to x. Now I want to express this in a simpler way by taking the universal case that u prime equals y. Take u prime equals y with identity morphism here. Then this means that y can be covered by open subsets, such that on every one of these subsets there exists a section. So the fact that we have an epimorphism of sheaves just means that x over y admits locally a section, locally over y. Every point of y is a neighborhood for which there is a section. Now this makes a very concrete sense. So the notion of an epimorphism of sheaves is a direct generalization of this notion of a morphism of schemes that admits locally a section. In fact, I could show that in a certain sense it reduces to this notion, but never mind. I think maybe that's enough to get the meaning through of this sheaf-theoretic language. And in the same way, if we have a family of morphisms, fi is equal to g, of sheaves, when is this family said to be epimorphic? It means just when the corresponding morphism of the sum of the sheaves fi into g is an epimorphism. And that means that every element of some g of s prime, this epimorphic, means that for every u prime over s, as before, and every g of u prime, there exists a covering. Now as the set of indices here is already I, you better take another set of indices. There exists a covering of u prime by open subsets u prime alpha, and for every alpha there exists an I, an index, so that G restricted to u prime alpha belongs to the image of fi alpha of u prime alpha goes to G of u prime alpha. It means that every element of G of some u prime perhaps does not come from one of the fi u primes, from some I, but that at least locally on U prime it does. So if again, this situation of a family of sheaves, of a family of morphle of sheaves with the same target coming from a family of morphle of schemes, what does it mean that this family of morphle of schemes is an epimorphism? It means that every point of y has a neighborhood such that for some of the xi, for at least one of the xi's, there's a section of this xi over this neighborhood. Or what amounts to the same, that means that if you look at the sum of the xi's goes to y, that this has locally a section over y. So I think all this doesn't offer any mystery, it's just a terminology which is, I think, which one just can't really dispense with in these matters that we want to work at ease in the setup of algebraic geometry. See. Maybe I should restate the theorem of representability that we have proved last time. Which is the standard criterion, elementary criterion of representability, which gives most elementary cases of representability. So it's the following. We know already that for a functor, concurrent functor from schemes to sets to be represented, it's necessary for this functor to be a sheaf in the sense we have explained. So we assume already F to be a sheaf. And the conditions for F to be representable are the following. There should exist a family Fi of subsheaves, which has the following properties. Every Fi is just an open subfunctor, open subsheaf of F, which means that Fi goes to F is an open inversion. Wherever I. That means when we make a base change with here with a representable sheaf S prime here, that is just a scheme over S, that then the inverse image of Fi, call it S prime I now, which is a priori a sheaf with morphism into S prime, that this sheaf is an open sub, can be represented by an open subset of S prime with the induced structure and the inclusion. That's what it means. So that's the first condition on the Fi's. The second is that F should be the supremum of the Fi's. Now we have made explicit what this means. That the value of the morphism Fi goes to F should be epimorphic in the sense of sheaves. And C, we want that every Fi is representable, is a scheme. And in fact, we have given a corollary of the statement, an analogous statement. We have assumed that the Fi's are representable by affine schemes lying over S, so that this theorem can be viewed as being a reformulation of the category, a reconstruction of the category of schemes, not using the notion of ringed spaces. Maybe I should make a little comment on the respective utility of the two ways in which we have interpreted schemes as being functors. On the one hand, we have interpreted schemes as being functors, let's say relative schemes over S as being functors from the category of schemes over S to sets, which might, from some logical point of view, seem kind of a vicious circle if you want to understand about schemes. We consider schemes as being something much more intricate than schemes that we functors from the category of schemes to sets. Well, in many questions, that's the right way to consider them, because in the examples that I started dealing with and some others that I'm going to deal with, a scheme really is embodied by the functor it represents. And what is really important is to understand what this functor is. And from this point of view, the larger the category on which this functor is defined, the better out we are. And in fact, for any one of the functors we are considering, like for instance, the vector bundle associated to a sheaf of modules, or the projective bundle associated to a sheaf of modules, etc. The interpretation of this functor on the whole category of schemes over S, and sometimes even on the category of larger categories like the category of all locally ringed spaces over S, or even all locally ringed topoi over S, this interpretation is quite essential. We have to know what the morphisms of an arbitrary scheme into the scheme that we have constructed as representing a functor. So we have to know this functor on as large a category as possible. And therefore, for most practical purposes, it's really this category that is the better category to work with. But we have seen also that we can take the category of affine schemes lying over S inside here and look at the restrictions of our functors to this. And in fact, this doesn't make, as for the category of sheaves which we construct in this way, this doesn't make much of a difference. This comes from the fact that for every given S prime, the affines lying in S prime form the basis of the topology of S prime, the affine open sets. All right. Yes?
In condition A, S prime is a representative functor, right?
Yes.
It's a scheme.
Yes, so put the tilde that you feel better.
All right. So does it follow then that the pullback S prime I is also
not at all. But it's assumed when we...
That's part of the assumption.
That's part of the assumption, yes. No, it's not true that the subfunctor of a representative functor is a representative functor. I didn't even assume a priori, in fact, that the Fi's go to F are monomorphisms. It follows from this condition here that it must be monomorphism. All right, so I can describe also schemes as functors consequent from affine schemes over S to sets, or still more in the sense of the spirit of commutative algebra, as a functor going from rings over S, or let's say K algebras if S is the spectrum of a ring itself, from K algebras to sets, this time covariant functors. Now, this has, not so much practical value. I don't think it's very useful practically, but it has some, what should I say? Philosophical value, almost, I would say. It turns out that there are various generalizations of the notion of scheme, various variants, like for instance the notion of a formal scheme, which is already closer to analysis, and the notion of algebraic spaces of Artin, which are obtained by clutching together, by gluing together affine schemes, but not for Zalki topology, but for some topology between quotes, which is final, the so-called étal topology. And there are still other variants. So it turns out that all these variants of the notion of scheme, which are generalizations of it here, they can be interpreted, all these schemes can still be interpreted as being functors from K-algebras to sets. So I mean, this is a common let's say, denominator of all these notions of schemes, formal schemes, algebraic spaces, formal algebraic spaces, etc. There are things associated that can be expressed in terms of the category of K-algebras. In this case, that would be just some types of complement functors from K-algebras to sets. They're all sheaves, in fact, for the Zalski topology. They're even sheaves for much smaller topologies, like the faithfully flat equated compact, like the faithfully flat topology, whatever this means. We will define this a little later. And as for still further generalizations, you see, like the algebraic stacks, which are more or less like schemes or algebraic spaces, except that it's more in the direction of topoid. Points can have automorphisms now. It's something that comes up when trying to solve modular problems, when we are classifying structures that have automorphisms. Then again, these new mathematical objects are being constructed can be explained in terms of not now functors going from K-algebras to sets, but something which resembles functors going from K-algebras to categories. They are fibered categories over the category of K-algebras. Or if you want to drop K, as you always may, they are fibered functors on the category of modulative rings. So in this sense, we can say that all the basic notions that keep turning up in algebraic geometry for the last, I don't know, 10 years or 100 years or 1,000 years, I don't know. In a sense, they seem all to be tied up in quite an essential way with the category of commutative rings, modulative rings with unit. Either as being that one can interpret the objects as being functors from this category to sets, or that one can interpret them, so main objects of the theory, as being fibered categories over this category of commutative rings. But for practical purposes, once again, if one works within a given context, like the context of schemes, viewed as being locally ring spaces, let's say, then interpreting schemes as functors from schemes to sets is, I think, the more convenient way. So therefore, perhaps from now on, I mean, the rings have served us as a, how do you say, tremplin, starting point. You see something you can jump from to get somewhere else. And we will perhaps now drop this systematic reference to rings, and we will just work freely within the category of schemes and come back to rings whenever it's technically necessary, and not otherwise. Now let's give one other corollary of the system of representability, which is often useful. So let F be again a sheaf on the category of schemes over S, and we wonder if F is representable. Is F itself a scheme over S? I claim that this is a purely local question on S. If F over S is locally over S representable, then F is representable. Now I will say what this means. So make the assumption, assume that S is a union of open subsets Si, which of the Si's is open. And then if I look at the restriction of the functor F to Si, well, I mean, if I have a scheme over Si, it's a scheme over S. And so if we have a scheme S prime lying over Si, for value in S prime, F of S prime is a functor. So you can view it as being a functor on the category of schemes over Si. Call this Fi, this functor. So we assume now that for every I in the set of indices, Fi, the restriction of F to Si, is representable, is a scheme. I claim that then F is itself representative. F is its scheme. Well, that's pretty evident, because Si goes to S is an open immersion, and therefore, in this functor that I described by restriction, I mean, an alternate way of describing it is just by saying that it's a finite product of Si and F over S. So the morphism which goes from Fi into F is an open immersion as an inverse image of an open immersion by this morphism here, base change. So we have subfunctors Fi and F, which are open subfunctors. And of course they cover F because the Si cover S, and therefore the inverse images must cover F. And therefore F is representable if and only if the Fi's are. In fact, I could put it if and only if. In the theorem, if we have subfunctors Fi and F which are open, and such that F is a supreme of the Fi's, then we can say that F is representable if and only if the Fi's are. Because the only if is clear, because we know by definition that if F is representable, then a subfunctor has an open embedding into it if and only if it's represented by an open subset of the scheme that represents F. Alright. So the question of the representability of a functor, therefore, is a purely local question on the basis. And now let's apply this to the question of defining the projective bundle associated to a module on a scheme. So let S now again be a ground scheme, and let Fm be a quasi-coherent sheaf of modules on S. Quasi-coherent, that means that it's locally on S the co-kernel of a homomorphism of free modules. And this means also that on every affine open subset of S, the restriction of M to this affine open subset comes from a module on the ring, on the ring of sections of this affine scheme. That's this affine theory which we have seen. All right. And now I associate to M the functor V of M on the category of all schemes S prime belonging over S. Vm prime, Vm of S prime is equal to the set of all quotient modules of the inverse image of M on S prime, called M lower S prime, which are invertible modules. Invertible, I recall, means locally free of rank 1. Now I claim that this functor, for variable S prime, of course, it's a contrarian functor in S prime, because I took here a property of the quotient, which is a local property, namely being locally free. It's clear that this is a sheaf on the category of all schemes over S, and I claim that this sheaf is a scheme. It's represented by a scheme, which scheme will of course be denoted by Vm again. Well, we are supposed to have done it last time. Maybe I can come back to it if it wasn't too clear. In the case when S was affine, when S was the spectrum of a ring. In fact, then we have represented this scheme as in a rather explicit way using a set of generating sections of M. We have represented it as the union of affines, open subsets, by applying this criterion. But now we will apply this criterion in the form of the corollary. Because in order to prove that this functor here is representable, we have to show only that it's representable locally over S. So I cover S by open subset Si, which I choose now to be affine. That's possible because S is a scheme. And when I look at the restriction of our functor to Si, I just see that this same functor essentially, except that M is replaced by its restriction to Si. So that we have the same problem as before, except that now S we are reduced to the case when S is affine, and now a quasi-equivalent modulo when affine scheme S, now assume S to be spec K, just means that we give ourselves a module V over K, such that the sheaf of modules N is just P tilde, up to isomorphism. And in this case, we have dealt with the problem yesterday. So in fact, this construction of the projective bundle associated to a module makes a sense when the basis is not necessarily affine. Any scheme is all right. Now, should I come back on the proof in the case of an affine basis? Alrighty, so let's do that. So, all we are going to use in this assumption that S is affine is that the sheaf M is generated by its sections, that we can find a family of global sections of M, which I call EI. Such that M is a submodule generated by the sections, that sum is the sum of OS EI. That's all I'm going to use. That's of course true in the affine case, because then, to give the sheaf of modules is the same thing as to give the module V over K, and I take a set of generators of this module over K, and this module is just the module of sections of the sheaf. So these are the I's. And now our functor here, what's this now? It's not V of n, it's P of n. Sorry. P is a little projective bundle. Alright, so I have this functor P, and I define this in P subfunctors, Pi if you want, in the following way. For every index I of the indexing family of these sections, Pi of Si prime is the set of all quotients of the module M lower S prime, such that for these quotients L if you want, such that the image of EI by the compositive homomorphism, which goes from the sections of M over S to the sections of MS prime over S prime, to the sections of L over S prime, because L is a quotient of MS prime. So call this image what do I know? EI bar, EI point if you want, EI dot, such that this image EI dot is the basis for L, and therefore defines an isomorphism between L and OS prime. Now certainly this is a subset of the set PS prime, because a free module of rank 1 is locally free of rank 1. It's invertible. And so all we have to do now is to prove that these subfunctors Pi satisfy the conditions of our main representability theorem. And now, so one of the conditions was that Pi goes to P is an open immersion. So does this offer any difficulty? It just means that the condition for an element of PS prime to belong to PIS prime is, so to say, an open condition. That's it. It means that we have an element of PS, it means the following, that if you have an element of PS prime, So that means just a quotient module L of ms prime, which is an invertible module. And if you look at variable s seconds over s prime, schemes over s prime, and we look at the functor which associates to every such scheme over s prime, either the set with one element if s second goes into s prime, has as an inverse image here an element of, let's consider the corresponding map from ps prime into ps second. We associate to s second over s prime the set with one element if the image of the L we have in here is an element of ps second which belongs to pi s second, and otherwise we associate with this empty set. So we have the subfunctor of s prime, which the subfunctor is represented by an open subset. So that's what it means. And we see that the condition for a section of an invertible sheaf to generate this, to be a basis for this invertible sheaf, is a punctual condition. It means that at every point, it's a basis of the store, or again, it's a basis for the reduced store. It's a non-zero element of the reduced store, which is a vector space of dimension 1 over the residue field. And therefore, being a pointwise condition, the condition for s second to s prime to be such that the inverse image should satisfy the condition is just a set circuit condition that s second maps into a certain subset of s prime. All I have to prove is that the subset is open. And it's a subset of points of s prime, where a certain section of an invertible sheaf becomes a basis, and this is an open set because if it's a basis at the stalk at one point, then it's clear that it's a basis in the neighborhood. Now this kind of argument, you see, is pretty evident. I mean, it turns up all the time when you try to prove that a functor is representable by using this kind of criterion, by having as an intermediate step to prove that the morphism of sheaf is an open inversion or is representable or something. Alright, so the PIs go to P are open inversions. Second condition is that P is a supremum of the PI. That means that every point of P with values in some S prime, every element in some PS prime belongs locally to one of the PIs. That means that whenever we have a quotient of MS prime, which is an invertible sheaf, then locally on S prime, one of the EIs must be a basis of it. But now, why is this? We know that the EIs generate the sheaf of modulus M, and therefore the inverse image on S prime generates the sheaf of modulus MS prime, and therefore the images in L will generate the sheaf of modulus L. And because this sheaf is locally free of rank 1, it can be generated locally by one element. If a family of elements generates it, then at the neighborhood at every point, one of these elements must generate it, and therefore must be a basis for it. Alright, so that's the second fact. And now the last fact you have to prove is that the PIs are representable. And now I become aware that we don't have the prerequisite to prove it directly over an arbitrary basis. So let's prove it now in the case when S is affine.
What were the prerequisites? What are the prerequisites?
To construct the spectrum not of a ring but of a sheaf of algebras. Not of an algebra but of a sheaf of algebras, and we have not done it yet. So, yeah. But we know that we can restrict to the case S affine by my little preliminary there. So let's do this. So that means that the EIs can be considered as being elements of the K module V, such that V tilde is equal to M, the K module V of sections of S by M in fact. And I will now restrict my functor for commutative references to arguments S prime with letter affine 2. So S prime corresponds to an algebra K prime over K, and therefore P of S prime is a set of quotients, modules, of M lower K prime deduced, V lower K prime deduced from V by base change from K to K prime. Quotient modules call them L, which are invertible. Invertible quotient modules. Alright. And Pi of S prime contained in here, it's the set of quotient modules L such that the image of EI in it, so EI is an element of M, it defines an element of MK prime, and therefore an element of its quotient by taking its residual class such that EI point is a basis for L, which of course is stronger than to say that L is invertible. It means even implies that it's free of rank 1. Alright, now I will reformulate this function Pi in such a way that it becomes evident that it's representable. Alright, if we have already a basis for this L, that means that L is isomorphic to K prime in a canonical way by using this basis. And therefore, now to give a quotient of the module MK prime, VK prime, and an isomorphism between this quotient and K prime is just the same thing as to give an epimorphism from VK prime into K prime. But on the other hand, we are interested in those for which the element EI lower K prime of VK prime goes into 1. The chosen basis, which corresponds to the chosen basis from L. And therefore, the set Pi of K prime is just the set of all homomorphisms of Vk prime into K prime, which transform EAK prime into 1. Once we have said this, we can forget about the fact of it being surjective, because it will be surjective, because the image will be a submodule of K prime containing 1, which generates K prime. Now, therefore, Pi K prime appears as being contained in what I call now, the notation is not too fortunate, but let's call it how do you say, fet V, capital N? Boldface V of Vk prime. Recall that if we had a module over V over K, we had associated to this the so-called vector bundle defined by it, which is a functor K prime goes to com over K prime of Vk prime K prime. This was the vector bundle. This functor was the so-called vector bundle defined by the module V over K, and it's representable by the symmetric algebra of V. Because to give a homomorphism of Vk prime into K prime, homomorphism of modules, the same thing as to give a homomorphism of K modules of V into K prime. And the universal solution of doing this through a homomorphism of rings is to take the symmetric algebra of V over K. So this is a functor with respect to K prime. This is the same thing as homomorphism of K algebras of sim V into K prime. So this functor is representable. Yes?
What is V sub K? V sub K?
V sub K prime, you mean? That's what you obtain, deduce from base change in the module V over K by base change K goes to K prime. We are using this notation systematically. Whatever we are deduced from base change by base change, from going over from K to K prime or from a scheme S to a scheme S prime, we denote by putting the subscript either k prime or s prime. So we can interpret the homomorphisms of vk prime into k prime as being the alpha homomorphisms of the k algebra sim V into k prime. Now we have to interpret the condition that we are interested in homomorphisms of modules which transform here, which transform the given element EI into 1. Well, I mean, in the symmetric algebra of V it contains V, and therefore it contains EI as an element. And in fact, if we have a homomorphism of modules here and the corresponding homomorphism of algebras, the image of EI in K prime is the same thing as the image of EI in K prime by the homomorphism of algebra. In fact, the homomorphism from V into K prime is induced by the homomorphism from sim V to K prime, by viewing V as being a submodule here. Alright, and we want now to express that EI is mapped into 1. That means that EI minus 1 is mapped into 0, and that means that we are interested in those homomorphisms which are 0 on a certain element. That means that are 0 on the ideal generates, and that factors through the quotient. And therefore PI is represented boldface V of a certain module is a functor that associates to every k prime the set of all k homomorphisms from V to k prime. What I want to say is the set of all k prime homomorphisms from V k prime to k prime.
What do you name it?
That's the vector bundle associated to V. It's represented by this symmetric algebra. So that's the representability of the projective bundle associated to a given module. And I mean, one can really mostly forget about the proof of representability and just recall that the functor is representable and certainly recall what the functor is. Now let's once again insist on what the main structure is of this projective bundle associated to V. That's the same story whenever we have a scheme that is defined as representing a certain functor. Here we have the scheme P equals P of M now, let's say, over S. We have the structural morphism from P into S, which makes P into a scheme over S, or it's F if you want. You have here the sheaf, quasi-current sheaf M on S we started with. We take its inverse image on P, F star upper M, F upper star M, which we call also M lower P. And there is canonically defined on P a quotient L of MP, which is an invertible sheaf. So which has several names. It's called in Serre's notation quite often it's called O lower P of 1. O lower P is the structure sheaf of P, and then it's something like a twist of the structure sheaf. And this is convenient because this allows us to define O lower P of n for every integer n as being the nth tensor power of L, which is again another invertible sheaf. Beware that L to the tensor power minus m, where m is positive or 0, is by definition equal to what you obtain by taking first the m's tensor power of L and then taking the inverse of it, or taking the inverse of L, the dual sheaf of L, the inverse, in the sense of the percentage of invertible sheaves, and taking its nth power.
I'm confused. What are we doing now?
I'm re-expressing that P represents a certain functor, and therefore there is an element of the functor Pm of P, that means identity morphism if you want, but it just corresponds to a certain invertible sheaf a quotient of MP.
Is script M connected with
It's a datum.
Yeah.
We start with a scheme S and a quasi-coherent sheaf of modules M on S. That's the data. It would correspond, if S is affine, would correspond to giving a ring K and the module V over K. In terms of this, we have constructed a scheme P over S, which is called the projective bundle of the sheaf of modules M, as representing a certain functor, and we call it represents a functor, call this functor again P of M. There's an element of P of P, a regular element, namely an element, namely a quotient sheaf which is invertible of the inverse image of M on P. So that's the main structure on projective space. It has the universal property that whenever we have some base change S prime goes to S, and whenever we have some quotient module, call it this universal one, that perhaps we call it L volte-phase, let's say, and call it OP of 1 if you want. And whenever we have a quotient module of MS prime that is invertible, there exists a unique morphism from S prime into P, such that this invertible quotient of MS prime is the inverse image of the universal one here. And I'm just re-expressing what it means. So that this scheme P over S represents our functor, P of N. That's really the main thing to know about a projective space. I mean, everything else will come out in a most of the interrelation of projective space will come out in a completely formal way from this description. Now let's perhaps play around a little more to see what the relations are between this projective bundle and vector bundles and such things. Just, I mean, to get the feel of the situation. When we recall over a field what is a projective space, but just as a set, we said that it was a set of all lines. And that we could, in a vector space, or rather now are set up as a dual vector space, and that we could do it therefore as being the quotient of the complement of the origin in the vector space by the operation of homotopsies, by the multiplicative group of the field operating on this vector space minus the origin. And we might want to express the same, the analogous fact here. So here the idea would be to compare the projective bundle P of M with the vector bundle V of M. So I should perhaps V volte-phase of M. I should perhaps recall the functor in global terms when S is no longer assumed to be affine, and when the argument S prime is neither supposed to be affine. This functor is the one that associates for every scheme S prime over S the set of all homomorphisms of OS prime modules of MS prime into OS prime. These are the points of the vector bundle associated to M OS prime. Recall that this functor depends on the contravariant wave on M, just as we will see that Pm depends constantly on M. We had also some W of M, W volte-phase of M, which depended currently on it, which was S prime goes to a set of sections of MS prime over S prime. But this, in many cases, is not representable. whereas this always is. Yes?
We might repeat the universal property
Of P?
yeah, of P.
Yes. So on P there is a quotient module of MP, which is an invertible sheaf, locally free range of rank 1. And this has a universal property in the following sense: whenever there is an S prime over S, a scheme, in fact it would work even for any local ring space, wouldn't make a difference. And if we look at the inverse image of M on S prime, if we have a locally free sheaf of rank 1, an invertible sheaf L, which is a quotient sheaf of MS prime, if we have some quotient of MS prime, which is invertible, then we can find a unique morphism from S prime into P in such a way that this quotient of MS prime comes from pullback from this universal quotient of M lower P. Of course, the inverse image of MP by S prime, as MP was itself the inverse image of M by this morphism, it's just the inverse image by this morphism, which is a composite of these two. You see? Therefore, it makes sense to speak of the pullback of this quotient. I'm just repeating that the set of all quotient modules of which are invertible is a functor for variable S prime. Here I have an element of the set of value of the value of this functor on P, and as I have a morphism, it's a content functor. It defines as an element of P of M of S prime. All right. So that's all. That's the whole mystery. It's just a general thing about quadrantable functors. Here saying that I have an object with quadrantable functors just means that I have an object together with an element of f of P if f is a functor, so such a quotient, and which is universal. That's all. Of course, if you are working with Pentagon rings only, I mean this object no longer belongs to the category of rings, and we would be a little bit in trouble to say that we have this universal object, except when taking induced topology and such things, and we could do it. But here, after all, I mean schemes as local ring spaces, they're kind of all right. They can do. Alright, now I want to compare PM with the vector bundle VM associated to M, so call these two, for simplicity, call these two schemes over S, call them P and V. So what one would expect is something like a morphism from V into P, except that from V I have first to delete something from it, something like the zero section. So we have to be clear about what this means. So we have first to define an open subscheme V star of V. Let's do that first. So therefore I will define the subfunctor. So here I have V over S. No, it's not the boldface V. The boldface V was the functor of variable M. So we have this now a scheme V over S. I will define a subfunctor from the functor represented by V. This will be the functor which associates to S prime the set of all homomorphisms, linear homomorphisms of OS prime over OS prime of MS prime into OS prime that are epimorphic. To say that they're epimorphic just means, because OS prime is free of rank 1, that fiber by fiber, when we look what it does on the reduced fibers, namely M of S prime goes to kappa of S prime, M of S prime being the tensor product over the local ring OS prime small s of the stalk of MSX prime with the residual field, that these homomorphisms should be non-zero. So it means that we are taking the homomorphisms MS prime to OS prime that pointwise do not benefit. So that's what stands for taking the complement of 0. Because here, after all, we have a bundle, and we have to say that we take the union of the complements of the various zeros. We take something like the complement of the zero section. And in fact, is this so? Is this not so? No, I guess yeah, it is. In fact, by what I just said, by the explanation I just gave, we see immediately that V star is an open subfunctor. And it's in fact that it is represented by the open subset V star and V, because V minus the unit section minus the zero section of V. In order for a morphism of S prime lying over S into V, namely an element in here, two factors for V star, it's less than sufficient that the image of S prime and V should not meet the zero section. V minus 0 in index V of S, if you want, the zero section, is something like this. All right, but now I want to define the homomorphism from V star into P. So once again, it's just a to define a homomorphism of a scheme is the same thing as to define a homomorphism of functors. And well, whenever I have an epimorphism from MS prime into OS prime, I want to associate to this an invertible sheaf, quotient sheaf of MS prime. Well, after all, the co-image of MS prime goes to S prime, the quotient of MS prime by the kernel of this given homomorphism from MS prime to OS prime, which is AP, the kernel, the quotient of this by the kernel, is a quotient sheaf that is not only locally free of rank 1, it's in fact free of rank 1. Therefore, I certainly have a map which goes from V star of S prime to P of S prime from the set of epimorphisms of MS prime to OS prime into the set of quotients. The image consists of exactly those quotients of MS prime that are not only locally free of rank 1, but that are free of rank 1. All right, and of course this map for variable S prime is functorial. So I get a homomorphism from V star into P. And I want now to express that P is a quotient of V star by GM operating on V star in a certain way, the multiplicative group. So I have to show that GM operates on this. In fact, it will turn out to operate freely, to operate without fixed points. We will see what this means factorially. And then we have to show that the quotient is just P. But the quotient in which sense? The quotient in the sense of sheaves, which will amount, which will imply if I prove that P is a quotient of V star by a certain equivalence relation. In the set of sheaves, this will imply that V star goes to P as an epimorphism, which means, I recall, that V star over P has locally sections over P, that every point of P has a neighborhood for which there is a section. So I will prove these various things. It's just, I'm using exercise of geometric syntax. So let's first prove that this is an epimorphism. And as usual, instead of proving directly that we have local sections, it's more handy just to prove that we have an epimorphism of sheaves. Really, the sheaf language is the most convenient things here. So that means that every element of PS prime perhaps doesn't come from an element of V star S prime globally, but it comes locally from it. That means an element of MS prime, once again, it just means that we have a quotient sheaf L of MS prime, which is invertible, which is locally free of rank 1. To say that it comes from V star S prime means that it's in fact free of rank 1. So that there's an isomorphism between L and OS. So that this quotient comes from an epimorphism of MS prime to OS prime. Now L may in fact not be free of rank 1, but we know it's locally free of rank 1. We know that S prime can be covered by open subsets. On each one of them, it's free of rank 1. All right. So on this open subset, it comes from B star S prime I. So this is certainly epimorphism of sheaves, therefore it has low clear section. That means it has low clear section. All right, that's one point. Now, what about the operation of GM? We have already noted that V is not only a functor from schemes over S2 sets, it's in fact a functor which has a module structure on the functor, on the ring functor, S prime goes to gamma S prime OS prime. This is represented in fact by standard affine space over S prime. All right, and therefore, a fortiori, the subfunctor of O, which is the mathematical group of invertible elements, O star, which is S prime goes to gamma S prime OS prime star, to the set of invertible elements of the ring of sections of OS prime, the structure sheaf, will operate as a group on the set for S prime, and this is functorial for S prime. Now this functor we have denoted by GM. It's representable too. That these two functors are representable. In fact, what represents O is just standard affine space of dimension 1 over S. It has a ring structure to it, and here is what we would call E1S star in the term we have just used before. It's a complement of the units of the zero section. To prove this representability, we have to prove it only locally on S, and in the affine case, we have done it quite trivially, by the way. In the course on groups, what represents these functors respectively are the rings K of T, and here K of T, T minus 1, then S is affine. All right. So we see that GM operates on V, and in fact, it operates also on the subfunctor V star. It leaves V star stable. This just means that if you have an epimorphism, MS prime goes to OS prime. If you multiply this epimorphism by an invertible section of OS prime, it still remains an epimorphism. This comes from the fact that an invertible section defines an isomorphism between OS prime and itself. So if you compose an epimorphism with an isomorphism, you still have an epimorphism. All right. So GM operates on V star. I claim that it operates freely on V star. GM operates freely on V star, which can be expressed either diagrammatically by saying that a certain morphism GM times V star goes into V star times V star is injective, is a monomorphism. But it's easier to see on the functor. It just means that for every S prime, the group GM of S prime, which is a group of units in the ring gamma S prime OS prime, operates freely on the set of all epimorphisms of MS prime and OS prime. That means the following: if there's an element in the set, an epimorphism U from MS prime on OS prime, then lambda U can be equal to mu U, lambda U being 2 units, if and only if lambda is equal to mu. Or if you prefer, let's call it rather, let's say the following way: lambda U equals to U implies that lambda is equal to the unit element of our group. That's what it means, that the group set operates freely. The stabilization of every element of the set on which it operates. Put the unit subgroup. But that's pretty clear, you see. If lambda U is equal to U, this means that lambda minus 1 U is equal to 0. But as U is an epimorphism, that means that lambda minus 1 operating on OS prime, that lambda minus 1 multiplied by the one element in OS prime is equal to 0, which means that lambda minus 1 is equal to 0. I mean, it's pretty clear. It wouldn't be true that GM operates freely on V. It operates freely on V star. of course, I mean, if you look at the origin of the vector space, the group GM, it's fixed under the action of GM. All right, and now it operates freely on V star. It's particularly tempting to look at the quotient. And now in the sense of sheaves theory, so we have already said how the sheaves theory for these big sheaves can be reduced to sheaves theory in the ordinary sense. So looking at the quotient just means that we look at the quotient for the ordinary sheaves on each of the S primes. So I will look now at the quotient V star divided by Gm. Of course, the map which goes from V star to P is compatible with the action of Gm when we let Gm operate on P trivially. That means that if we have two morphisms from NS prime to OS prime, which are epimorphisms, U and V, V being reduced from U by scalar multiplication, if V is equal to lambda U, lambda being a unit, then the two quotients of MS prime defined by U and V are the same. This is clear, isn't it? Because they have U and lambda being a unit, have the same kernel. Now I'm just reconstructing now projective space or projective scheme as a quotient of vector space minus a point by the action of Gm. Alright. So because the morphism from V star into P I defined as compatible with the action of Gm, it can be factored into V star goes to V star over Gm, I pass it to quotient, which goes to P. And now all I have to prove is that this is an isomorphism. When we have proved this, then we will know that V star is a principal homogeneous space over P with group Gm lower P. That V star is a torso over P with group Gm over P. Which is also kind of standard way of viewing the vector space minus a point as being a fiber bundle over projected space with fibers homogeneous space under the mathematical proof. So that's what we have explained. So we know already that this is an epimorphism because the composite term is an epimorphism. So certainly it's AP, so all we have to prove is that it's a monomorphism. That means the following, that if two points of V star have the same image in P, then they are congruent on an action of the group Gm. I'm just re-expressing that 2 points of a vector space define the same element in the projective space, and if one is multiple of the other by a scalar. All right. So let's U and V be two homomorphisms of MS prime and 2 OS prime. So I do now the converse of what I did before. I prove that if V is a multiple of U by a scalar, that then they define the same quotient of MS prime. Now I'm going to prove the converse. If U and V define the same quotient, then they must be so that one must be a multiple of the other by an invertible scalar. But that's clear too, because this just means that after all, what does it mean? We have one and the same quotient, L of M, which happens to be free of rank 1, and U or V are two different isomorphisms between this quotient and OS. This here is U, this is V. That's essentially, except that we have to compose with the quadratic morphism here. And we can deduce one from the other by taking isomorphism of OS with itself, namely U minus 1 composed with V. Then we can start call it rather U naught here and V naught here. V naught minus 1 composed with V naught. But an isomorphism from OS to OS, I'm sorry, there are primes to be put. From OS prime to OS prime, it's just a multiplication by an invertible scalar. I mean, scalar now in the sense of section of OS prime. All right. So I have shown that V star, the vector bundle of the set to M, minus the zero section, is a principal bundle over P with structure sheaf of groups Gm. Or if you prefer Gm over P. Gm put it back as being a sheaf of groups over P. Now, to complete this picture, I want to interpret this principal homogeneous space I have over this torsa under GMP. And now recall that the group GM, that's also the group GL1 if you prefer, the linear group scheme in one variable. That's also can be good as a function of automorphisms over O of the free module of rank 1 over the basis we are considering S here. It's a functor which associates to every S prime the group of automorphisms of OS prime modules of OS prime itself. And because of this, because it's a group of, it's a functor of automorphism of a certain object, it turns out that torsors under GM are essentially the same thing as twisted representatives of this object. In fact, they have a one-to-one correspondence between torsors over a given S, let's say, torsors over S with group GM, and the category of locally free sheaves of rank 1, namely sheaves of modules on S prime that are locally isomorphic to the standard free sheaf of rank 1. The correspondence between the two is the following. If you have a locally free sheaf of rank 1L here on S, we associate to it the following torsor. It's as a functor on S, it's the functor of isomorphisms of OS modules, over O, say, of OS with L. Torsors over S with group GM. These are the sheaves F over S on which GM operates in such a way that GM operates freely on F, transitively on F, and that locally that F goes to S as an epimorphism, so that there are locally sections, so it's locally trivial. Or it amounts also to the same by saying that GM operates on F and that locally on F, for the topology you're working with, F is isomorphic to GM operating on itself by left or right translation. I mean, that amounts to the same because GM is commutative. Whenever we have a sheaf of groups G operating freely on a sheaf F, and then when we look at the quotient F over G, then F can always be viewed as a torsor over F over G for this T if you want, this T with group G over T, sehen das image of G on T, viewed as being a group object over T. And that's general nonsense of sheaf theory, which works in fact also in arbitrary topology, but here ordinary sheaf theory is essentially enough for us because we do it on all of the spaces as prime. And now to terminate our description of the situation, I recall that there is equals of categories of torsors over for given matrix S of torsors under the group object GM, the multiplicative group, which is in fact a scheme over S endowed with a group structure over S, and the category of locally free sheaves of rank 1 over S. They are associating to every locally free sheaf of rank 1L, the torsor of all whose underlying sheaf functor, if you want, is a set of all isomorphisms of OS with L. Of course, on this, the set of automorphisms of S operates by composition. So I think you should perhaps think a little bit about this equivalence, which is quite an important translation from one language into another. Now, the point which I want to make is the following. If we use this equivalence on P on which we have just constructed a canonical torsa with group GM, so we get on P an invertible sheaf, canonical invertible sheaf, and now you make a guess which invertible sheaf it may be. Well, this invertible sheaf is the canonical one here on P. That's the L here. It's a canonical invertible quotient of MP. And in order to prove this, we can forget about P, and we do it on the functor. We do it on arbitrary S prime, which is mapped into P. And then it just means that if you have a quotient L of M lower S prime, then to give an isomorphism of between L and OS, which just means n point is an S prime of this, a section over S prime of this functor is the same thing as to give a lifting of this element of PS prime to V star of S prime. Namely, this means that the quotient considered of MS prime has been deduced from an epimorphism of MS prime to OS in the way considered. But that's all. I mean, turned out to be a complete tautology. Once we translate back things in the universal situation to relations on the functor. So that's, I mean, the kind of game, back and forth, that one has to play all the time if one wants to be at ease and to seize with proper generality the relations between geometrical objects. So I think we have to stop. So tomorrow we are going to represent, to give us some more important examples of representable functors, including other products of schemes over another. And now in 10 minutes or so, we're going to start speaking a little bit more about group schemes. I got a few echoes from the last talks, so it seems that the introduction document is getting kind of painful and obscure to an increasing number in your audience. So I don't know too much who I want to do about it. So is it worth it? The first time repeating all the things we said once more again, or just go in and kind of hope that finally by accumulating some number of examples.
I think you forgot this time to give the examples.
Well, I mean, projective space is an example. So that's the kind of examples I was filming.
No, but I mean examples of spectra. For instance, distinguish those who can be interpreted in classical language or those who cannot be interpreted in way. Like that.
Well, I mean, if neither I nor anybody in the audience knows the classical language, or there are very few, I think, who do, so I don't think it would help so much. I mean, in a way, the whole setup in a way is, of course, it's related to the classical things, but it's technically quite different, because we never see the difference whether there are nilpotents or not. I mean, we just write the equations and divide by the equations, let's say, and we write down functors that represent the functors. And we never stop to bother whether or not what we get is whether schemes we get are reduced, whether even whether they are finite type, let's say, over ground field is for us a secondary matter. So it turns out that this works in a way very smoothly, except that I have psychological blocks which come from this systematic use of the functorial language. But however, this is very, very close to the geometric intuition, but one has just to get this point. I mean, the idea is that any relation between schemes, you see one scheme lies over another, is fibered over another in a certain way, it may be a torso with structure group GM or such a thing, and certain relation between morphisms of schemes. So, how do we express them? Well, the schemes, we express them through their points with values in arbitrary rings, namely through the functors. And all these relations are expressed by relations between the functors, in fact, essentially between the points. With the structures we have on the points, for instance, there may be a group structure on some set of points because we have a group object, and this group may operate on something else, on some other, this group object may operate on another scheme. Let's say this means that the sets of the group which we obtain will operate on a certain other set which defines functorial on K prime, etc. And everything is just plain under the eyes. Now it turns out that practically, really, almost all schemes one has to work with, when one wants to do them geometrically, you see, not sticking to any particular set of equations. I mean, the way they are described is through the functors in a domain. Through their points after all. But not only points with values in a field. I mean, that's the typological difference, it seems. That's the block. They points with values in any K prime, or even points with values in any scheme, let's say, instead of an affine scheme, a spectrum of K prime. And we work with these points. But sometimes we come back to the schemes and we remark that whatever relations we have established between those functors, which are essentially set-theoretical relations, well, there are no relations between schemes and between local ring spaces. And then we can exploit these relations by looking again on to the spaces. That's the whole thing. So, for instance, for projective space, take it over field, why not? So Pn, which would be the projective bundle associated to Kn plus 1. So even working over a field and taking vector space of finite dimensional field and taking standard projective space, it is important to know if you have any algebraic variety in the most classical sense, whatever, it may be non-singular, it may be projective, embedded in a very explicit way in projective space, never mind. So whether the setup is classical or not, it's quite important to know how to characterize morphisms from X into projective space. How are they described? Now, if we view projective space as being formed by gluing together n plus 1 pieces which are affine, then it would be very unpleasant to express this, because this would mean to give a morphism of X into projective space, we have first to decompose X as a sum, not the disjoint sum, but the union, let's say, of open subsets Ui, and for every Ui to give a morphism of Ui into the corresponding affine piece Vi isomorphic to K to the N. And then we have to check that these things in the intersections kind of match, and then we have to check. Then having defined a morphism from X into Pn, we have to check that the UIs are effectively the inverse image of the VIs which we have here. And all this, doesn't give us any insight into the geometric significance of having a morphism into Pn. We just get lost in crowds of indices, and we have lost track of the geometric content of the situation. Now what I say is the following: to give a morphism from X into Pn is first of all to give oneself an invertible sheaf L on X. Now that's a very sound geometric object. It has a lot of things to it, invertible sheaf on X. And second, to give a set, in this case it would be a set of n plus 1 sections, Si, I between 1 and n plus 1, sections of L over X, in such a way that these sections of L generate in every point the invertible sheaf L, so that at every point at least one of these sections should be different from 0. Because when I have said this, or if you prefer, to give a homomorphism of the vector space K to the n plus 1, that's the vector space we have taken as projective bundle associated to into this vector space over K. Because to give such a homomorphism is the same thing as quite evidently than to give a homomorphism of Ox to the n plus 1 into L by giving the images of the n plus 1 basis elements of Ox in L, and to say that the SI together generate L means that you have an epimorphism. That means that L can be interpreted as being a quotient, invertible quotient sheaf of Ox to the n plus 1. So here we have exactly expressed what is the morphism of X into projective space. And that's something intrinsic. And we really do work with this all the time, with these kind of interpretations. So, of course, I mean, this is nothing new for anybody, for the old timers. I mean, they know that to map a variety into projective space, that's the same thing. Well, they wouldn't say invertible sheaf because they don't have sheaf theory. They will say that's the same thing. Yes, with a linear system of dividers. And yeah, linear system of dividers. And well, there's a dictionary, which is where in fact the language is translated to is slightly less accurate because various factors which I don't want to describe here. So that's about it. I mean, when you have said this, you have described projective space, because when you know what are the morphisms into projective space, you know what is projective space, because you know the functor the projective space represents. And the same, I mean, is true all the we have given about a dozen or two of specific examples of schemes. I mean, at the beginning when we had only affine objects, well, they were all represented by rings. But I mean, all these schemes which we gave, I mean, all these group objects, for instance, they're all given in terms of the function. And that's the way to understand what they are. If you give them by equations, you won't understand what they are. I mean, by explicit equations. Once you have a bunch of equations on the blackboard, I mean. So that's the philosophy, which, by the way, is not only has become, I think, really essential in order to dealing with algebraic geometry. Otherwise, you just get lost. You can't do the things. But I think it's quite useful also in other contexts. For instance, in analytic geometry, it's quite useful. I have given an outline of the yoga in Carton's seminar about 10 or 15 years ago. And I mean, the yoga of representative functors is essential. And I think even any context of algebra or geometry is quite useful. So I think it's worthwhile and insofar as mathematics perhaps is not worthwhile. If one likes to do mathematics, or if one has to do mathematics because one needs a degree or a salary or whatever. So when it's in the logics, let's say, of the present evolution of mathematics to do this kind of stuff. That will be done for a very long time still. Alrighty, so maybe I should go on now, perhaps giving a few more comments on this example of projective bundle, and then give a few more other examples of representative functors. So I took the more general case, so no ground field, no ground ring. I have a ground scheme S. On this ground scheme S, I have a quasi-coherent sheaf of modules M, and the functor I'm going to represent by the projective bundle P of M associated to M. That's the functor which associates to every S prime lying over S, the set of all quotient sheaves of M lower S prime that are invertible. So it's just this is a set also of, if you want to express it in this way, of isomorphism plus of following things, an invertible sheaf, plus a homomorphism from M lower S prime into L, S prime is free by any chance. That means that the sections of L corresponding to the basis elements of MS prime. That means if M is free, let's say, if we have basis sections of M which make up a basis, that means that corresponding sections of L make up a set of generators of the sheaf. That's a sheaf of modules. All right. Now let's see a little bit how this projective bundle behaves when we make, let's say, a base change. So let's make a base change S prime goes to S, and let's see what is a priori the functor deduced from the functor Pm over S by making the base change S prime goes to S. In fact, we will see, I hope today, that fiber products exist inside of the category of all schemes. So that the fiber product which I'm writing here, we would know then, if we know the theorem, that a priori we would know that it's a scheme. But I will show something more precise. I will know that this scheme, in fact, is obtained in the following way. I take the inverse image of M on S, MS prime, as I did before, and I take the projective bundle associated to it. So I will show that this projective bundle is a fiber product, that it can be viewed as being deduced from Pm over S by base change. I don't even have to know that fiber products exist in the category of schemes. So that's the most simple behavior one could expect. And I mean, this most simple behavior will hold throughout all the examples I will give. Everything will work out very, very smoothly. So what does this mean? This means to make the fiber product in the category of sheaves or in the category of functors that amount to the same, of pre-sheaves, on the category of all schemes over S. It's the same thing when S2 takes the restriction of the functor Pm, which we have over the category of schemes over S, to schemes over S prime, and we use schemes S second over S prime as being schemes lying over S. That's general nonsense again about general categories. And I have already explained this point. All right. So we have to take the restriction of this functor here when we replace S prime, which now is fixed, by an S second prime over S prime. So I have to take this. But of course, here I take the inverse image of the sheaf M on S second, viewed as lying over S through the compositor morphism. But to take this inverse image, I can first take its inverse image on S prime, and then take its inverse image over S second of this one. Therefore, this MS second here can be viewed as M prime, called MS prime, called also M prime, to make it still clearer, lower S second. So, and therefore, the description we have here is the description of the functor, which we call the projective bundle associated to M prime. All right. So, nothing more than this. Let's give an example. Take the base change, where S prime is just reduced to one point, which is a point of capital S, and where we put as a structure sheaf on this one point space, we take the residue field kappa S of small s. And for the homomorphism of ring spaces, because we have also to define the homomorphism on the sheaves, we will take the homomorphism of the stalk of the sheaf, structure sheaf of S at the point S, which is a local ring, the canonical homomorphism of this, onto its residue field. So in this way, every point of a scheme S can be viewed as a scheme in its own right, endowed with kappa S as the unique stalk at this point, and scheme lying over S as a natural morphism from S, small s into capital S. All right. So, and whenever we have a scheme X over S, quite generally, I mean, intuitively we view the scheme as being something like a family of schemes over fields parameterized by S, by associating to every point S and A, capital S, by associating the so-called fiber of X at the point S, which will be a scheme again, which will be a subfunctor of X, just as it's the one that is deduced from the scheme small s mapped into capital S by the base change. Alright, we are not supposed to know that fiber products exist within the category of schemes, but this we will see a little later. So X over S, this fiber will be a scheme itself. And in fact, set theoretically, it will be just the inverse image of the point S by this morphism. It will be, the underlying set will be just the set of elements of X which maps to the point S. So this, and by the way, the topology of XS coming from scheme structure will turn out to be induced by the topology of X. So really, I mean, from the topological point of view, it's this point of view of viewing X over S as being a family of schemes parametrized by capital S from the topological point of view. That makes perfectly good sense. The fibers here, XS, however, are not only topological spaces, they are schemes. And now, whenever we have defined a scheme over S, it's interesting to ask ourselves, what are the fibers? So, what are these fibers in this family of fibers? Of course, XS can be viewed as being a scheme over small s, in other words, as being a scheme over the field kappa S. But here the ground field for these various fibers a priori will vary with the point which we have in capital S. So I will put the variable residue field. Alright, now let's do this in the case of the projective bundle. What are its fibers? So it's just a particular case of base change by just a scheme S prime equals to S reduced to one point, which is the point of S, the way I've explained. And the fiber is obtained by taking this inverse image of this sheaf of modules M on small s and taking the associated projective bundle. But now MS is a vector space over kappa S. And what is this vector space? Well, M of S equals M cancelled over OS with kappa S. That's also obtained the following way. I take the stalk of M at the point S, it's a module over the local ring, and I reduce it module maximal ideal. I take a tensor product over the stalk with kappa S, which is also equal to MS divided by the maximal ideal of at the point small s multiplied by MS. So that's a vector space. In the same way as I view, let's say, heuristically speaking, a scheme over S as being a collection, a family of schemes over the various residue fields parameterized by S, a sheaf of modules M over S we view as being a family of vector spaces over the various residue fields parameterized by S, and these vector spaces are these vector spaces which I've written down here. And it turns out that the projective bundle associated to M, its stalk at S, is just the usual projective space, so to say, projective scheme or whatever you like to call it, associated to the vector space M of S.
Is this a closed embedding that case? Fiber? Is it closed?
No, because it can't be closed and unless S in capital S is closed also. But we take such points as general points.
So,
whenever S goes to capital S as a closed immersion, that means in fact that the point S is closed in the space S. Then, I mean, by base change, this will be a closed immersion too.
Because in classical algebraic geometry, let's say, always the image of a projective space is closed, right?
Yeah, but it's somewhat different here because you should, yeah, of course, but it's what will be true. I will tell you. What will be true is the following: if you have projective bundle over S, you see, and you have any scheme X over S, the same S, you see, not small s but capital S. You don't change your basis; then you change your basis. And if you have any S morphism from Pm into X, then this is a closed morphism. The image of P and X will be a closed subset of X. That's true at least if X is separated over S. One has to be a little careful. I have not yet defined the separation condition. But I mean, in classical algebraic geometry, all algebraic varieties are separated. In fact, they're quasi-projective, they're embeddable in projective space. So there is no problem. So with this little proviso that X should be separated over S, it's true that any morphism, S morphism into X, has a closed image. But here you see there are two different bases. And I mean, if this what you said was true, it would be true, for instance, if M is the free module of rank 1. But then the P, the projective bundle associated to the free module of rank 1, I mean, it's into the projective space of dimension 0 relative to S. In fact, it's S itself. And in this case, your statement would mean that the inclusion of S and small s and capital S is a closed embedding. But I mean, you take a general point of S, and a generic point of S, let's say, if S is irreducible, I mean, this point is not closed in S, unless S is reduced to that point. So we can say that the projective bundle over S, it's just the collection of the projective bundles over the various vector spaces over the radio fields that stem from the sheaf of modules M.
Are the projective spaces complete here? Are the projective bundles complete? That is, if you take product and projection on the second factor, it shows.
Well, I mean, that's equivalent to the question whether here the image is closed. They are in this sense, except that as I took very general M's, I didn't make any finite assumption on them. They won't be of finite type, you see.
But even there, it will be complete.
Yes. In this general sense that, yeah, that's a morphism into anything that is separated over S will be closed, and that's the same thing will be true after arbitrary base change. I mean, that's the business about your taking product. Base change is just a product of S. Yeah. Maybe, yes, we should make a little, well, let's first finish this dependence of projective bundle on M. So we have seen what happens with space change. Now we will see what happens if S is not changed, but if M is changed. All right. So let M and N be two quasi-projective modules over, quasi-coherent modules over S. So in the case when S is affine with ring K, this just means that we have a homomorphism of K modules from M into N. And we wonder, can we describe, associate to this a homomorphism, a map, a morphism between the associated projective bundles? And of course, we expect the arrow to be in the opposite direction, the way to be defined projective bundle associated to a module was kind of contrary with respect to the module. Instead of taking lines, we took hyperplanes. So we want to define something like this. So let's recall what the two functors are, what the points are over any S prime. So we have to take on the one hand quotient modules of NS prime that are locally free of rank 1. And on the other hand, you have to take quotient modules of MS prime which are locally free of rank 1. So either arrows epimorphisms like this, where L is an irregular sheaf, or epimorphisms like this. And of course, the natural thing to do is whenever we have an epimorphism like this, to take the compositon with this, and certainly what? Well, the compositor, we would like it to be an epimorphism. Now, it may not be so unless we make some assumption on this, unless we assume essentially that this is an epimorphism itself. And therefore, we will assume that M goes to N is an epimorphism. This is epimorphism of sheaves. In this case, well, any quotient sheaf of NS prime can be viewed, if you want, as a quotient sheaf of MS prime, because NS prime itself is a quotient of MS prime. All right, and therefore, we have a natural embedding of Pn and Pm. It turns out, it's easy to check, that it's a closed immersion. But I have not defined closed immersions yet, so let's not insist too much on this point. Pn is embedded as a closed subscheme in Pm. We have defined the notion of closed immersion only for affine schemes. All right. So if we take the category of quasi-coherent modules over S, where we take the morphisms only the epimorphisms, then we see that the projective boundary associated to M depends as a constraint functor on it. And if M goes to N is not an epimorphism, then in fact there is no natural way to map Pn into Pm in a way, in a natural way. What we get is only what we can define then is a certain open subscheme U of Pn, an open subset with a U structure, and a morphism which goes from U to Pm. So in classical terms, it would be a rational map from Pn to Pm, and U would be the set of points where it is defined. And I can tell you what this open subset is, what is the functor that it corresponds to. Well, that is the set of all homomorphisms, epimorphisms of Ns prime onto invertible sheaf L, such that the compositum happens to be an epimorphism too. It turns out that this is an open condition, that this subfunctor of the functor Pn is represented by an open subset. I mean, we do, at every step, we do just the most evident things that come to mind in order that things make a sense. Yes?
Some problem with M being 0, 0, 1, 2, 3, 4, 0.
Well, if M is 0, Pm is the empty scheme. That's true. Yeah, let's see. Why not make the checking, you see? We have to take, if M is 0, then its inverse image on S prime is 0, and we have to take all quotient sheaves of 0 lower S prime, which are invertible. But unless S prime is empty, there is no such quotient sheaf, you see. Because you don't have an epimorphism of the 0 sheaf onto a sheaf which is locally free of rank 1. The rank should be at most equal to 0 if we have an epimorphism on a non-empty scheme. That means that our functor has value empty set if S prime is non-empty, and if S prime is empty, well, in this case, I mean, all sheaves on the empty set are the same, and the functor is a one-point set. And we have seen that this functor is just the functor represented by the empty scheme. Let's take the example of when we take M to be OS, as we are taking. So these are the examples. So we will complain. So what are the quotient sheaves of OS prime? The inverse image of M on S prime is OS prime. What are the quotient sheaves of OS prime? That are locally free of rank 1. So what are the epimorphisms of OS prime onto sheaf L? That is locally free of rank 1. But if it's an epimorphism, because these are locally free sheaves of the same rank, it must be an isomorphism. And therefore, this means that this quotient sheaf of OS prime is OS prime itself. That's exactly 1. So our functor has for every S prime as a value a set with just one element. But that means that it's the final functor. That means that it's a functor represented by S itself, the final object of the scheme over S. So the first, so to say, non-trivial case, interesting case is taking three modules is M equals OS squared, and in this case we get the projective line, the standard projective line over S.
Excuse me, can you say again what is that open set U?
I will define what the functor is U of S prime for value S prime. I mean, when I know this functor, I know the sub-object. It will turn out that it's represented by an open subset of Pn. So US prime equals the set, it will be contained in P of n, it's a set of all invertible quotients L of ns prime, such that the compositum ms prime goes to ns prime, which is reduced by base change from u, that we got here, us prime, goes to L, is an epimorphism. So that L can be a quotient of ms prime also, and therefore on this that's exactly the largest subfunctor on which we can define in a natural way a morphism into Pm, which would be kind of contragradient, transpose, I'm sorry, kind of transpose to the homomorphism M goes to N. And that's, of course, when we are in classical setup with S a field and K vectors with defined dimensions. This open subset is really a subset where a certain rational function is defined. The old timers, anyhow, I mean, the models didn't even exist for old timers. They had rational functions, and then they said that well, a rational function is defined in this form. They defined it for it. Was kind of the philosophy was kind of different.
U is an open subfund of P of M.
Yes, so do this as an exercise perhaps. It's pretty easy. It's an open condition. The fact you see that the morphism from a module into some L should be an epimorphism is a pointwise condition you see it. That a subsheaf of L generates L because L is locally free of rank 1 of. In fact, it would be enough to be in fact, it would be true whenever L is of finite time. It's a pure local condition. It means that when you reduce the mathematical idea, it is so. Therefore, it's associated to a subset of Pn. And now you have to see that the subset is open. This means that if a bunch of sections, local sections of L generates L at a point, it generates it in the neighborhood 2, right? Of course, this homomorphism between projective bundle associated to M goes to N is compatible with space extension. In an evident sense. The homomorphism deduced from this one by base extension from S prime to S, when we interpret the inverse images of these as being the projective bundles associated respectively to MS prime and NS prime, is exactly so in embedding which is associated to the homomorphism of modules over S prime. Alright, I guess that for the sequel it's not worthwhile noting too many of these compatibilities. Every compatibility that suggests itself to mind, I mean, is true here, and is trivial moreover. So, what examples have we seen? We have seen the projective bundle associated to a sheaf of modules. We have seen the vector bundle associated to a sheaf of modules. And we have seen the relations between the two. Let's define perhaps something which is associated with a sheaf of algebras. Let A be a sheaf of modules on S, which is moreover a sheaf of algebras, of commutative algebras. Call it A. I assume that A is quasi-coherent as a sheaf of modules, and moreover it's a sheaf of algebras. It's an OS algebra, understood commutative and unitary. So in case when S is a spectrum of a ring K, then to give a quasi-coherent sheaf of modules over S is just the same thing as to give a module A over K. Now what does it mean to give an algebra structure on A? It means that you give a homomorphism of the tensor product of A by itself over OS into A, satisfying certain axioms. But the tensor product of two quasi-coherent sheaves is also quasi-coherent. It's in fact the quasi-coherent sheaf associated to A tensor A over K. And to give such a homomorphism, because of our dictionary, is just to give a homomorphism like this of K modules. That means that I have a bilinear pairing of A times A into itself. I have a multiplication, bilinear multiplication. And of course, so I have a general algebra structure without axioms so far, except by linearity. And to say that this here is associative means that this here is associative, that this is commutative means that this is commutative, that this has a two-sided unit means that this has a two-sided unit. I mean, the dictionary works very smoothly. And therefore, a commutative algebra structure on A is just the same thing as a commutative algebra structure on the K module A. And that's a general setup. And maybe it's worthwhile systematically, to replace now ground rings and algebras over it by ground schemes S and sheaves of algebras over it that are quasi-coherent as sheaves of modules. And I want also to associate to this algebra the spectrum of A, which would be a scheme over S, in such a way that in the particular case, when S is affine with ring K, and if the sheaf of algebras is associated to the algebra A over K, that this should be just the spectrum of A, which lies over spectrum of K, because A is a K algebra. So I want to generalize this construction of the spectrum in the relative case. And therefore, I mean, just as in the affine case, we had to here we describe spectra by the functors that they represent, so here we'll do the same thing. So there's an x we want to define, and therefore we'll define the functor. So what should be x of S prime? All right, in the affine case, S prime was assumed to be affine to 2. So it was just to give an S prime was just to give an algebra K prime over K. And what we associated to A was the set of all algebra morphisms of A into K prime. K prime. So the obvious thing to do here is now to take the set of all OS prime algebra morphisms of AS prime, the inverse image of our sheaf of algebras on S, which gives us a sheaf of algebras on S prime, into OS prime. Because of the dictionary I have explained on K, I mean by doing the same dictionary over K prime, we see that the K prime homomorphism of algebras of A prime into K prime just correspond to these homomorphism of sheaves of algebras. And on the other hand, algebra homomorphisms of K prime algebra homomorphism of A prime into K prime correspond just to the K algebra homomorphisms of A into K prime. If you want, you can also write this as being the homomorphisms of OS algebras of A into OS prime, but now the sheaves lie on different spaces, one on S, the other on S prime. And where I take homomorphisms which are associated with a given morphism of Riemann spaces. All right. So, and this, of course, is a functor for variable S prime, and I have to show that this functor is representable. All right, now how are we going to do this? We are going to reduce to the case that is affine by the lemma which we have seen last time, namely that the question of representability of a functor over S is a local affair on S, so that if you cover S by open sets Si, if S is a union of open sets Si, you just have to prove that the restriction of our functor to each of the SIs is representable by a scheme over Si. So we take the SIs to be affine. If you want, we take the covering of S by all open affine subsets, if you want. And what's the induced functor? Well, it's essentially the same functor, except that now S prime is supposed to lie not only by S but over Si. And where we replace the algebra A by its restriction to Si, call it AI. But in the affine case, I mean, we have already the solution. The algebra, forget now about I and assume now S to be affine. So S corresponding to a ring K, Grothendieck A corresponding to an algebra A over K. We know that the functor which we have just written down, at least if we restrict it to affine S primes, maybe to spectra of rings, so that we may consider it as a functor, covariant functor from rings, from K algebras to sets, is representable by the spectrum of A. Now, on the other hand, we know also that to represent the functor on affine schemes or on all schemes is the same thing, provided we are certain that our functor is a sheaf for the Zariski topology. Because then the category of sheaves on the category of all schemes over S, or the category of sheaves on the category of schemes over S that are affine over, they are just different categories. Alright, so is this functor here a sheaf for the Zariski topology? In other words, is this kind of objects that make up XS prime, homomorphism of AS prime to OS prime, are these local affairs? Do these things mesh together? Quite obviously, yes. If S prime is covered by open subsets, S prime alpha if you want. Then to give a homomorphism of that by AS prime into OS prime is the same thing as to give it by each of the S prime alphas in such a way that they mesh in the intersections. Alright, and that does it. And moreover, we see that the inverse image of the spectrum of A, so therefore the spectrum of A, which we defined as a functor, is in fact a scheme over S, called X now. And we know moreover that the restriction of X, the part of X lying over any SI, called Xi here, is an affine scheme. In fact, it's a spectrum of the ring AI. Xi is just a spectrum, therefore, of the ring of sections of the sheaf A over the open set Si. And that's true for any affine open subset of S. So we have a very thorough description of the spectrum. But here, moreover, we have some we have something extra which is suggested by the affine situation. You see, the spectrum of A depends as a congruent functor on the variable ring A over K. And in this way we get A goes to spectrum of A, we know, is a fully faithful functor going from the category of K algebras, or rather the opposite category of this, to the category of schemes over K. In fact, it induces an equivalence between the opposite category of K algebras with the category of affine schemes over K. That is, we can reconstruct, for instance, this implies up to canonical isomorphism, the algebra A over K by knowing the associated scheme over K. And now we want to establish the same thing in this relative situation, and an arbitrary ground scheme instead of an affine ground scheme. So first of all, we have to see how the spectrum of A depends for variable sheaf of algebras A. So we have to see what happens if we have a homomorphism of sheaves of algebras. A goes to B, both quasi-coherent over S. Alright, I claim that then we have a natural homomorphism associated to it, which goes from a spectrum of B to the spectrum of A. And why is this? This comes from the fact that whenever you have an S prime over S, then any homomorphism of B into OS prime, compatible with the homomorphism of linked spaces, induces by composition homomorphism of A into OS prime, and this is controlled for variable S prime. So we have a homomorphism between the functors and therefore a morphism between the schemes. So this shows us that the spectrum of a sheaf of algebras depends functorially as a congruent functor on the variable sheaf of algebras. So let's write it. We have the category of quasi-coherent algebras over OS, quasi-coherent OS algebras, that makes us a category. And we have a functor going from this, the opposite category to this one, into the category of schemes over S. The functor being A goes to the spectrum of A. And now what I contend is that this functor is fully faithful, and I will say what the like image is. So, first of all, this functor is fully faithful, and second, the essential image of this functor consists of all schemes x over s. So such a scheme is, I say, is isomorphic to some spec A, if and only if, well, if S was affine itself, you would say if and only if X is affine. That's what the affine theory tells us. So here I have to relativize the notion of being affine when the basis S is arbitrary. And here the condition is the following: if and only if, for every open subset U of S, U being open and affine, the inverse image of U by the structural morphism from X to S, the part of X lying over U, is affine. So these schemes over S are called schemes that are affine over S, that are affine relative to S. And a morphism from a scheme X into another, they are called, so definition, schemes X affine over S. That doesn't mean that they are affine in the absolute sense, that means that they are affine relative to S. Or else we say also that the morphism from X into S, which turns X into an S scheme, is an affine morphism. So we have relativized the notion of affineness to a morphism instead of a scheme in the absolute sense. Of a relative scheme, where the basis need not be affine. Now let's give an indication of the proof. Let's first show that this functor has its image in the category of schemes that are affine over S in this sense. Alright, so maybe I should remark the following thing. It's that if we take the spectrum of a sheaf of algebras A over S, and if we make the base change by some S prime over S, and we get here X prime equals X times SS prime, maybe we know not as yet that it's a scheme itself, if we don't know the existence of Hilbert product within the category of schemes, but at least it's a sheaf, it's a functor, and I claim that this is in fact the spectrum of AS prime. So therefore it is a scheme. And the proof is exactly the same as was analogous statement for projective bundles. You just see that the restriction of the functor represented by spec A is over S is the functor of S prime represented by spectrum of S prime. Just an tautological identity of functors. Alright? And in particular, if S prime is an open subset of S, then X prime, the Hilbert product, is of course the part of X lying over S prime. And therefore, in order to prove that this functor takes its values in those schemes over S having this property, we are just reduced to proving that if S is affine itself, then X is affine by replacing S by any affine open subset. And this we have already seen in the construction of the spectrum of machine algebra. If S is affine, then the thing that we constructed is affine. Alright. Therefore, let's call these schemes, the pattern of these schemes over S that are affine over S, let's call it aff scheme over S, something like this. be careful, it doesn't mean that these are schemes that are affine, that are moreover endowed with a morphism into S. These means that we have schemes endowed with morphism into S, and that turn out to be affine over S, not affine in the absolute sense. And in order to prove that this now, therefore our theorem says that this is an equivalence of categories. So that's what we have to prove, and it maybe the handiest way perhaps is to describe the functor that goes into the opposite direction, and then to prove that the two functors are inverse of each other. And so let's put this as third part of the statement. The crazy inverse functor that means the functor such that the two composita here are isomorphic to the identity functors is, up to unique isomorphism of course, the functor which associates to every x over S the direct image by the structure morphism of the structure sheaf of X. So it turns out that if X is affine over S, then the direct image of the structure sheaf of X, which of course is a sheaf of OS algebras, because we have a morphism of ring spaces, it turns out to be quasi coherent. Therefore, it's in this category here. And in this way, of course, it depends on the consequence way on X. If X is mapped to X prime, then the direct image of OX prime is mapped to the direct image of OX, because function on X prime are mapped to function on X. Alright, so we certainly have a functor like this once we prove that f bar of X is quasi coherent. Now let's prove this. That's a local affair, the quasi coherence of a sheaf over S. So in order to check it, we can assume S to be affine, because everything we do commutes with space change. So we make the base change of S prime goes to S, where S prime is an affine open set. So assume S is to be affine. But in this case, how do we get the direct image of this functor? Well, X, now the assumption that X is affine over S means, because S itself is affine, that X is affine. Therefore X is written corresponds to a corresponds to a ring A, to an algebra A over K. And zoomorphism from X to S is just zoomorphism is transposed of this morphism between the rings. But we have seen that the direct image of a sheaf, which is of the type M tilde, where M is any A module, is the sheaf M tilde, but when M now is viewed as being a K module, and we make the restriction of scalar. So it's quasi coherent therefore. And in fact, it's in this case, when we take M to be A, and we take the structure sheaf of X, it's just A itself. Therefore, the direct image of the structure sheaf of X by the structure morphism is just A tilde, where A is viewed as being a sheaf of as being a K algebra, as being a K module, I'm sorry. And of course the algebra structure of the direct image comes from the algebra structure of the K module A. Alright, so I have the functor in this direction, and we have now to show that the compositor of these two functors in these two directions are isomorphic to the identity functors. Now this is kind of trivial, you see. Everything boils down to verification in the affine case. I think I won't do the verification on the blackboard. It's really a little chore of minutes of the same order. It's just checking. But I mean, it's tautological once one writes down what it means. Everything boils down to the affine case, where it's contained in the general dictionary, affine dictionary. if you want as an exercise, you can relativize the general nonsense we said about distributions on an affine scheme over K, over ring K, by taking affine schemes over ground scheme S, and by speaking then of the function of distribution on X, which is a function which contains X as a subfunction, which is various funny properties. Alright, so now let's come to something more basic, in fact, to the formalism of schemes. That's inverse limits of schemes. So that's another application of the representability theorem. Let's prove the theorem that finite inverse limits exist in SCH, or what amounts to the same in each of these categories SCH over S. Of course, they always exist in SCH head, category of all functors, and we know already that these inverse limits, in fact, schemes being identified with functors that are in fact sheaves, these inverse limits will be sheaves also. But the point is that these sheaves are representable. For infinite inverse limits, it's no longer true that they exist inside of the category. It's true in certain cases. So we will give one interesting case where it works. But for the time being, I mean, the most important is really this here. So finite inverse limits in a category just means that A, there exists the final object, and B, that there exist finite products. Now a category, final object in the category of all schemes, that's just the scheme spectrum of Z. You see, or more generally, if you take the category of all schemes over S, where S is any ground scheme, the spectrum of Z is just, I mean, arbitrary schemes are just schemes over Z. Z is arbitrary ground, is, I mean, the universal ground length. In the same way, means the final object of scatter of all schemes over S is S itself. This is purely tautological. So this here, the tautology. Now what about finite products? Here, the situation is the following. We have a diagram X and Y go to S. We look at the finite product in the category of all functors or all sheaves. Is just isomorphic to xi times siyi. Therefore, the lemma of localization on S tells us that if S is covered by open subset Si, and if for every I the finite product of xi and yi over Si is a scheme, then the finite product of x and y over S is a scheme too. Alrighty, so this reduces us to assuming that in the case when S is affine, S can be covered by affine open sets. So first reduction, we may assume S affine. Alright, now we will do the same kind of reduction on X and Y. Assume that X is covered by open sets xi, and that y is covered by open sets yj. Then taking the Cartesian product over S of the inclusions of xi and x and yj in y, I get inclusions of xi times over s yj into x times sy. course, the Cartesian product of monomorphisms is the monomorphism. You get subfunctors like this. And the statement which comes next is that x times over sy is a scheme if and only if these here are schemes. That's a priori statement which I will prove. Well, this comes from the fact that these subfunctors, call these, if Z is a private product, call these subfunctors Zij if you want. Well, the morphism of these subfunctors into Z first of all are open immersions. And that moreover, Z is a supremum of the Zij's. So we have these two statements, which I will check in a minute. And therefore, if we apply our lemma, we see that Z is a scheme if and only if the Zij's are schemes. And in fact, we will then know that the Zij's are open subschemes of the scheme Z, whose union is the whole of Z. Now, why is this an open immersion? Zij goes to Z. So I can drop the indices if I want. I just take an open subset here, an open subset there, and I take the functor from U times over SV, let's say, goes to X times SY. So U being open in X and V being open in Y. And I say that this morphism of functors is an open immersion. Well, so what is a functor here? It's a functor which associates to over S prime the set of morphisms, of pairs of morphisms of S prime into X and into Y. S prime varies as a scheme over S here. So when I assume that we have such a morphism, and I now should look at the private product of S prime and U times SB over this here. And this will be some sheaf a priori, call it W prime if you want, contained in S prime, and I want to show that this is an open subset. It's an open subscheme of S prime. And what will it be? So I have a morphism of S prime into X, another of S prime into Y. That's what expresses this arrow. And I take the inverse image of U, call this morphism here for F, G. And W prime, in fact, will be the intersection of F minus 1U and G minus 1V. I claim that this open subset of S prime, viewed as being an open subscheme, is the private product. And that's, again, pure tautology, because if you have an S second, you see, we must see what it means that we map S second into S prime in such a way that the compositum factors through the subfunctor. That means, however, to give a morphism from S second, so I look at the compositum with X times Sy. That means if this morphism here is U, I look at the pair of morphisms Fu, Gu, which go from S second into X and into Y. What does it mean that it factors through this? It means that we can find a pair of morphisms of S second into U and into V, so that this here is deduced by it through the inclusions of U and V into X and Y. But that means that Fu and Gu factor through U and through V. But this means also that U factors through the inverse image of U by F and through the inverse image of V by G simultaneously. But that means that it factors through the intersection of the two. All right, and now what does it mean that these Zij's now cover Z That means that whenever we have a morphism from S prime into x times sy, then locally it can be lifted to one of the zij's. That's what it means. Or in other terms, that the inverse images of the zij's in S prime cover S prime. Now what is the inverse image of Cij? That's S prime ij equals f minus 1 of xi intersects g minus 1 of yj. Now if I take the union of all these here, I have to show that it's equal to S prime, but the union of all these is equal to the union of all f minus 1 xi intersects the union of all f minus 1 yj's, and because inverse images commute with unions, that's f minus 1 of x intersects g minus 1 of y. That's z intersects z. That's I'm sorry, s prime intersects s prime. That's just s prime. All right. So this shows us that the problem of representability localizes also on x and y. And now, I guess I'm through, because I now cover x by affine open sets xi and y by affine open sets yj, and I'm reduced to the case when x, y, and s, all three of them are affine. Now let's introduce the rings corresponding to these. Let's call them K, A, and B. So the diagram we started with corresponds to the diagram of rings. K goes to A and goes to B. We have two K algebras over two pairs of A and B. And the finite product of X and Y over S in the category of affine schemes, or affine algebraic spaces, we have already seen to exist in the same category, and it's the spectrum of the tensor product of A and B over K. So all we have got to do now is to prove that this object Z, which we now construct, is the spectrum of A tensor B, tensor product taken over K, that this spectrum is a finite product. So let's see. We have to see what the functor is. We want to present x times sy as a functor for a variable on with respect to variable s prime, which is therefore s prime is a scheme that varies over s. This is equal to xs prime times ys prime, which is equal. Now you have to take the morphisms of a scheme over K into the spectrum, namely S prime, that's the set of morphisms of S prime into X, into the spectrum X of an algebra A over K. And we have seen that this is just a set of homomorphisms of K algebras of A with values in the ring of sections of the structure sheet of S prime. And we have to multiply it by the same thing, but replacing A by B. So the value, the set, which is a value of our functor on S prime, is just a set of pairs of a homomorphism of A into gamma S prime OS prime, also a homomorphism, and another B of gamma S prime OS into gamma S prime OS prime. But such a thing corresponds just to, such a pair just corresponds to homomorphism of the tensor product A tensor B over K to gamma S prime OS prime. So let's write it down. This is a set of homomorphisms of K algebras of A tensor B into the same gamma. And this again can be interpreted as being the set of homomorphisms, of S homomorphisms of S prime into the spectrum of A tensor KB into Z. So we see that Z represents our functor.
Or A tensor A, B is an argument sum of A, B, A.
Yes,
Sure.
it's a tensor model of algebras, but it affects the amalgamated sum in the category of algebras, yes. But it's a tensor model as a module, and you put on this in a way an algebra structure.
So how come the first equality?
That's what we said once, you see. If we have an affine scheme X equals spectrum of some A,
So the very first
Back
one,
one.
very
Yeah.
first one is the definition of the.
that's the definition of the fiber product over S as being the product in the category of schemes over S. So that does it. We have finite inverse limits because we know that they are reduced to finite products and final object. Kernels, for instance, can be expressed in terms of finite products, etc. So, and I won't repeat here what I said about interpretation of finite products as being base chains. I mean, I've used it a number of times. It's something that works in arbitrary categories. And how base change can be interpreted as a restriction of a functor, X over S being interpreted as a functor for objects over S. Its inverse image on S prime is just a restriction of this functor to objects over S prime, viewed as lying also over S. So again, having finite products, we can take fibers, you see. For a point S in capital S, we can endow it with a residue field kappa S as a ring. And we have a morphism of schemes here. And the inverse image of X over S, it's a scheme over kappa S, which is called the fiber. Now, I like to leave it, I think you may do it as an exercise to show that X over S, of course, X over S goes into X, will be injective. It's in fact a subfunctor of X, because here this is a monomorphism. But also, therefore, a fortiori the set of points of XS is contained as a subset in the set of points of X, so it's injective in the space, but also the topology of XS is induced by the topology of X. I don't think I will check it here. You are reduced to the affine case, as you put it in the affine case, you did it, the affine case. You are reduced to it by covering X by affines. Perhaps I should emphasize upon the byproduct of our proof, of the preliminary steps in our proof, namely that the consideration of that the fiber product of two schemes over S reduces to the case when everything is affine, you see. Namely, if you want to visualize it in terms of clutching together affine pieces, you first cover S by affine pieces and you look at the inverse images of these to reduce to the case when S itself is affine. So let's assume this already. And then if X is covered by affines Xi and Y covered by affines Yj, then these products here, they are already known through the affine theory. They correspond to tensor products of algebras. And these can be viewed as open subsets of this here. They match together in a natural way. In fact, Xi times Syj by our proof is just the intersection of the inverse images of Xi and of Yj by the two projections of X times Sy to X and to Y. So that's how we obtain these open subsets. For instance, if you have an open, if X is covered by open subsets Xi, which you may take affine, this shows that the fiber Xs is covered by the fibers XIS, which are open subsets of XS. And this gives a reduction to affine case. And this way you will check that the topology of X is induced by the one of X. Now, taking finite inverse limits of schemes is one of the, probably the most trivial and also the most usual operation on schemes. I mean, all the time you're doing base changes, for instance. That's just finite products. That's a very, we have done it all the time already, by the way, doing base changes. Sometimes you wouldn't say so, but or restricting functors to S primes, you see. Yeah?
Could you say what you mean by finite inverse limits?
By what?
Finite inverse limits. I know what filtering inverse limits are.
But what inverse limit filtering? Finite. The set of the diagram that you take as a basis, you see, with a bunch of points and arrows between them, is finite. Finite number of points, finite number of arrows. For instance, taking finite products, finite products, that mean products of finite family of objects, taking kernels of 2 arrows of a bunch of a finite number of arrows. All these are finite inverse limits. Whereas infinite products of filtering inverse limits on an infinite filtering ordered set, these are not finite inverse limits. So I could give now the standard example. I mean, there's scarcely an existence of infinite inverse limits except in the case I will tell you. It's the following. We have schemes that are already over a scheme S, scheme xi's, and I assume that all of the xi's are affine over S, and they form a diagram. There are a bunch of arrows in between them. The xi, the indexing element here I is the set of, goes over the set of vertices in some diagram, a category for instance, something like this. And I look at the inverse limit of the xi's, which already exists as a sheaf, let's say, but then I claim that it's a scheme over S, which is affine over S. And here, the evident thing to do is to recall the equivalence between category of schemes affine over S and category of algebras over S that are quasi-coherent. It's an anti-equivalence if you want. So, therefore we would expect that this inverse limit, if it's an inverse limit in the category of all schemes, of course it will be an inverse limit in the category of all schemes affine over S, and therefore it should correspond to the direct limit within the category of sheaves of algebras. So be careful that the direct sum, for instance, would be the tensor product of the AIs. And now we have to check that this, first of all, that this is a quasi-coherent sheaf of algebras, but this comes from the fact that the category of quasi-coherent sheaves of modules is stable under all kind of limits operations. We can say, if you prefer, the following thing, that we have to construct arbitrary inverse limits. We have to take we can reduce it to arbitrary products and to kernels. Kernels we can already handle. It corresponds to co-kernels in the category of algebras. And now we are reduced to the case of arbitrary products, which corresponds to arbitrary sums in the category of algebras. Now these sums are interpreted in terms of commutative algebra as tensor products, infinite tensor products. And however, we can also say that to take an infinite product, I'm also taking the finite products corresponding to finite subsets of the set of indices, and then to take the filtering inverse limit. So here it would mean that in order to take the infinite tensor product of the AIs, we take the finite tensor products, we take filtering direct limit. Now we know that there is no trouble in the case of the finite operations. So in fact what we are reduced to is to look at the case of a filtering inverse limits of xi's, which means to the case of a filtering direct limits of AIs. And of course we know that if the AIs are quasi-coherent, then the dike limit, which is just the dike limit in the sense of modules also, is quasi-coherent. Because we have to check it only in the affine case. In the affine case, it comes from the dictionary between usual modules and sheaves of modules, which is, this dictionary is compatible with dike limits. All right. So, therefore, in our statement, we can reduce to the case of filtering inverse limits, and these, in fact, are the most important. This is the most important case. One important case is, for instance, that S is, well, never mind. In fact, I made these reductions in order to be sure that the sheaf A which we construct, the limit of the AIs, is really quasi-coherent. All right. Now we have to use a little extra fact in order to prove that the spectrum of this, well, the spectrum, of course, of A, call it X, is mapped into the Xi's because each of the AIs is mapped into A. And we know by construction that X is an inverse limit of the Xi's in the category of affine schemes over S. But it's not clear that it's also an inverse limit in the category of all schemes over S. In fact, it will turn out to be an inverse limit in the category of all local linked spaces over S. So this we have now to prove. In order to do so, we have to prove a little proposition, which I could have given at the moment when I spoke about affine schemes over S. Let X over S be an affine scheme over S, and let Z over S be an arbitrary scheme over S. Then the set of S homomorphisms of Z into X can be identified by functorially in a way compatible with space and everything you want to the set of homomorphisms of OS algebras of OS itself, of A, when X corresponds to A, X is a spectrum of A, therefore A is just the direct image of the structure sheaf of X by our previous theorem into the direct image of the structure sheaf of Z. So I denote by G the structural morphism of Z, and by F, let's say, the structural morphism of X. You see, I mean, this is a pretty natural statement, because if S is itself affine, then schemes over S are just schemes over K, K being the ring of S, and then S being affine, to say that X is affine over S just means that X is affine itself, and this statement just says that to give a morphism of a local linked space to scheme here, let's say, into an affine scheme is the same thing as to give in the opposite direction homomorphism of the ring corresponding to X, namely A, into the ring of sections of the sheaf. That of the structure sheaf of Z. So here we have this, and well, the proof I think should be pretty evident. We're reducing precisely to the affine case when S is not supposed to be affine yet. Because let's say the following. If we replace S by an open subset of S here, so we get both sides here become then functors with respect to an open subset of S, or variable open subset. And these are sheaves with respect to the variable open subset. To give a morphism from Z into X, or to give a homomorphism of sheaves of algebras, it's a local affair. And therefore, to prove that this morphism is bijective, we have to prove it only over the basis of open sets of S. Then it will be also bijective on the section, on the global sections. And this reduces us to the case when S is affine. Because the affine open sets in S from a basis. All right. So this is a little, so we can say in a way that the functor which associates to every quasi-coherent sheaf of algebras on S its spectrum is an adjoint on the devil knows which side of the functor which associates to every Z over S the direct image of its structure sheaf. Now let's come back to this question of infinite inverse limits. I don't really care whether they're filtering or not anymore. So we want to represent the functor Z goes to inverse limit over the same indexing category of homo Z xi. That's by definition the inverse limit functor of the xi's. And by our lemma, each of these homo Z xi's can be interpreted as being the set of homomorphisms of OS algebras of AI into the direct image of OZ. But now I have here homomorphism in the category of OS algebras. And I have to take an inverse limit of such sets of homomorphisms. But that's by definition of direct limits. That's the set of homomorphisms of OS algebras of the direct limit of the AI, but this direct limit of course being taken in the category of OS algebras into OZ. Now this direct limit we have given it a name. We call it A. And I tell you once more our previous lemma. This is a set of homomorphisms over S of Z into the spectrum of A, which we call X. Which means that our X represents the function not only in the category of all affine schemes over S, but in the category of all schemes over S. So let me make a last remark concerning all these examples that we have dealt with so far. So we have constructed a number of schemes. For instance, we have constructed the vector bundle associated to a sheaf of modules. We have constructed the projective bundle associated to a sheaf of modules. We have constructed the spectrum of a sheaf of algebras. In all these cases, we assumed our sheaf of modules and algebras to be quasi-coherent. We have constructed inverse limits, finite or infinite, according to the case. Well, it turns out that in all these constructions, the functors that we are representing, we viewed them as being functors on the category of all schemes over some S. But in a natural way, I mean, whenever we wrote down this functor, it made a sense if we viewed this as being functors on the category of all locally linked spaces over S. In fact, even over, when we extended it to a functor over all locally linked topoi over S, right? Never mind. They're kind of good objects, but maybe a little general. Fine. Now, when we viewed these functors on here, we saw that they were representable by these schemes, but you will see very easily in each of these cases that the proof shows that they are representable, and that the object we construct represents in fact the functor on the larger category of all locally linked spaces. So it just turns out that the catalog of schemes within the catalog of locating spaces is stable, very much stable under a certain number of operations, like taking certain types of inverse limits, including all finite inverse limits, or constructing functions like vector bundles associated to basic real modules, at least if they were not basic real, would no longer be true, or projective bundles associated to them as spectra, etc. In fact, the main ingredient of the statement, I mean, what makes the statement be true is that to give a morphism of any locating space Z into the spectrum of the ring A is the same thing as to give a homomorphism of A into gamma Z or Z, as we saw already. For instance, this statement, for instance, is not so silly. If, for instance, we are doing algebraic geometry over the complex numbers, then I mean there are very interesting local spaces over complex numbers that are by no means schemes. Let's say, for instance, differential varieties or analytic varieties or such things. And the morphisms of these into schemes are quite interesting. And so it's a kind of trivial remark here, but it's technically useful in a number of contexts. Alright, so maybe we stop for 10 minutes before speaking about algebraic groups. So in the previous lectures we have defined the notion of a scheme presented under at least two, perhaps three different disguises. And the main way of handling schemes is to view schemes as being functors from certain categories to sets, from category of rings to sets, or category of schemes to sets, or categories of locating spaces to sets. But of course, particular functors of particular type, not all functors will be represented by schemes, and here I have given a few examples of such functors that are represented by schemes. I would suggest that you give to yourself other examples of schemes if you're not too familiar with this approach. For instance, I defined the projective bundle associated to locally associated to a basic real sheaf of modules on a scheme S, which intuitively, when S is the spectrum of a field in M a vector space, corresponds to taking hyperplanes. But instead of taking hyperplanes, you can take subvector spaces of arbitrary given codimension, let's say, finite codimension, if you want to have something which will yield representable functors. So if you generalize this to this relative situation, you want to define a scheme, by the way, whether you're over a field or not, you will have to change the basis and then to introduce general scheme or at least general rings. Then you will be induced to construct the so-called Grassmannian bundle associated to a sheaf of modules, or the Grassmannian variety associated to a vector space. So, I mean, the existence theorem, I mean, the representability theorem is not any more difficult than in the particular case which we have treated for the projective bundle associated to M. You can also consider flag manifolds, flag bundles associated to considering in M, let's say, not just one sub module M1 such that the quotient M over M1 should locally free of a given ring, let's say N1, but within M1 also another M2 such that the quotient here should be of a given locally free of a given ring N2, etc. So when the sequence, finite sequence of integers is fixed, then we get the corresponding flag manifold over S. And between these flag manifolds you have various morphisms. Whenever we have a flag of type n1, n2, etc., we will get an object of the Grassmannian bundle, a section of the Grassmannian bundle of type n1 by just looking at m1 and forgetting the others. And that's just an example of the relations between the various bundles. Also, you have the operation of the linear group of M, the group scheme of automorphisms of M, that will operate on the corresponding bundles, whether Grassmannian or flag bundles or projective bundles. In fact, the flag bundles are the marginal ones. When I spoke about the scheme of automorphism of M over S, we have seen, at least we can speak about the function of automorphism in all cases without restriction. But if M is locally free of finite type over S, which is a more important case, then the function of automorphism of M over S in fact is representable by something which more or less is the full linear group of rank n, if n is the rank of M over S. So in this case we have in a natural way group schemes that operate on various geometric objects, various schemes. So you can spend a few hours or a few days working out some of the examples. I think it's not worthwhile to do it here on the blackboard because I mean it's all the same kind of things you've done already, but I think it's a good exercise to do it at home. What we will rather do now is to have a kind of a crossing of the desert, namely you have the notion of scheme, the morphisms of schemes, and there are 20 or 30 conditions on properties of that schemes may have or not, and that morphisms of schemes may have or not, which are of continual use in all instances where one is working with these notions of scheme and algebraic geometry. And I'm afraid I will have to expose a large part of them because they are really so often used that one can't dispense with them. So I'm going to set up, not even a dictionary, I mean just a vocabulary for today. I guess it will take us at least this lesson. So that's one of the things we have to do. Another thing which I would like to do, there are just 3 weeks left, in order to have a firm basis of the main formats of algebraic geometry, would be to speak about the questions of passage to quotient of descent. I have shown that inverse limits do exist, at least finite inverse limits in the category of schemes, and even inverse limits in many cases do exist, make a good sense. And their construction is kind of trivial, and in fact it's continually used. About any question of algebraic geometry, you have to make a lot of base changes and such things, private products. But we have not spoken much about direct limit operations, with the exception of direct sums. But passage to quotient is such an important operation. And in order to deal with it properly, one has to insert it in the notion of, in the yoga of descent and of general sheaf theory, so that one is really at ease and knows that the operations one perform passing to quotient have the usual properties with respect to taking products, private products, etc. So this I will have to explain, and this is of course quite basic also in group theory, where we have to take all the time quotient groups of a group object by invariant subgroups or homogeneous spaces under arbitrary more or less arbitrary subgroups. And in order to understand this formalism really well and to end it with all possibilities, I think it's quite important to understand this general process of passage to quotient. So this at least I would like to explain thoroughly, and what else we are going to do, I don't know. Except also there's a third type of things which we will have to do also. I think I will start today with the next lesson on group schemes, as the groups we are mainly interested in are groups over fields. Name is to develop a certain number of notions of schemes over fields, and in such a way that they should be invariant under ground field extension. So there are a number of notions to develop, and to see to what extent a certain number of geometric notions, of topological notions, are or not invariant under ground field extension. So I think this I will do within the part of the course, within the course supposed to be dedicated to algebraic groups. Won't take us too long. All right, now let's first give some compliments about the local structure of schemes. Let X be a scheme, and let small x be a point of capital X. I will define the localization of X at small x. That would be a scheme, in fact an affine scheme. By definition, it is the spectrum of the local ring of X at the point X. And I'm going to interpret now the spectrum in metric terms. Would like to point out also that I was rather painstaking, you see, in the exposition of the main fundamental notions of schemes and of the affine formalism. I think I will be a little more sketchy now. I mean, most things that I'm going to do are still kind of trivial. But I mean, once the foundation, the very notion of scheme, affine scheme, and the formalism in the affine case are well understood, these things are, which I'm going to say, are kind of trivial, and we are not going to be as detailed in checking things. All right. So, first point I want to make is that this spectrum, call it also log lower x of capital X if you want, can be viewed as being a scheme over X. There's a natural morphism of this into capital X. How are we going to define this morphism? Well, take any affine open set in U and X which contains the point X. It's a spectrum, can be viewed as a spectrum of the ring A. And then X corresponds to a prime ideal P in A, according to the affine dictionary. And we know that OXX is just the localization of A at P. And because we have the homomorphism of A into its localized module, so just the global sections of structure sheaf which go to the store, therefore in the opposite direction we have a homomorphism of the spectrum of OXX which goes into the spectrum of A, which is just U. This here is the localization, which of capital X at small x. This is contained in X. So we can look at the composite morphism into X, factors for U, and it's trivial checking that this morphism doesn't depend on the particular choice of U. So we get a morphism from the localized scheme into X. And I will give two properties of this morphism. This is a monomorphism in the category of schemes. In other words, the localized scheme can be viewed as being a subfunctor of X. And as a consequence, it is an injective map as far as underlying sets go. In fact, it is a little more than this. It's also a homeomorphism into. The topology of the localized scheme is induced by the topology of X through this canonical monomorphism. You are reduced to proving this to the affine case. And you just look at the open sets, for instance. So this here is a topological subspace of X. Now, what are its points? Well, we see the following thing. Here we have a spectrum of a local ring. A local ring is a ring which has just a unique maximal ideal. That means that the spectrum has a unique closed point. And all other points, which correspond to arbitrary prime ideals, which must be contained as a unique maximal ideal, so all other points are generalizations of the unique closed point. That is, this unique closed point is a common specialization of all other points. Now, of course, if we have a map from a scheme, a morphism from a scheme Y into another X, or even any continuous map from a topological space Y into a topological space X, and if you have 2 points Y and Y prime in Y, and if Y is a specialization of Y prime, then the image X of Y is a specialization of the image X prime of Y prime. The specialization relation is invariant by any continuous map. And therefore, if you apply this to this situation, we see